Part 2, Senior Technical Depth and Modern Infrastructure.
Welcome to Part 2 of Explain a Bad Decision You Made. In this segment, we dive into the remaining 45 questions, 55 to 99. We will cover the most difficult architectural failures involving Kubernetes, Docker, Kafka, and concurrency. We will also explore the critical areas of security, compliance, and business impact misjudgment. This is where we separate the junior responders from the senior engineers who design systems that survive the impossible.
Part 1 Recap, the Tactical Foundation.
In the first half of this series, we covered questions 1 through 54, establishing the tactical foundation for every Java support engineer. We explored production crashes, deep JVM tuning, database locks, and the essentials of incident communication. Those scenarios focused on the immediate response required to keep a system alive. Mastering those 11 categories ensures you have the technical boots on the ground expertise to handle standard production challenges.
Part 2 Transition, from triage to strategic leader.
Now in Part 2, we shift our focus from day-to-day triage to the strategic depth required for senior and lead roles. Over the next 45 questions, we will dive into complex architectural failures, modern cloud-native environments like Kubernetes, and advanced Java concurrency. We will also address high-level business impact, security compliance, and vendor management. This is where you prove to the interviewer that you do not just fix bugs, you design resilient systems.
Part 2, the Senior Expertise Categories, questions 55 to 99.
In this advanced segment, we dive into high-stakes architectural and business-critical failures. Category 12, Learning from Mistakes, the high-level reflection questions that close every interview. Category 13, Security and Compliance, handling PII leaks, access errors, and GDPR violations. Category 14, Vendor and Third-Party Integration, managing external API and SDK failures. Category 15, On-Call Handoff and Escalation, the art of seamless team collaboration. Category 16, Cloud and Containerization, troubleshooting Java pods in Kubernetes and Docker. Category 17, Concurrency, Locks and Threading, senior deep dives into deadlocks and starvation. Category 18, Message Queue and Event-Driven, handling Kafka lag, poison pills, and idempotency. Category 19, Change Management and ITIL, navigating CAB and risk assessment in regulated firms. Category 20, Capacity Planning, solving scale issues and resource limits. Category 21, Business Impact Misjudgment, product thinking and incident prioritization. Category 22, Observability Tools, mastering APM traces, metrics, and dashboard accuracy. This half of the series separates the junior responders from the senior architects.
Category 12, Learning from Mistakes.
Category 12 is often the most important part of a senior-level interview. Hiring managers know that every veteran engineer has caused an outage at some point. What they care about is your reflection and growth. These questions evaluate your maturity and your ability to implement long-term process improvements. They want to see that a mistake made early in your career changed your architectural approach forever, making you a safer and more reliable lead engineer.
Category 12, questions 55 to 59.
Hiring managers use these questions to end the interview and gauge your professional growth. 55. What is the biggest technical mistake you made in production and how did it change you? 56. What is the most expensive bug you caused in terms of revenue or business impact? 57. What specific process improvement came from a mistake you made early in your career? 58. What monitoring or observability tool would have prevented your worst production incident? 59. What single lesson changed the way you approach production systems and architectural risk? A senior engineer is defined by the depth of their reflection after a failure.
Explain a bad decision you made. Question 55, the JVM native memory leak.
Interviewer asks, what is the biggest technical mistake you made in production? Incident type, resource miscalculation, and native memory exhaustion. Interviewer insight. This is a test of your architectural humility. The interviewer is not looking for a minor typo. They want a scenario where you misunderstood a fundamental system constraint. A senior engineer discusses how they overlooked native memory and the catastrophic impact of ignoring resources outside the Java heap.
The star story and reflection.
Here is the account of my biggest technical oversight involving off-heap memory. Situation: we were upgrading a high-throughput Java data streaming application that used Netty for asynchronous I/O. The app was running in a 16 GB Linux container. Task: my task was to optimize the performance by increasing the heap size to 14 GB to handle a massive surge in incoming telemetry data. Action: the bad decision plus why it happened. I made the bad decision to allocate nearly all the container memory to the JVM heap, XMX14G. I assumed that because Netty used direct memory, it would somehow be managed within that limit or would not require much extra space. I ignored the native memory overhead required for thread stacks and C-level buffers. Result: the impact. Within 2 hours of the surge, the Linux OOMKilled terminated the Java process. The JVM was healthy, but the container had run out of physical RAM because Netty's direct buffers and the Java thread stacks pushed the total usage to 17 GB. This caused a rolling crash across the cluster, leading to a 3-hour data loss window for our telemetry platform. Reflection: I learned that the Java heap is only one room in the house. If you do not account for the native foundation, Netty buffers, JIT metadata, and thread stacks, the operating system will eventually evict your entire application. A senior engineer monitors the container, not just the JVM.
The investigation steps and root cause.
Since the JVM logs showed a clean exit without an out-of-memory error, I looked at the kernel logs. 1. Ran dmesgt on the host and found out-of-memory kill process Java entries from the Linux OOMKilled. 2. Enabled native memory tracking NMT and observed that internal and direct memory usage was exceeding 2 GB. 3. Found that each of our 500 threads was consuming 1 MB of stack memory, adding another 500 MB of off-heap pressure. 4. The root cause: native memory over-provisioning where the SUM of the heap and native overhead exceeded the hard physical limit of the container.
The technical resolution.
We rebalanced the memory allocation to ensure OS-level stability. 1. Reduce the JVM heap to 10 GB, XMX10G, providing 6 GB of native room for the OS, stacks, and Netty buffers. 2. Explicitly limited Netty's direct memory usage using -XX:max direct memory size equals 4G to prevent unbounded off-heap growth. 3. Reduced the thread stack size using XSS 512K since our deep recursion needs were minimal, saving 250 MB of RAM. 4. Implemented always pre-touch to force the JVM to commit memory at startup, allowing the container to fail fast if resources were unavailable.
What I changed forever.
I implemented these 4 structural guardrails to prevent native OOM incidents. 1. Native memory baselining mandated that all performance tests must report RSS, resident set size, from the OS, not just heap usage from the JVM. 2. The 75% rule established an architectural standard that the JVM heap must never exceed 75% of the container's total RAM allocation. 3. Automated NMT alerts configured Datadog to monitor native memory tracking metrics and alert if non-heap memory exceeds a 4 GB safety threshold. 4. Container-aware tuning migrated all deployment templates to use initial RAM percentage and max RAM percentage to allow the JVM to scale dynamically with the pod limits. We have had 0 OOMKilled incidents since moving to RSS-based monitoring.
Summary card.
Key takeaway for your interview: incident type, resource miscalculation and native memory exhaustion. Bad decision, allocating 90% of container RAM to the Java heap while ignoring Netty's off-heap requirements. Impact: 3-hour data loss window as the Linux OOMKilled terminated the process cluster-wide. Guardrail implemented: the 75% rule for heap allocation and mandatory resident set size, RSS monitoring. The JVM is a guest in the operating system's house. Respect the host's limits.
The interview-winning answer template.
My biggest technical mistake was over-provisioning a Java heap in a constrained container environment. I allocated 14 GB of a 16 GB container to the heap, forgetting that Netty buffers and thread stacks require native memory. This caused the Linux OOMKilled to crash our nodes during a traffic spike. I resolved this by rebalancing the heap to 75% of the limit and implementing native memory tracking. This taught me that senior support requires a full-stack view of memory. I have since enforced RSS-based monitoring and the 75% heap rule, which has eliminated container-level crashes in our organization.
Follow-up 1. If the JVM does not throw an out-of-memory error, but the process disappears, what is your first command on a Linux server?
Answer: my first command is dmesgtgrep IOOM. This checks the kernel ring buffer for evidence that the OOMKilled terminated the process. If that is empty, I check /var/log/messages or journoctal to see if a system-level event or a human user sent a sigkill signal.
Follow-up 2. How does native memory tracking, NMT, impact the performance of a production Java application?
Answer: NMT has a very low overhead, typically around 1 to 3% CPU impact. In a senior support role, I believe this cost is well worth the visibility it provides. We enable summary-level tracking in production by default and only switch to detail level if we are actively chasing a native leak.
Follow-up 3. Curveball. What if your RSS is growing, but NMT shows that native memory is stable? Where is the memory going?
Answer: that points to a leak outside the JVM's control, such as a JNI, Java Native Interface, library written in C or C++, or a memory-mapped file, mmap, that is not being released. I would use OS-level tools like pmap or valgrind to inspect the memory map of the PID and find the raw memory addresses that are leaking.
Pro tip: the resident set rule.
In a senior Java support role, heap usage is a vanity metric. Resident set size, RSS, is the reality. The OS kills processes based on RSS, not heap. Always monitor your application from the outside and using OS metrics to ensure your JVM is a good citizen of the host.
Explain a bad decision you made. Question 56. The rounding error.
Interviewer asks, what is the most expensive bug you caused? Incident type: data integrity and floating point precision error. Interviewer insight: this question evaluates your risk assessment and financial accuracy. In fintech and banking, a small code error can result in massive financial discrepancies. They want to see that you understand the danger of floating point math and how you implemented automated reconciliation to detect financial leaks instantly.
The star story and reflection.
Here is the account of how a quick performance optimization cost $250,000. Situation: we were processing 10 million currency conversions per day for a global payment platform. The original Java code used big decimal for all calculations. Task: my task was to optimize the processing speed of our exchange rate engine, which was hitting 100% CPU during peak hours. Action: the bad decision plus why it happened. I made the bad decision to refactor the inner loop to use the primitive double type instead of big decimal. I assumed that for simple currency math, the precision loss would be negligible and the 10 times performance boost was worth the risk. I was chasing processing speed over data integrity. Result: the impact. After 30 days, the finance team performed a monthly audit and found a $250,000 discrepancy in our balance sheets. The tiny rounding errors in the double calculations had accumulated over 300 million transactions. We had to halt all international payments for 48 hours and perform a manual data correction on millions of records. Reflection: I learned that in finance, accuracy is the only metric that matters. If you optimize for speed and lose a single cent, you have not optimized the system. You have broken it. Performance should never come at the expense of precision. Precision is the foundation of trust in financial systems.
The investigation steps and root cause.
As the finance team reported the missing funds, we audited the calculation logic. 1. Compared the database records with the raw logs and identified a drift of 0.0001 per transaction on specific currency pairs. 2. Created a Java test case to reproduce the math using both double and big decimal and confirmed the binary floating point error. 3. Found that the double type was unable to represent exact decimal fractions, like 0.1, leading to truncation during summation. 4. The root cause: inappropriate data type selection, where the use of binary floating point math for decimal financial calculations led to cumulative rounding errors.
The technical resolution.
We restored the financial accuracy and implemented strict math standards. 1. Immediately reverted the exchange engine to use big decimal with half_even rounding, bankers rounding, to restore precision. 2. Developed a repair batch in Java that recalculated all 300 million transactions from the last month and generated adjustment entries. 3. Configured a global math context with a scale of 12 to ensure that even intermediate calculations remained highly precise. 4. Implemented a daily automated reconciliation job that compares the SUM of individual transactions with the expected total and alerts on any drift exceeding $1.
What I changed forever.
I implemented these 4 structural guardrails for financial data integrity. 1. Mandatory big decimal policy established a hard-coded rule in our Sonar Quebec linter that fails the build if double or float is used for any variable tagged as currency. 2. Bankers rounding standard standardized the use of rounding mode .half_even across all financial microservices to ensure unbiased rounding errors in large datasets. 3. Real-time drift monitoring integrated a custom Prometheus metric that tracks the precision error of sample calculations, alerting us if the system drifts by even 1 cent. 4. Data integrity unit tests mandated a financial edge case test suite for all releases that validates math accuracy for 15 decimal places across 1 million iterations. We have reduced our financial discrepancy incidents to 0 since implementing these standards.
Summary card.
Key takeaway for your interview. Incident type, data integrity and floating point precision error. Bad decision, switching from big decimal to double for currency math to gain a 10 times performance boost. Impact, $250,000 cumulative discrepancy over 300 million transactions and a 48-hour payment blackout. Guardrail implemented, mandatory big decimal linting and real-time financial drift monitoring dashboards. In Java support, correctness is the only performance metric that counts in finance.
The interview-winning answer template.
The most expensive bug I caused was a financial precision error. I refactored a currency conversion loop to use the double type instead of big decimal for a 10 times speed boost. Over a month, this created tiny rounding errors that accumulated into a $250,000 discrepancy. I resolved this by reverting to big decimal and leading a massive data repair effort. This taught me that performance should never compromise data integrity. I have since implemented mandatory static analysis rules and daily reconciliation jobs, which have completely eliminated financial math errors in our system.
Follow-up 1. Why is rounding mode .half_even bankers rounding preferred for large-scale financial systems?
Answer, it minimizes cumulative error. Standard rounding, half_up, always rounds. 5 up, which creates an upward bias in large sums. Half_even rounds to the nearest even number, meaning it rounds up 50% of the time and down 50% of the time, effectively canceling out the rounding error.
Follow-up 2. If big decimal is too slow for a real-time system, how do you handle precision without losing speed?
Answer, I use long-based math. We represent all currencies as their smallest unit, for example, cents for USD, and perform integer math using the long type. This provides the speed of primitives while maintaining 100% precision for additions and subtractions. We only convert back to decimal for display purposes.
Follow-up 3. Curveball. What if the rounding error is coming from the database level and not the Java level? How do you isolate it?
Answer, I compare the SUM of records in the database with the SUM of logs from the Java application. If the Java logs show precise values but the database shows rounded ones, I check the column type. Using float or real in SQL is just as dangerous as using double in Java. I always advocate for the decimal or numeric type for financial data.
Pro tip, the cent rule.
In a senior Java support role, remember, you do not own the money, you own the math. If your application handles a single cent of customer money, primitives are off limits. Use big decimal or long and verify your rounding modes, or you will eventually face an audit you cannot win.
Explain a bad decision you made. Question 57. The manual key disaster.
Interviewer asks, what process improvement came from your mistake? Incident type, manual process failure and lack of lifecycle automation. Interviewer insight. This question measures your operational leadership. They want to see that you did not just fix a technical bug, but you identified a flaw in the human workflow. A senior engineer discusses how they replaced a manual, error-prone procedure with a zero-touch automated process to eliminate human fallibility.
The star story and reflection.
Here is the account of how a manual security update led to a company-wide automation mandate. Situation: we were managing a Java cluster that communicated with a legacy mainframe using client-side SSL certificates. These certificates required rotation every 90 days. Task: my task was to manually update the Java Trust Store on 40 production nodes with the new certificate and perform a rolling restart. Action: the bad decision plus why it happened. I made the bad decision to rely on a manual 15-step runbook. Because it was a repetitive task I had done twice before, I became overconfident and skipped the validation step on the final 5 nodes. I assumed the copy-paste command had succeeded because the terminal did not show an error. Result: the impact. Those 5 nodes were left with the old certificate. When the mainframe switched to the new key at midnight, 12% of our traffic began failing with SSL handshake exception. We suffered a 4-hour partial outage that impacted $110,000 in transaction volume and required an emergency midnight bridge call. Reflection: I learned that any process requiring a human to repeat a manual step 40 times is not a process. It is a statistical guarantee of failure. If a task is critical for security or availability, it must be governed by code, not by a runbook. Confidence is a poor substitute for automation.
The investigation steps and root cause.
As the SSL errors began spiking in Splunk, we identified the discrepancy. 1. Ran a distributed shell command to check the MD5 hash of the truststore.jks file across all 40 nodes. 2. Identified that 35 nodes had the new hash, but 5 nodes were still running the version from the previous quarter. 3. Used keytool list to inspect the certificate aliases and confirmed the mainframe CA entry was missing the new expiry date on the failing nodes. 4. The root cause, manual execution variance, where a human error during a repetitive CLI task led to environment drift and a security handshake failure.
The technical resolution.
We restored the security chain and moved toward a hands-off infrastructure. 1. Immediately synchronize the trust store files across the 5 failing nodes using an emergency Ansible ad hoc command. 2. Performed a graceful JVM restart on the impacted nodes to reload the trust store into memory and restore connectivity. 3. Developed a Java startup interceptor that logs the MD5 hash and expiry date of all loaded certificates, allowing us to see the identity of every node in the logs. 4. Initiated an emergency project to migrate our certificate management to AWS Certificate Manager and HashiCorp Vault to remove manual handling entirely.
What I changed forever.
I implemented these 4 structural guardrails to eliminate manual configuration errors. 1. The script-only mandate established a hard rule that no configuration change, SSL properties or keys, can be performed via manual SSH. All changes must be applied via Ansible or Terraform. 2. Automated trust store verification. Integrated a check into our CI/CD pipeline that automatically verifies the trust store contents against the expected manifest before a deployment is allowed. 3. Certificate expiry monitoring. Configured a Prometheus alert that scans the live JVM key store and triggers a P3 ticket 30 days before any certificate expires. 4. Post-change MD5 audit. Implemented an automated post-deployment check that compares the file hashes across all nodes in a cluster and fails the release if a single node is out of sync. We have had 0 SSL-related outages in the 2 years since automating this process.
Summary card.
Key takeaway for your interview. Incident type: manual process failure and lack of lifecycle automation. Bad decision: relying on a manual 15-step runbook for SSL certificate rotation across 40 nodes. Impact: partial system blackout and $110,000 revenue loss due to SSL handshake exceptions on 5 misconfigured nodes. Guardrail implemented, mandatory Ansible automation for all config changes, and automated MD5 hash sync auditing. Standardize your failures so you can automate your successes.
The interview-winning answer template.
My biggest process improvement came after I made the mistake of manually rotating SSL certificates across 40 nodes. I missed 5 nodes due to overconfidence, leading to a $110,000 loss when those nodes failed to connect. I resolved this by automating our trust store management via Ansible. This taught me that manual runbooks are an operational risk. I have since enforced a zero manual touch policy for all production configuration. We now use automated hash verification and expiry alerts, which has completely eliminated SSL-related environment drift in our organization.
Follow-up 1. If a certificate rotation requires a JVM restart, but you are in a zero downtime environment, how do you handle it?
Answer: I use a rolling update strategy. We take one node out of the load balancer, apply the change, verify the handshake on a test port, and then put it back. We automate this using a blue or green deployment pattern or a Kubernetes rolling update to ensure the user never sees a connection error.
Follow-up 2. How do you verify that a Java application has correctly loaded a new certificate without restarting the entire JVM?
Answer: in standard Java, the trust manager is initialized at startup and is immutable. To reload without a restart, I would implement a dynamic trust manager that monitors the file system for changes and reloads the key store programmatically. Otherwise, a graceful restart is the only way to ensure the new key is in the active memory buffer.
Follow-up 3. Curveball. What if you automate the rotation, but the source certificate provided by the vendor is corrupt? How does your automation handle that?
Answer: this is why we use pre-flight validation. The script should attempt to perform a test handshake with the new certificate against a sandbox endpoint before pushing it to production. If the handshake fails, the automation halts and alerts the team. We never trust a file simply because it was delivered.
Pro tip: the automation threshold.
In senior support, if you find yourself doing a technical task for the 3rd time, you are no longer an engineer. You are a script. Spend the extra hour to automate the task, or you will spend a career fixing its inevitable manual errors.
Explain a bad decision you made. Question 58. The invisible deadlock.
Interviewer asks, what monitoring would have prevented that incident? Incident type: observability gap and thread deadlock. Interviewer insight: this question tests your SRE maturity. Most candidates talk about CPU or memory. A senior engineer discusses internal resource health like thread states and connection pool wait times. They want to see that you understand that a healthy server can still be a failing application if you are looking at the wrong metrics.
The star story and reflection.
Here is how basic monitoring failed to detect a total system hang. Situation: we were managing a Java-based insurance platform. Our standard monitoring suite tracked CPU, RAM, and disk usage at the OS level. Task: during a month-end processing surge, the system stopped processing all claims, but our health dashboards remained green. Action: the bad decision plus why it happened. I had designed the monitoring alerts to trigger only if CPU exceeded 90% or memory exceeded 85%. I made the bad decision to skip internal thread state monitoring because I thought the OS level metrics would be sufficient for a standard Java app. I focused on infrastructure health rather than application logic health. Result: the impact. The application had entered a circular deadlock in a logging module. CPU dropped to 2% and memory remained flat. Because the system looked healthy to our alerts, the outage lasted for 3 hours before a customer reported the failure. We missed our claim processing SLA for 5,000 customers. Reflection: I learned that quiet is not the same as healthy. A server at 2% CPU is often more dangerous than one at 90%. If your threads are blocked, the OS metrics will tell you the system is fine while the users see a blackout. Monitor the work, not just the resources.
The investigation steps and root cause.
As I logged into the healthy-looking server, I performed a deep Java audit. 1. Took a thread dump using JCMD and identified 2 threads in blocked state waiting on each other. 2. Found that a custom audit logger was using a synchronized block that conflicted with a transaction interceptor. 3. Observe that the incoming request count was spiking in the load balancer, but the thread pool active count in Java was stuck at its maximum. 4. The root cause. Observability gap where we were monitoring symptoms, CPU, but not the work pipe active threads and locks, allowing a deadlock to remain invisible.
The technical resolution.
We broke the deadlock and modernized our observability stack. 1. Immediately performed a rolling restart to clear the deadlocked threads and restore the claim processing flow. 2. Refactored the Java code to use reentrant lock with a try-lock timeout, ensuring that a thread would fail fast rather than hanging indefinitely. 3. Removed the nested synchronized blocks in the audit logger and moved to an asynchronous log publishing model using an executor service. 4. Implemented micrometer metrics to export the state of every thread pool and connection pool directly to Prometheus.
What I changed forever.
I implemented these 4 structural guardrails for deep-level monitoring. 1. Active thread alerting. Configured an alert that triggers if the blocked thread count exceeds 5% of the pool size for more than 2 minutes. 2. The low CPU anomaly alert. Implemented a negative alert that triggers if request volume is high but CPU usage is abnormally low, identifying deadlocks instantly. 3. Automated JFR profiling. Integrated Java flight recorder to automatically start a 60-second capture if an API response time exceeds 5 seconds, providing a time machine of the failure. 4. Hikari CP wait time monitoring. Added dashboard tiles for connection acquisition delay. We now alert if a thread waits more than 1 second for a database connection. We reduced our mean time to detection, MTTD, from 3 hours to 3 minutes.
Summary card.
Key takeaway for your interview. Incident type, observability gap and thread deadlock. Bad decision, relying solely on OS-level metrics, CPU or RAM, and ignoring internal JVM thread states. Impact, 3-hour silent outage for 5,000 customers because the health dashboards remained green during a deadlock. Guardrail implemented, active thread state monitoring, and low CPU/high traffic anomaly alerting. A green dashboard is a lie if it is not measuring the business logic.
The interview-winning answer template.
During a claim processing outage, I realized that our standard CPU and memory monitoring were completely insufficient. We suffered a 3-hour hang due to a Java deadlock, while our dashboard stayed green because CPU was at 2%. I resolved this by implementing internal thread state monitoring. This taught me that you must monitor the pipe as much as the resources. I have since implemented block thread alerting and Hikari CP wait time metrics, ensuring that silent hangs are detected in minutes rather than hours.
Follow-up 1. How do you identify a thread leak using monitoring before the application actually crashes?
Answer: I track the total thread count metric over a 24-hour period. If the count is steadily rising after every deployment or after specific traffic peaks, and it never returns to the baseline, you have a leak. I would then use JStack to see what those leaking threads are named and what they are waiting for.
Follow-up 2. What is the benefit of monitoring P99 latency versus just average latency?
Answer: average latency masks the suffering of your users. P99 shows the worst-case scenario. If your average is 100 milliseconds but your P99 is 30 seconds, it means 1% of your users are experiencing a total system failure. In senior support, we alert on P99 to catch long-tail issues like GC pauses or locking early.
Follow-up 3. Curveball. What if your monitoring tool itself is what is slowing down the application? How do you diagnose monitoring overhead?
Answer: I look for agent-induced overhead in a CPU profile. If the top consuming methods are related to the APM agent, for example, Dynatrace or New Relic, I would reduce the sampling rate or disable deep transaction tracing for high-frequency methods. Monitoring should be a passive observer, never a resource competitor.
Pro tip: the zero usage rule.
In a senior Java support role, remember, flatline CPU with high traffic is a crash. Always implement alerts that monitor the correlation between incoming requests and resource usage. If the system stops using resources while requests are coming in, the engine has stalled.
Explain a bad decision you made. Question 59. The dependency domino.
Interviewer asks, what lesson changed the way you approach production systems? Incident type, architectural trust and cascading failure. Interviewer insight, This is a philosophy question. They want to see that you have evolved from hope-based architecture to defensive architecture. A senior engineer discusses the isolation principle and how they learn to never trust a dependency, whether it is an internal API or a third-party SDK.
The star story and reflection.
Here is the account of the lesson that turned me into a defensive architect. Situation: we were managing a high-volume retail platform where our Java application called a third-party loyalty SDK to display points to users on the home screen. Task: my task was to ensure the home screen remained fast and responsive during our annual Black Friday event. Action: the bad decision plus why it happened. I made the bad decision to trust the loyalty SDK's internal timeouts. I assumed that because it was a reputable vendor, they would handle their own network failures gracefully. I integrated the SDK directly into the main thread of the homepage without a wrapper or a circuit breaker. Result: the impact. During the event, the vendor's API slowed down but did not crash. Each homepage request now took 15 seconds to wait for the loyalty points. Within 10 minutes, our entire Java thread pool was exhausted. The home screen crashed for 100% of users, and we lost an estimated $400,000 in revenue because our home page was held hostage by an optional feature. Reflection: I learned that in a distributed system, trust is a technical debt. If you do not wrap a dependency in a circuit breaker, you are essentially giving a stranger permission to crash your entire application. This lesson changed my approach from optimistic integration to pessimistic isolation. An optional feature should never be a mandatory source of failure.
The investigation steps and root cause.
As the homepage response times hit 20 seconds, we performed an isolation audit. 1. Captured a JStack dump and found that 400 HTTP worker threads were in socket read state inside the vendor's jar file. 2. Used TCP dump to confirm that the vendor's server was taking 14.8 seconds to return a simple JSON payload. 3. Identified that our application had 0 in-app timeouts configured for this specific SDK call. 4. The root cause, unbounded dependency trust, where a non-critical feature was allowed to consume 100% of the system's request handling capacity during a bottleneck.
The technical resolution.
We stabilized the platform and implemented the isolation principle. 1. Immediately used a feature flag to disable the loyalty module, which instantly released the blocked threads and restored the homepage speed. 2. Refactored the Java code to wrap all vendor SDK calls in a resilience 4J circuit breaker with a strict 1-second timeout. 3. Implemented an async fallback mechanism. If the loyalty points do not load in 500 milliseconds, we show a loading spinner and allow the rest of the page to render. 4. Moved all non-critical dependency calls to a dedicated, isolated slow pool to ensure they can never starve the main application thread pool.
What I changed forever.
I implemented these 4 structural guardrails to ensure architectural resilience. 1. The circuit breaker first rule mandated that no external network call, API or DB, can be added to the code without a verified circuit breaker and a fallback strategy. 2. Dependency impact audits established a rule that every third-party SDK must be load-tested in failure mode to see how the app behaves when that dependency hangs. 3. Isolation of concerns enforced a standard where critical business paths, like checkout, must be physically or logically isolated from optional paths, like loyalty or analytics. 4. Zero downtime fallbacks mandated that every UI component must have a graceful degradation plan. If the backend fails, the user should see a simplified working experience. We have reduced our cascading failure incidents to 0 since adopting the isolation principle.
Summary card.
Key takeaway for your interview: incident type, architectural trust and cascading failure. Bad decision, trusting a vendor SDK's internal timeouts and integrating it directly into the application's main thread pool. Impact: homepage blackout for 100% of users during Black Friday and $400,000 in lost revenue. Guardrail implemented, mandatory resilience 4J circuit breakers, and the isolation of concerns architectural standard. Resilience is not an accident. It is a design choice.
The interview-winning answer template.
The single lesson that changed my career is never trust your neighbors. I once crashed a retail platform during Black Friday because I trusted a third-party SDK to handle its own timeouts. It did not, and it held our main threads hostage for 15 seconds, costing us $400,000. I resolved this by implementing circuit breakers and fallback logic. This taught me that every dependency is a liability. I have since pioneered a defensive isolation architecture, where every external call is wrapped in a circuit breaker, and critical paths are protected from optional feature failures.
Follow-up 1. What is the difference between a timeout and a circuit breaker, and why do you need both?
Answer: a timeout stops a single request from hanging. A circuit breaker stops all requests to a failing service for a period of time. You need a timeout to protect the thread, and a circuit breaker to protect the entire system from trying to talk to a dead neighbor repeatedly.
Follow-up 2. How do you decide when to open the circuit versus just slowing down the requests?
Answer: I use error rate and slow call thresholds. If 50% of requests fail or exceed our latency target, we open the circuit. In senior support, we prefer to fail fast and show a cached value than to let the user wait 10 seconds for a 503 error.
Follow-up 3. Curveball. What if the dependency is your own database? Can you use a circuit breaker for your primary DB?
Answer: yes, but the fallback is different. For a DB, the circuit breaker might trigger a switch to a read-only cache or show a maintenance message. You cannot just skip the DB, but you can prevent your Java app from becoming a zombies by failing fast when the DB is unresponsive.
Pro tip, the neighbor rule.
In a distributed Java architecture, your application is a castle and every API or database is a gate. Never leave a gate wide open. If you do not have a circuit breaker, you do not have a wall. You just have an invitation for a cascading failure.
Category 12 wrap-up, the growth lesson.
We have explored the profound personal and process-level growth that comes from our worst failures. The lesson is that a senior engineer is not someone who never makes mistakes, but someone who ensures those mistakes result in systemic change. However, in today's landscape, a mistake is not just about uptime. It is about protection. A leak of customer data or a compliance breach can be more damaging than a total system blackout. This brings us to Category 13, Security and Compliance Mistakes.
Category 13, Security and Compliance Mistakes.
In a senior Java support role, you are a custodian of the company's most sensitive assets, its data and its reputation. Security is no longer a separate department. It is a core operational requirement. This category evaluates your security-first mindset and your ability to weigh operational urgency against regulatory risk. Interviewers want to see that you understand the gravity of GDPR, PCI, and PII protections, even when you are under the pressure of a P1 outage.
The security challenge, questions 60 to 64.
Be prepared to discuss these high-stakes compliance and security failures in your next interview. 60. Tell me about a time you accidentally logged sensitive data like PII passwords or tokens. 61. Describe a situation where you granted excessive production access to resolve an incident quickly. 62. Have you ever bypassed a security policy or change approval process during an urgent outage? 63. Tell me about a time a compliance violation like GDPR or PCI happened because of a change you made. 64. Explain a mistake involving missing data masking or encryption in application logs. Interviewers evaluate your risk assessment skills and your commitment to regulatory safety.
Explain a bad decision you made. Question 60, the PII log leak.
Interviewer asks, tell me about a time you accidentally logged sensitive data. Incident type, data privacy breach and observability misconfiguration. Interviewer insight. This question tests your compliance awareness. Logging a password or a credit card number is a major security incident. A senior engineer explains how they moved from object-level logging to pattern-based masking to ensure that even if a developer makes a mistake, the system protects the data.
The star story and reflection.
Here is the account of how a simple debug log exposed 50,000 customer credit cards. Situation: we were troubleshooting a complex payment routing bug in our Java microservice. The errors were inconsistent and only happened with specific international cards. Task: my task was to identify the exact field in the JSON payload that was causing the payment gateway to reject the transaction. Action: the bad decision plus why it happened. To see the full context, I made the bad decision to enable debug logging for the entire request object. I assumed that because the card number field was in a sub-object, our standard logger would handle it. I did not verify if the lombok@toString annotation on the card details class had been configured to exclude sensitive fields. Result: the impact. For 24 hours, our central logging system, Splunk, recorded the full credit card numbers and CVVs for 50,000 transactions in plain text. This was a direct PCI-DSS violation. We had to rotate the encryption keys for our entire log store and report the breach to the compliance office, resulting in a 48-hour emergency cleanup operation. Reflection: I learned that convenience logging is a security nightmare. You should never log a raw object in production. If you cannot describe exactly what you are logging too much. In production, blind logging is a breach waiting to happen.
The investigation steps and root cause.
Once the security team flagged the plain text data in Splunk, we performed a forensic audit. 1. Search for patterns matching 40 to 912, 0 to 93, Visa in the last 24 hours of logs. 2. Identified the specific Java class and method that initiated the log.debug request object call. 3. Found that a recent developer update had added the lombok@data annotation to the payment request DTO without an @toString dot exclude on the sensitive fields. 4. The root cause, implicit serialization failure, where a broad lombok-generated toString parentheses method was used on a sensitive object in a production log path.
The technical resolution.
We sanitized the environment and hardened the logging framework. 1. Immediately deployed a hotfix to change the log level to info and added @toString dot exclude to all PII-related fields in the Java domain model. 2. Used the Splunk delete API to purge the sensitive records from the indexers across all clusters. 3. Implemented a custom logback masking pattern layout that uses regex to replace card numbers and emails with at the moment of log generation. 4. Added a privacy interceptor to our HTTP client that intercepts the JSON body and masks sensitive keys before they reach the logging appender.
What I changed forever.
I implemented these 4 structural guardrails to prevent data leaks in logs. 1. Mandatory PII linting. Integrated a security linter, like checkmarks or snike, into our CI/CD pipeline that fails the build if any lombok@data class contains PII without exclusions. 2. Log gatekeeper architecture. Configured a central log proxy that scans all outgoing logs for regex patterns matching credit cards or SSNs and drops the messages automatically. 3. Selective logging standard. Established a hard rule that no object-level logging is allowed in production. Engineers must explicitly log individual non-sensitive primitive fields. 4. Annual security and code training. Initiated a mandatory workshop for the Java team focusing on secure logging and data serialization pitfalls. We have had 0 PII leak incidents since automating our log masking policy.
Summary card.
Key takeaway for your interview. Incident type: data privacy breach and observability misconfiguration. Bad decision: enabling debug-level logging for a raw request object that contained PII via a lombok-generated toString method. Impact: PCI-DSS violation, exposing 50,000 credit card numbers, and a 48-hour emergency data purge operation. Guardrail implemented. Mandatory regex-based log masking and automated CI/CD linting for PII fields. If data is sensitive in the database, it is sensitive in the logs.
The interview-winning answer template.
During a complex payment troubleshooting session, I made the bad decision to enable debug logging for a full request object. I did not realize a lombok annotation was including credit card numbers in the output, which resulted in 50,000 plain text cards being logged to Splunk. I resolved this by purging the logs and implementing regex-based masking. This taught me that raw object logging is a major security risk. I have since enforced a selective logging standard and automated PII detection in our pipeline, which has completely eliminated data leak risks in our observability stack.
Follow-up 1. If you mask the data, How do you debug an issue that is specific to a certain credit card or user ID?
Answer: we use cryptographic hashing or opaque tokens. We log the SHA-256 hash of the ID. This allows us to search and correlate logs for the same user without ever knowing their actual identity. It provides traceability without compromising privacy.
Follow-up 2. What is log injection and how do you protect your Java application from it?
Answer: log injection occurs when an attacker puts new line characters into a request field to create fake log entries. I protect against this by using structured JSON logging. Since every entry is a JSON object, new lines within a field do not break the log format or allow for fake record creation.
Follow-up 3. Curveball. What if a developer insists that logging PII is required for troubleshooting a P1? How do you handle that request?
Answer: I say no. No outage justifies a permanent security breach. I would suggest alternative methods, such as remote debugging in a staging environment that has masked production data, or adding temporary specific tracing that only logs the metadata of the error, never the PII itself.
Pro tip, the Lombok rule.
In a senior Java role, never use @data on a class that holds PII. Use @getter and @setter individually and manually override to string parentheses to ensure sensitive fields stay out of your logs. Your code should be private by default.
Explain a bad decision you made. Question 61. The pseudo panic.
Interviewer asks, describe a situation where you granted excessive production access. Incident type: identity and access management, IAM. Failure. Interviewer insight: this question evaluates your access discipline. During a crisis, it's tempting to give everyone root to fix it faster. They want to see how you moved from static broad access to just-in-time, JIT least privilege models to protect the production environment from well-intentioned human errors.
The star story and reflection.
Here is the account of how generous access during an outage led to a secondary disaster. Situation: at 2 a.m., our primary orders database became locked due to a corrupted index. The entire support team and 3 developers from the warehouse team were on the bridge. Task: my task was to coordinate the troubleshooting and ensure the DBAs had the technical context they needed to clear the locks. Action: the bad decision plus why it happened. I was overwhelmed by the pressure to restore service. I made the bad decision to grant read-write access to the entire SQL cluster for all 3 developers so they could self-serve their diagnostic queries. I bypassed the standard request and approve workflow to save 10 minutes of administration time. Result: the impact. One of the developers, unfamiliar with the production schema, accidentally ran an update query without a where clause on a small metadata table while trying to clean up his session. This caused a secondary outage that broke our shipping label generation for 6 hours. My attempt to save 10 minutes caused a $60,000 operational loss. Reflection: I learned that access is a liability. Giving a developer more power than they need is not helping them. It is setting them up to make a high-stakes mistake. Speed should never be gained by sacrificing guardrails. Excessive access is an invitation for an accident.
The investigation steps and root cause.
As the shipping system began failing, we audited the database activity. 1. Ran pg_stat_activity and identified an active transaction from a non-DBA user account. 2. Checked the database audit logs and found a bulk update executed on the shipping_carriers table with 0 filters. 3. Traced the user account to one of the warehouse developers who I had granted broad access to 2 hours prior. 4. The root cause: violation of least privilege where broad write access was granted to non-experts during a high-stress incident, leading to an accidental data modification.
The technical resolution.
We restored the data and revamped our access protocols. 1. Performed an emergency data restoration of the shipping_carriers table from the most recent WL write-ahead log backup. 2. Immediately revoked the temporary broad access for all non-DBA users and moved them back to read-only roles. 3. Implemented database proxy, like Proxy SQL, that automatically blocks any DML query, update, or delete, missing a where clause. 4. Initiated a postmortem to apologize to the shipping team and took full ownership of the access misconfiguration.
What I changed forever.
I implemented these 4 structural guardrails for production access management. 1. Just-in-time JIT access migrated all production access to a tool like CyberArk or Teleport, where permissions are granted for exactly 2 hours and then automatically revoked. 2. Mandatory dual approval established a policy that even during a P1 outage, write access requires a digital thumbs up from both an incident commander and a security lead. 3. Read-only by default configured all developer accounts to have read-only access to production replicas, ensuring they can debug without the risk of modifying data. 4. Automated access audits implemented a weekly script that scans for any stale or orphaned high-privilege accounts and automatically disables them. We have reduced our accidental data modification incidents to 0 since adopting JIT access.
Summary card.
Key takeaway for your interview. Incident type: Identity and Access Management (IAM), failure, bad decision, granting broad read-write DB access to developers during a P1 outage to save time on administrative overhead. Impact: accidental bulk data update by a non-expert, causing a secondary 6-hour outage and $60,000 loss. Guardrail implemented. Just-in-time, JIT, access management and mandatory dual approval for write permissions. The fastest way to fix an incident is with the right experts, not the most experts.
The interview-winning answer template.
During a major database outage, I made the bad decision to grant broad write access to several developers to help speed up the fix. One developer accidentally wiped a metadata table, which caused a secondary 6-hour outage. I resolved this by restoring the data and then leading an overhaul of our access policies. This taught me that least privilege is non-negotiable, even in a crisis. I have since implemented just-in-time access and dual approval workflows, which ensures that production power is only granted when necessary, and always with a safety net.
Follow-up 1. How do you balance security with speed when every minute of an outage costs thousands of dollars?
Answer: I use automated security. By having a JIT tool like Teleport pre-configured, I can grant access in 30 seconds with a single Slack approval. Speed does not come from skipping security. It comes from automating it so it is not a bottleneck.
Follow-up 2. What is the difference between authentication and authorization in a production support context?
Answer: authentication is verifying who you are, for example, your LDAP login. Authorization is verifying what you can do, for example, your permission to run an update query. In senior support, most mistakes are authorization failures, where we give a user the right login but the wrong level of power.
Follow-up 3. Curveball. What if the incident commander is the one asking for excessive access? How do you say no?
Answer: I frame it as risk mitigation. I say, I can grant you read-only access immediately. If we need write access, we should use a DBA-reviewed script to ensure we do not cause a secondary outage. I offer a safe path rather than a flat refusal.
Pro tip: the JIT rule.
In a senior Java support role, permanent access is a security hole. If you do not use a permission every day, you should not have it. Transition your team to temporary elevate models, where permissions die automatically after the work is done.
Explain a bad decision you made. Question 62. The policy shortcut.
Interviewer asks, have you ever bypassed a security policy or change approval process during an urgent incident? Incident type: process bypass and unauthorized production change. Interviewer insight: this question evaluates your integrity under pressure. Interviewers know that P1 outages are stressful, but they want to see if you respect the chain of command. A senior engineer explains how they learned that bypassing a safety policy often creates a larger disaster, and how they implemented emergency change tracks to ensure speed and compliance can coexist.
The star story and reflection.
Here is the account of how a quick fix bypassed the security audit and led to a secondary crisis. Situation: it was 3 a.m. during a total blackout of our retail banking API. The issue was a misconfigured thread pool size in a hidden properties file. Task: my task was to update the configuration and restart the Java cluster as fast as possible to meet a strict 30-minute recovery SLA. Action: the bad decision plus why it happened. I made the bad decision to bypass the official change advisory board, CAB, emergency ticket process, and the two-factor authentication check on our deployment gateway. I used a backdoor SSH key to edit the file directly on the production nodes. I assumed the urgency of the outage justified ignoring the admin audit trail. Result: the impact. While the fix worked, my manual change was not recorded in the central GitOps repository. 2 days later, an automated deployment overrode my manual fix with the old broken configuration, causing a second identical outage. Furthermore, the security audit team flagged the unauthorized access, resulting in a formal disciplinary review and a week-long audit of the entire support team's access. Reflection: I learned that safety policies are not red tape, they are system memory. If a change is not audited, it does not exist for the rest of the automation stack or the team. A fix that is not audited is just a delayed failure.
The investigation steps and root cause.
During the postmortem, we analyzed why the fix failed to persist. 1. Compared the live server configuration with the Git version control and found a significant configuration drift. 2. Checked the audit log of the deployment gateway and found 0 entries for the 3 a.m. change event. 3. Identified that my manual SSH access had bypassed the pre-deployment hook that normally synchronizes changes back to Git. 4. The root cause: process circumvention, where a manual change outside the established CI/CD pipeline led to a loss of configuration integrity and an audit violation.
The technical resolution.
We stabilized the process and removed the backdoor risks. 1. Immediately synchronized the properties change into the master Git branch and triggered a full pipeline deployment to ensure all nodes were identical. 2. Decommissioned the legacy SSH backdoor keys and replaced them with a session-based access manager that requires a Jira ticket ID to initialize. 3. Implemented an emergency CAB Slack bot that can grant authorized approval in under 60 seconds, removing the incentive to bypass the process. 4. Added a drift detector in our monitoring stack that alerts the team if any production file differs from its Git source by even a single byte.
What I changed forever.
I implemented these 4 structural guardrails to ensure speed with compliance. 1. Emergency change standard. Created a break glass deployment track that allows for 2-minute releases while still maintaining a full audit trail and peer review requirement. 2. Automated Git sync. Configured all production servers to be read-only at the OS level, ensuring that changes can only be applied through the CI/CD pipeline. 3. Audit failure alerts. Configured a real-time alert for any direct SSH login to a production node, triggering an immediate security investigation. 4. Zero manual touch culture. Initiated a policy-first training for all on-call engineers, emphasizing that the audit trail is as important as the fix during a P1 outage. Compliance is the framework that allows for sustainable speed.
Summary card.
Key takeaway for your interview: incident type, process bypass and unauthorized production change. Bad decision: bypassing the CAB process and MFA to manually edit a production config file during a 3 a.m. outage. Impact: recurring outage 2 days later due to configuration drift and a major security audit failure. Guardrail implemented: break glass emergency deployment tracks and OS-level read-only enforcement. Never trade auditability for urgency.
The interview-winning answer template.
During a high-pressure P1 outage, I made the bad decision to bypass our emergency change process and MFA to apply a configuration fix manually via SSH. While it restored the service temporarily, the change was overwritten by our automation 2 days later, causing a second outage and a security audit failure. This taught me that safety policies are essential for system integrity. I have since pioneered an emergency fast-track process that allows for 60-second authorized changes while maintaining a full audit trail. This has ensured that our team can act fast without ever sacrificing compliance or long-term stability.
Follow-up 1. If the emergency CAB members are all asleep and you have a 100% blackout, what is your move?
Answer: I follow the post-facto approval policy. I record my actions in the ticket, notify the security channel, and proceed with the fix using the official pipeline. I never use a backdoor. A senior engineer understands that being authorized to fail is better than being unauthorized to succeed.
Follow-up 2. What is the risk of having a manual SSH option at all in a modern Java environment?
Answer: the risk is unintended side effects. A human typing in a terminal can make a typo, delete the wrong directory, or leave a session open. In senior support, We advocate for immutable infrastructure where SSH is disabled and servers are replaced rather than repaired.
Follow-up 3, curveball. What if a vice president is telling you to just fix it now and ignore the CAB process? How do you respond?
Answer, I offer a compromise of speed. I say, I can apply this through our emergency pipeline in 3 minutes, which ensures the fix is permanent and audited. This is faster and safer than a manual fix which might be overwritten by the next deployment. I use logic to maintain the policy while respecting their urgency.
Pro tip, the audit law.
In a senior Java support role, remember, an unaudited change is a ghost. It will haunt your team in the next deployment, and it will fail you in your next compliance review. Always use the pipeline, even when the house is on fire.
Explain a bad decision you made. Question 63, the GDPR data leak.
Interviewer asks, tell me about a time a compliance violation happened because of a change you made. Incident type, regulatory breach and data sovereignty violation. Interviewer insight. This question tests your regulatory awareness. Interviewers want to know if you understand that data has borders and privacy laws. A senior engineer discusses the mistake of moving production data into a non-compliant environment and how they implemented data anonymization to prevent future breaches.
The star story and reflection.
Here is the account of how an innocent data export became a GDPR violation. Situation: we were troubleshooting a data-dependent bug where certain European customers could not view their invoices in our Java portal. The issue could not be reproduced with dummy data. Task: my task was to identify the specific record corruption that was causing the Java null pointer exception in the invoice generator service. Action: the bad decision plus why it happened. I made the bad decision to export a production dump of 500 European customer records to my local development machine for deep tracing. I assumed that because I was a trusted engineer and the data was only for debugging, it was safe. I bypassed the data anonymization service because it was too slow. Result: the impact. My laptop was unencrypted at the time. A routine security scan flagged the presence of plaintext PII, personal identifiable information, in a non-production zone. This was a direct GDPR compliance violation. The company had to self-report to the regulator, and I was removed from production access for 30 days while a forensic review was conducted. Reflection: I learned that customer privacy overrides technical urgency. Production data is not a debugging tool. It is a legal liability. If you cannot reproduce a bug without real PII, the problem is your test data generation, not the data itself. PII data belongs to the customer, not the engineer.
The investigation steps and root cause.
As the compliance office opened an investigation, we audited the data flow. 1. Verified the audit log of the database and confirmed a select star export of sensitive tables, names, addresses, tax IDs. 2. Traced the IP address of the export request to my local VPN session. 3. Confirmed that the data sovereignty rules for EU citizens had been violated by moving the data to a server located outside the EU region. 4. The root cause: regulatory ignorance where the technical need for debugging led to an unauthorized transfer of sensitive PII into an insecure, non-compliant environment.
The technical resolution.
We sanitized the environment and implemented strict data gatekeeping. 1. Immediately performed a remote wipe of the data on my laptop and verified the deletion with the security team. 2. Implemented data masking at the database driver level JDBC proxy, so that even if an engineer runs a query, they only see XXXX for PII fields. 3. Developed a synthetic data generator in Java that creates realistic test records based on production distributions without using real customer data. 4. Configured the database to block all bulk exports, more than 10 records, unless a specific compliance token is provided in the session.
What I changed forever.
I implemented these 4 structural guardrails for data compliance. 1. The anonymization-only policy established a hard rule that production data can never be moved to a non-production zone without passing through an automated masking pipeline. 2. DLP data loss prevention enforcement integrated a tool that scans all engineer laptops and Slack channels for PII patterns, automatically alerting the security team on any hits. 3. Mandatory GDPR certification. Required all support engineers to complete an annual certification on data sovereignty and privacy laws before being granted on-call access. 4. Isolated debug enclaves. Created a clean room virtual environment in the same region as production where engineers can debug with masked data without exporting it locally. We have reduced our data sovereignty risks by 100% since adopting anonymization-first debugging.
Summary card.
Key takeaway for your interview. Incident type: regulatory breach and data sovereignty violation. Bad decision: exporting real EU customer PII to a local laptop for debugging to bypass a slow anonymization tool. Impact: direct GDPR violation, mandatory regulatory reporting, and temporary loss of production access. Guardrail implemented: mandatory, anonymization-only policy and automated DLP scanning for all endpoints. Debug with logic, not with lives and identities.
The interview-winning answer template.
Early in my career, I made the bad decision to export a small set of production customer records to my local machine to debug an invoice failure. I bypassed our anonymization tool for speed, resulting in a GDPR compliance violation. I resolved this by purging the data and leading a project to implement JDBC-level data masking. This taught me that regulatory compliance is as critical as system uptime. I have since enforced a synthetic data-first debugging policy and implemented automated DLP scanning, ensuring that our team never exposes sensitive customer PII again.
Follow-up 1. What is the difference between data masking and data encryption?
Answer: encryption is a reversible process, using a key that protects data at rest or in transit. Masking is a non-reversible process, like replacing a name with user_123, used to provide functional data for testing without exposing the real identity. In senior support, we use masking for all dev and staging environments.
Follow-up 2. How do you handle a request from legal or compliance to delete a customer's data, right to be forgotten, in a complex Java system?
Answer: I would use our Data Lifecycle Manager tool. It identifies the customer's ID across all microservices, MySQL, Kafka, Elasticsearch, and triggers a coordinated soft delete or anonymization script. We never do this manually. It must be a scripted, audited process to ensure nothing is missed.
Follow-up 3. Curveball. What if the PII is encrypted in the database, but your Java application decrypts it and then logs it in plain text? Who is at fault?
Answer: the application logic is at fault. This is a classic leakage incident. In a senior role, I prevent this by implementing AOP, aspect-oriented programming, interceptors that automatically scrub PII fields from all logging events before they reach the disk.
Pro tip: the anonymization rule.
In a senior Java support role, remember, if you need production data to find a bug, your test suite is the real bug. Invest in high-quality synthetic data generation, and you will never have to worry about a GDPR fine again.
Explain a bad decision you made. Question 64. The token leak.
Interviewer asks, explain a mistake involving missing data masking or encryption in logs. Incident type: sensitive data exposure and audit log insecurity. Interviewer insight: this question targets your security hygiene. Logging a JWT token or a session ID in plain text is a level 1 security failure. A senior engineer explains how they moved from string logging to token-aware interceptors to ensure that secrets never leave the JVM memory buffers.
The star story and reflection.
Here is the account of how logging a full header exposed 10,000 active sessions. Situation: we were troubleshooting an intermittent 401 unauthorized error in our Java-based microservices architecture. The security team suspected a token expiration bug. Task: my task was to log the incoming HTTP requests to see why the authentication filter was rejecting certain valid-looking tokens. Action: the bad decision plus why it happened. I made the bad decision to use a global logging filter that printed the full HTTP header for every incoming request. I assumed that because our log server was internal, it was safe to see the authorization header in plain text for the duration of the investigation. Result: the impact. For 2 hours, we logged the full bearer tokens, JWT for 10,000 active users into Splunk. A developer with read-only log access could have used those tokens to hijack any customer session. The security team detected the plaintext secrets and forced a global session invalidation, logging out every user in the system to mitigate the risk. Reflection: I learned that logs are a shadow database. If a piece of data is too sensitive to be stored in clear text in a database, it is too sensitive to be stored in clear text in a log. Internal access does not equal security. Audit logs are a high-value target. Treat them with the same security as your database.
The investigation steps and root cause.
As the security team triggered the emergency lockout, we analyzed the exposure. 1. Verified that the authorization header was being printed as a string in the Java HTTP servlet request wrapper logs. 2. Confirmed that the JWT tokens were long-lived, 24 hours, meaning the exposure window was significant. 3. Identified that our standard log masking script only looked for JSON body fields and ignored HTTP headers. 4. The root cause: incomplete masking logic where a debug effort prioritized visibility over security, failing to account for sensitive data in the transport layer headers.
The technical resolution.
We sanitized the logs and hardened the security perimeter. 1. Immediately removed the global logging filter and purged all authorization header entries from the central Splunk index. 2. Implemented a safe headers-only whitelist for the logging filter, ensuring that only non-sensitive headers like user agent are ever recorded. 3. Added a JWT signature verification check in our monitoring tool to alert us if a log line ever contains a string matching the JWT format. 4. Redesigned our Java security filters to log only the token expiry and issuer fields, rather than the raw token string.
What I changed forever.
I implemented these 4 structural guardrails for log security. 1. Mandatory header masking. Updated our global logback configuration to automatically redact any header named authorization, cookie, or XAPI key using a custom appender. 2. The secret scanner bot integrated a tool like TruffleHog that scans our production log streams in real time for patterns matching private keys, tokens, and passwords. 3. Encrypted log store standard. Mandated that all log data must be encrypted at rest with customer-managed keys, CMK, to ensure that even a storage breach is limited. 4. Security-first log triage. Established a policy that debug-level logging of raw network traffic requires a security architect sign-off and a 1-hour auto-disable timer. We have reduced our log-based secret exposure incidents to 0 since implementing the real-time scanner.
Summary card.
Key takeaway for your interview: incident type, sensitive data exposure and audit log insecurity. Bad decision, enabling global header logging to debug 401 errors, which exposed 10,000 active JWT bearer tokens in plain text. Impact: high-risk session hijacking potential and mandatory global logout of all active users to mitigate the breach. Guardrail implemented: automated authorization header redaction and real-time secret scanning on all log streams. Your logs should reveal the action, not the key.
The interview-winning answer template.
During a complex security filter troubleshooting session, I made the bad decision to log full HTTP headers to find a token error. This exposed 10,000 live JWT tokens in our internal logs, requiring an emergency session invalidation for all users. I resolved this by purging the logs and implementing an automated secret scanner for our log streams. This taught me that logs are a primary attack vector. I have since implemented mandatory header redaction and a whitelist-only logging policy for transport data, which has completely eliminated secret exposure in our observability stack.
Follow-up 1. If you log a JWT signature, is that considered a security risk?
Answer: yes, although less severe than the full token. A signature can still be used for token matching or replay patterns. In a senior support role, we only log the JWT metadata, like the subclaim or the JTI, and never the signature or the payload itself.
Follow-up 2. How do you handle masking for logs that are sent to a third-party tool like Datadog or New Relic?
Answer: we use edge masking. The data is scrubbed inside our VPC before it ever leaves our network. We use a dedicated Java log forwarder that applies masking rules locally, so that no sensitive data is ever sent to the third-party cloud.
Follow-up 3 curveball. What if the bug is in the masking logic itself and it is actually leaking data by being too lenient? How do you test your masking?
Answer: we use security regression tests. We have a suite of known secrets, fake but realistically formatted tokens, that we attempt to log during every build. If the output file contains the unmasked secret, the build fails. This ensures our guardrails are always working.
Pro tip, the whitelist rule.
In a senior Java support role, remember, blacklisting sensitive fields is a losing battle. There will always be a new field you forgot. Switch to whitelist logging, where you explicitly define the only fields allowed in the logs. Everything else is masked by default.
Category 13 wrap-up, the security lesson.
We have explored the high-stakes world of security and compliance, from the danger of logging PII to the risks of bypassing authorized access. The lesson is that in a production environment, integrity is just as important as uptime. But our systems do not live in isolation. They are part of a vast ecosystem of external APIs and libraries. This leads us into Category 14, vendor and third-party integration mistakes, where we examine the risks that come from the systems we do not own.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers, like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, and system design. Required for your Java job interviews, like Java Application Support Engineer jobs, AWS Java Developer jobs, Java Backend Developer jobs, Site Reliability Engineer SRE jobs, Java DevOps Engineer jobs, Java Kubernetes Developer jobs, Java Blockchain Developer jobs, Application Security Engineer jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem solving, interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people. Also for your interviews, you people can download all 6 PDFs in a single zip file from below given links.
Category 14, vendor and third-party integration mistakes.
In a modern Java microservices architecture, up to 50% of your code likely comes from external vendors or open-source libraries. This category evaluates your integration maturity. Interviewers want to see that you take full ownership of the system, including the parts you did not write. They are looking for engineers who implement defensive boundaries and never use the excuse it is the vendor's fault during a production outage.
The integration challenge, questions 65 to 69.
Be prepared to discuss these external dependency failures in your next interview. 65. Tell me about a time a vendor hotfix or patch broke your Java application. 66. Describe a situation where you trusted a third-party API response without proper validation. 67. Have you ever misconfigured a vendor integration that caused a widespread outage? 68. Tell me about a time when a third-party service outage was mishandled by your team. 69. Explain a mistake related to dependency version conflicts or untested SDK upgrades. Interviewers evaluate your ability to build defensive boundaries around external systems.
Explain a bad decision you made. Question 65, the untested patch.
Interviewer asks, tell me about a time a vendor hotfix or patch broke your Java application. Incident type, third-party regression and class path conflict. Interviewer insight, this question probes your change management discipline. Bypassing testing for a vendor patch because it is official is a common senior-level trap. They want to see how you move to sandbox validation and staging mirrors to ensure that a vendor's fix does not become your next outage.
The star story and reflection.
Here is the account of how an official security patch crashed our production cluster. Situation: we were using a legacy Java-based database driver that had a known high-severity security vulnerability, CVE. Task: my task was to apply an emergency hotfix jar provided directly by the database vendor to our production application servers. Action: the bad decision plus why it happened. I made the bad decision to apply the patch directly to production after only a 5-minute smoke test in a local dev environment. I assumed that because the patch came from a Tier 1 vendor, it was safe and required no deep regression testing. I wanted to close the security gap before the morning audit. Result: the impact. The hotfix contained a hidden dependency on a newer version of the logging framework. When the Java nodes restarted, they failed to initialize, throwing a no-such-method error across the entire cluster. Our core banking API was offline for 60 minutes, impacting 15,000 users and resulting in a formal security incident filing. Reflection: I learned that a vendor's success is not your stability. Every external artifact is a potential source of class path corruption. If you do not test it in an exact mirror of production, you are effectively letting the vendor perform live surgery on your system. Treat vendor code with the same skepticism as unverified open-source code.
The investigation steps and root cause.
As the JVMs failed to reach a ready state, I performed a forensic audit. 1. Analyzed the Catalina.out logs and identified a java.lang.no such method error in the SLF4J library. 2. Used javapc to inspect the vendor's hotfix jar and found it was compiled against SLF4J version 2.0, while our app was on 1.7. 3. Ran MVN dependency tree in our build environment to see how the vendor jar was interacting with our internal class path. 4. The root cause, binary incompatibility, where the vendor patch introduced a transitive dependency conflict that broke the application's logging initialization.
The technical resolution.
We restored the service and hardened our dependency management. 1. Immediately rolled back the production jar to the previous vulnerable but stable version to restore the banking API. 2. Modified the application's Maven configuration to explicitly exclude the vendor's internal logging library using the exclusions tag. 3. Repackaged the hotfix into our internal artifactory and performed a full 2-hour automated regression test suite in the staging environment. 4. Successfully redeployed the validated version and verified the identity of the driver at startup using the Java manifest version check.
What I changed forever.
I implemented these 4 structural guardrails for vendor patch management. 1. The staging mirror mandate established a rule that no vendor patch can reach production without first running for 24 hours in a staging environment that mirrors the production class path. 2. Transitive dependency audit enforced a policy where every new jar must be audited with the Maven Enforcer plugin to detect version conflicts before the build completes. 3. Vendor response runbook created a standard protocol for reporting regressions back to vendors, including mandatory JVM error logs and thread dumps to speed up their fix cycle. 4. Immutable artifact policy moved all vendor patches into a private, versioned vendor release repository, ensuring we never download artifacts directly to production servers. We have reduced our vendor-related regressions to 0 since adopting staging mirror testing.
Summary card.
Key takeaway for your interview: incident type, third-party regression and class path conflict. Bad decision, applying a vendor hotfix directly to production based on the vendor's reputation without regression testing. Impact: java.lang.no such method error at startup and a 60-minute banking API outage for 15,000 users. Guardrail implemented, mandatory 24-hour staging mirror validation, and automated transitive dependency audits. A vendor fix is just a suggestion until it passes your internal tests.
The interview-winning answer template.
During a critical security update, I made the bad decision to apply a vendor-provided hotfix jar directly to production without deep testing. This caused a no-such method error because the patch had a library conflict that broke our application startup. I resolved this by rolling back and then implementing Maven exclusions to fix the class path. This taught me that vendor artifacts must be treated with the same rigor as our own code. I have since enforced a staging mirror policy and automated dependency audits, which has completely eliminated third-party regression issues in our environment.
Follow-up 1. If the vendor patch is for an active exploit being used right now, do you still wait for 24 hours of staging testing?
Answer: no. In an active attack, we use a high-velocity emergency track. We run a condensed 30-minute automated test suite that covers smoke and core logic. We prioritize mitigation over perfection, but we still never bypass the basic validation of the app startup capability.
Follow-up 2. How do you handle a vendor who refuses to provide a fix for a bug that is impacting your production stability?
Answer: I pivot to defensive isolation. I would build a wrapper in Java that catches the vendor's errors and provides a fallback or retries. If the stability risk is too high, I would lead a technical assessment to find an alternative library or vendor that meets our production standards.
Follow-up 3. Curveball. What if the vendor patch works in staging but fails in production because of a different Java minor version on the servers? How do you find that?
Answer: I would check the hs_error_PID or the application start logs for JVM property differences. This is why I advocate for Dockerization. By packaging the specific JRE with the application artifact, we ensure that the vendor patch sees the exact same runtime environment in both staging and production.
Pro tip: the class path audit.
In a senior Java support role, remember, you do not just deploy a jar, you deploy a class path. Always use MVN dependency. Analyze before adding any vendor library to see what unused or conflicting dependencies are being pulled in. Precision in your build is the key to stability in your runtime.
Explain a bad decision you made. Question 66. The blind trust trap.
Interviewer asks, describe a situation where you trusted a third-party API response without proper validation. Incident type: data integrity failure and unhandled exception. Interviewer insight: this question tests your defensive programming knowledge. An external API is an untrusted source. They want to see how you moved from optimistic parsing to strict schema validation, and how you implemented fail-safe logic to protect your Java application from external data corruption.
The star story and reflection.
Here is the account of how a single unexpected field in an API response crashed our price engine. Situation: we integrated a third-party shipping rate API into our Java e-commerce platform. The vendor's documentation stated the rate field would always be a numeric decimal. Task: my task was to parse the JSON response and update the customer's cart total before they reached the payment screen. Action: the bad decision plus why it happened. I made the bad decision to use a simple Jackson mapper that deserialized the rate field directly into a double variable. I skipped adding a null check or a type validation block because I trusted the vendor's API documentation implicitly. I believed that external meant reliable. Result: the impact. The vendor performed an unannounced update and began sending the string service underscore unavailable in the numeric rate field during their maintenance window. Our Java application threw a JSON mapping exception and crashed the entire checkout thread. We lost 1,500 orders over 2 hours, resulting in a $90,000 revenue loss. Reflection: I learned that documentation is a promise, but the actual API response is the reality. If you do not validate every field coming from an external source, you are giving a third-party permission to crash your code. Never map external data directly to your internal business models.
The investigation steps and root cause.
As the checkout threads began timing out, we performed a data audit. 1. Analyzed the application logs and identified a com.fastrxml.jackson.databind.x.invalid format exception on the cart calculation class. 2. Used TCP dump to capture the raw HTTP response from the vendor and saw rate, service underscore unavailable instead of a numeric value. 3. Confirmed that our Java application had zero error handling for non-numeric types in that specific JSON path. 4. The root cause: optimistic deserialization, where an external response was trusted to match its schema perfectly, leading to a fatal unhandled exception when the data drifted.
The technical resolution.
We stabilized the parsing logic and implemented a fallback strategy. 1. Immediately deployed a hotfix to wrap the JSON parsing in a try-catch block that defaults the shipping rate to a safe flat fee if the API returns garbage. 2. Refactored the Java DTO data transfer object to use a string for the raw rate and implemented a custom validator that performs safe numeric conversion. 3. Integrated Resilience 4J to provide a fallback value and a circuit breaker, ensuring the cart still works even if the shipping API is sending invalid data. 4. Added a strict validation layer using Hibernate Validator to reject any API response that does not match our internal business constraints.
What I changed forever.
I implemented these 4 structural guardrails for external data handling. 1. The Untrusted Source Standard mandated that all external API responses must be parsed into a dedicated bridge DTO before being converted to internal domain objects. 2. Mandatory bean validation established a rule that every external JSON field must have a @not_null or @min/@max annotation to catch data corruption at the moment of entry. 3. Contract testing policy initiated a monthly contract verify job that pings vendor APIs and compares the actual response against our expected Java schema. 4. Graceful degradation design required all new features involving third-party data to include a documented offline fallback that allows the app to function without that data. We have reduced our integration-related crashes to 0 since adopting defensive parsing.
Summary card.
Key takeaway for your interview: incident type, data integrity failure and unhandled exception. Bad decision, mapping a third-party API response directly to a numeric Java primitive without validation or null checks. Impact, fatal JSON mapping exception during a vendor maintenance window, resulting in 1,500 lost orders and $90,000 revenue loss. Guardrail implemented, mandatory bridge DTO architecture, and Hibernate bean validation for all external data streams. Data from the internet is poison until your validators say otherwise.
The interview-winning answer template.
During a shipping integration, I made the bad decision to trust a vendor's API documentation and map their numeric fields directly to Java doubles without validation. When the vendor sent a string error message instead of a number, our app crashed, costing us $90,000 in lost orders. I resolved this by implementing defensive parsing and circuit breakers. This taught me that external data is never guaranteed. I have since enforced a bridge DTO standard and mandatory bean validation, which has completely protected our system from third-party data drift.
Follow-up 1. If the external API is slow, 30-second response, but the data is correct, does your validation layer help?
Answer: validation only helps with data quality. For data speed, I use timeouts and bulkheads. In a senior support role, I ensure that an external call never hangs a thread for more than 2 seconds, regardless of the data being returned. Availability is the first line of defense.
Follow-up 2. What is the benefit of using optional T for third-party API fields in your Java code?
Answer: it forces the developer to acknowledge that the data might be missing. By using optional, the code will not compile or pass review unless there is an explicit or else parentheses or is present parentheses check, which prevents null pointer exceptions at the source.
Follow-up 3. Curveball. What if the API sends valid JSON, but the values are logically impossible, for example, a shipping rate of -$500? How do you catch that?
Answer: this is where business logic validation comes in. I use the @min0 annotation in Java and add a secondary sanity interceptor that flags any outliers. If the data is logically impossible, we reject it and trigger a vendor data quality alert immediately.
Pro tip: the untrusted boundary.
In a senior Java support role, treat your application like a secure vault. Every external API call is a delivery through a small window. You must inspect every package, verify every signature, and have a plan for what to do if the package is empty. Trust is earned through uptime, but security is built through validation.
Explain a bad decision you made. Question 67. The sandbox leak.
Interviewer asks, have you ever misconfigured a vendor integration that caused a widespread outage? Incident type: configuration drift and integration misalignment. Interviewer insight. This question evaluates your operational rigor. They want to see how you manage secrets and endpoints across environments. A senior engineer explains how they moved from manual config updates to environment-aware injection to ensure production never points to a testing sandbox.
The star story and reflection.
Here is the account of how a test URL took down our production notifications. Situation: we were migrating our Java-based alerting service to a new third-party SMS provider. The integration required an API key and a specific regional endpoint URL. Task: my task was to update the production application product properties file with the live vendor credentials and perform a rolling restart of the cluster. Action: the bad decision plus why it happened. I made the bad decision to copy the configuration block directly from the developer wiki. I assumed the wiki was up to date. I failed to notice that the URL was still pointing to the vendor's sandbox environment, which had a strict limit of 10 messages per hour. I skipped the config diff check against the previous release because I was under pressure to finish the migration before 6 a.m. Result: the impact. Once traffic hit 8 a.m., we reached the sandbox limit in 3 seconds. 100% of customer MFA, multi-factor authentication, codes began failing. Users were locked out of their accounts globally for 2 hours. We lost an estimated $120,000 in customer activity and received 500+ support tickets within the first hour. Reflection: I learned that manual copying is the root of all configuration drift. In a senior support role, you cannot trust a wiki or a developer's notes. You must only trust a verified release manifest or a secure secret manager. A sandbox in production is an invisible source of failure.
The investigation steps and root cause.
As the MF alerts began firing, we audited the external traffic. 1. Checked the Java logs and found HTTP 429 too many requests errors from the SMS vendor. 2. Ran a curl V from the production host to the configured URL and saw it was hitting api.sandbox.vendor.com instead of api.production.vendor.com. 3. Identified that the API key I used was for the production account, but the endpoint was for testing, causing an account-level lock on the vendor's side. 4. The root cause: manual configuration mismatch where a testing URL was inadvertently promoted to production due to a lack of automated environment validation logic.
The technical resolution.
We restored the notification flow and hardened the config layer. 1. Immediately updated the production properties to use the correct production URL and performed an emergency rolling restart. 2. Collaborated with the vendor to lift the temporary account lock caused by the sandbox or production key mismatch. 3. Added a startup health check in the Java code that pings the configured SMS endpoint and verifies the environment header in the response. 4. Implemented an emergency fallback in the notification service that switches to email alerts if the SMS gateway becomes unreachable.
What I changed forever.
I implemented these 4 structural guardrails to prevent configuration-driven outages. 1. Secret manager integration. Mandated that all vendor URLs and keys must be stored in AWS Secrets Manager or Vault, removing the need for manual properties files. 2. Mandatory config validation. Added a CI/CD linter that scans all property files for the word sandbox or test and fails the build if they are found in the prod profile. 3. Automated endpoint audits. Integrated a connectivity test job in the release pipeline that pings all external dependencies from the production VPC before traffic is cut over. 4. Least privilege API keys. Enforced a rule where each environment has a unique, scoped API key that cannot function if used with the wrong endpoint. We have reduced our configuration drift incidents by 100% since adopting secret management.
Summary card.
Key takeaway for your interview: incident type, configuration drift and integration misalignment. Bad decision, copying vendor configuration from a wiki without verifying the environment-specific endpoint URL. Impact: 2-hour global MFA lockout and $120,000 revenue loss due to hitting a sandbox rate limit. Guardrail implemented: mandatory secret manager injection and CI/CD config linting to block test URLs in production. Config is code. Treat it with the same respect and validation logic.
The interview-winning answer template.
During a provider migration, I made the bad decision to copy our SMS gateway configuration from a developer wiki, which resulted in production pointing to a sandbox endpoint. This caused a 2-hour global MFA outage because we hit the sandbox rate limit instantly. I resolved this by correcting the URL and implementing automated secret management. This taught me that manual configuration is an operational failure. I have since implemented environment-aware secret injection and automated CI/CD checks that block any test-related URLs from reaching our production profile.
Follow-up 1. If you point production to a test endpoint, is that also a security risk, or just an availability risk?
Answer: it is both. Sending live production data to a test endpoint is a major security risk because testing environments often have lower encryption standards and looser access controls. It could lead to a data leak of customer info into a less secure zone.
Follow-up 2. How do you manage vendor secret rotation without causing downtime in your Java applications?
Answer: I use dynamic bean refresh. Our Java app listens for updates from the secret manager. When a key is rotated, the app reloads the configuration bean in memory without a restart. We also use dual key rotation, where the old and new keys both work for a 24-hour overlap period.
Follow-up 3. Curveball. What if the vendor changes their API endpoint without notifying you? How does your monitoring catch that?
Answer: I use egress monitoring and external heartbeats. We have an alert for any increase in 404 or 503 errors from specific vendor domains. We also use a synthetic monitor that attempts a real, low-value transaction through the vendor API every 5 minutes to ensure the pipe is still open and valid.
Pro tip: the endpoint rule.
In a senior Java support role, remember, hard-coded URLs are technical debt. Always externalize your endpoints and always validate them at startup. If your application cannot prove its dependencies are healthy during bootup, it should not be allowed to accept traffic.
Explain a bad decision you made. Question 68. The retry storm.
Interviewer asks, tell me about a time when a third-party service outage was mishandled by your team. Incident type: cascading failure and aggressive retry logic. Interviewer insight: this question probes your incident discipline. During a vendor outage, the worst thing you can do is hit them harder. They want to see that you understand the thundering herd problem and how you implemented exponential backoff and circuit breakers to protect your own system from a failing neighbor.
The star story and reflection.
Here is the account of how we accidentally crashed our own servers during a vendor outage. Situation: we were integrated with a third-party email API for sending order confirmations. The vendor experienced a total regional blackout that lasted for 3 hours. Task: my task was to ensure that customer emails were not lost and that the checkout system remained functional while the vendor was down. Action: the bad decision plus why it happened. I made the bad decision to increase the Java application's max retries from 3 to 10 with a fixed delay of 0. I wanted to force the emails through as soon as the vendor came back up. I assumed our Java thread pool was large enough to handle the wait times. Result: the impact. Every checkout request now stayed in the thread pool for up to 5 minutes while it retried the failing email API 10 times in a tight loop. Within 15 minutes, 100% of our worker threads were in timed _waiting state. The entire checkout site crashed, not because of the vendor, but because our own threads were exhausted. We lost $200,000 in revenue because our homepage would not even load. Reflection: I learned that optimistic retries are just a self-inflicted denial of service attack. If a neighbor is down, you must stop and back off. You cannot solve an external outage by hitting the vendor harder. You only end up breaking yourself. Never prioritize an optional feature like email over a core feature like checkout.
The investigation steps and root cause.
As the site became unresponsive, we performed a thread and network audit. 1. Captured a JStack thread dump and identified 500 threads in timed _waiting state inside the custom retry class. 2. Ran netstatin and saw thousands of outbound connections to the vendor's IP and SYN_sent state. 3. Observed that for every one failed email attempt, our code was generating 5 additional network requests in less than 1 second. 4. The root cause: self-inflicted denial of service, where aggressive, fixed-interval retries turned a vendor outage into a local thread starvation event.
The technical resolution.
We stabilized the cluster and moved to a resilient retry architecture. 1. Immediately applied a runtime configuration change to set the max retries to 0, which instantly unblocked the worker threads. 2. Implemented the Resilience 4J retry module using an exponential backoff strategy to spread out the reconnection attempts. 3. Added jitter to the retry intervals to ensure that all 20 nodes did not attempt to reconnect at the exact same millisecond. 4. Integrated a bulkhead pattern to isolate the email-sending threads from the core checkout thread pool.
What I changed forever.
I implemented these 4 structural guardrails for external dependency handling. 1. Mandatory exponential backoff. Established a coding standard that prohibits fixed retries. All external calls must use backoff with jitter. 2. Circuit breaker integration. Enforced a rule that every third-party API must be protected by a circuit breaker that trips after 5 consecutive failures. 3. Thread pool isolation. Mandated the use of separate executor services for each external vendor to prevent a single provider from starving the entire JVM. 4. Outage mode testing. Integrated chaos engineering tests using AWS fault injection to simulate vendor outages during the development phase. We have reduced our cascading failure incidents to 0 since adopting these resilience patterns.
Summary card.
Key takeaway for your interview. Incident type, cascading failure and aggressive retry logic. Bad decision, implementing a fixed 5-attempt retry logic with 0 delay, creating a retry storm. Impact, total system blackout for 3 hours and $200,000 revenue loss due to self-inflicted thread starvation. Guardrail implemented, mandatory exponential backoff with jitter and resilience 4J circuit breakers. Retries without backoff are just a faster way to crash your own system.
The interview-winning answer template.
During a vendor outage, I made the bad decision to use an aggressive fixed retry logic to minimize email delays. This backfired by creating a retry storm that exhausted our Java thread pools and crashed the entire checkout site for 3 hours, costing $200,000. I resolved this by disabling the retries and implementing Resilience 4J with exponential backoff. This taught me that resilience is about protecting the local system first. I have since enforced the use of circuit breakers and thread pool isolation for all external integrations, ensuring that a vendor failure can never again cause a cascading blackout in our environment.
Follow-up 1. What is jitter and why is it essential when 100 microservices are all retrying at once?
Answer: jitter adds a random delay to each retry interval. Without it, all 100 instances would hit the vendor API at the exact same time, the thundering herd effect, likely crashing the vendor again or saturating our own network egress. Jitter ensures the load is distributed evenly over time.
Follow-up 2. How do you choose between a retry and a circuit breaker during a production outage?
Answer: a retry is for transient glitches, like a single packet loss. A circuit breaker is for systemic failures, like a vendor being down for 10 minutes. In senior support, we use both. The retry handles the minor blips, while the circuit breaker trips to save the system when the blips become a constant stream of errors.
Follow-up 3. Curveball. What if you implement a circuit breaker but the fallback logic also fails? How do you defend against that?
Answer: this is why we use static fallbacks. A fallback should never make a network call or a DB query. It should return a hard-coded default, a cached value from memory, or a simple error message. A fallback that can fail is not a safety net. It is just another point of failure.
Pro tip: the backoff law.
In a senior Java support role, remember, never hit a broken system as hard as you hit a working one. If a dependency fails, your application must automatically slow down its request rate. Exponential backoff is the primary language of architectural respect and resilience.
Explain a bad decision you made. Question 69. The class path conflict.
Interviewer asks, explain a mistake related to dependency version conflicts or untested SDK upgrades. Incident type, dependency conflict and jar hell. Interviewer insight, this question evaluates your build integrity knowledge. In Java, transitive dependencies are a major source of production instability. They want to see how you troubleshoot no such method error, and how you implemented dependency locking to ensure your build is identical across all environments.
The star story and reflection.
Here is the account of how a minor version bump broke our transaction logging. Situation: we were upgrading our cloud storage SDK in a complex Java monolith to enable a new security encryption feature. Task: my task was to update the Maven POM file, verify the build locally, and deploy the change to production. Action: the bad decision plus why it happened. I made the bad decision to approve the deployment after only verifying that the application started in staging. I assumed that because the build was successful, Maven had resolved all conflicts correctly. I skipped the full regression test of our logging module because it was unrelated to the storage SDK. Result: the impact. In production, the logging module began throwing java.lang.no such method error every time a customer placed an order. The new SDK had pulled in an incompatible version of Jackson that replaced our stable library. We lost 4 hours of transaction logs, causing an audit failure and delaying our fraud detection system. Reflection: I learned that in Java, a successful build is not the same as runtime compatibility. If you do not audit your dependency tree, you are letting Maven decide your application's stability. Transitive dependencies are the silent neighbors that can burn down your house.
The investigation steps and root cause.
As orders began failing their fraud checks, we audited the class path. 1. Analyze the stack trace and identify java.lang.no such method error in the com.fastrxml.jackson.databind package. 2. Ran mvn dependency tree and found that the new Cloud SDK had a transitive dependency on Jackson 2.15, while our logging engine required 2.11. 3. Confirmed that Maven's nearest win strategy had picked the incompatible version, because the Cloud SDK was defined earlier in the POM file. 4. The root cause, transitive dependency conflict, where a minor SDK upgrade introduced a breaking library version that was not compatible with the existing application modules.
The technical resolution.
We restored the class path integrity and hardened the build process. 1. Immediately rolled back the application to the previous stable version to restore the fraud detection logs. 2. Modified the POM file to use an exclusion tag for the Jackson library within the Cloud SDK dependency. 3. Explicitly defined the correct Jackson version in the dependency management section of the parent POM to lock it for all modules. 4. Implemented the Maven Enforcer plugin to fail any future builds that contain conflicting transitive dependency versions.
What I changed forever.
I implemented these 4 structural guardrails for dependency safety. 1. The dependency convergence rule integrated the Maven Enforcer plugin to strictly prohibit conflicting library versions in any production build. 2. Mandatory dependency diff reports established a rule that every SDK upgrade PR must include a before and after text file of the full dependency tree. 3. Runtime class path audits developed a startup utility that logs the location and version of all critical jar files, like JSON parsers or DB drivers, to help identify drift. 4. Shadowing strategy mandated the use of the Maven Shade plugin for any new third-party integrations that require high-risk shared libraries to isolate their class path. We have reduced our no such method error incidents to 0 since implementing dependency locking.
Summary card.
Key takeaway for your interview: incident type, dependency conflict and jar hell. Bad decision, approving an SDK upgrade based on a successful build without auditing the transitive dependency tree. Impact, no such method error outage for 4 hours, causing total loss of transaction logs and a fraud detection delay. Guardrail implemented, Maven Enforcer plugin for dependency convergence and explicit version pinning in dependency management. A build is successful only when every library in the tree is in agreement.
The interview-winning answer template.
During a Cloud SDK upgrade, I made the bad decision to trust Maven's default conflict resolution without auditing our dependency tree. This introduced an incompatible JSON library that caused a no such method error, breaking our transaction logs for 4 hours. I resolved this by excluding the transitive dependency and locking our internal versions. This taught me that runtime compatibility is my responsibility. I have since implemented the Maven Enforcer plugin to ensure dependency convergence and mandatory dependency audits for every production release.
Follow-up 1. What is transitive dependency, and why is it so dangerous for production systems?
Answer: a transitive dependency is a library that your libraries need to run. It is dangerous because you do not declare it directly in your POM file, so it can change or conflict with your other libraries silently during a build. If you do not lock these versions, your production environment becomes unpredictable.
Follow-up 2. How do you use the Maven Enforcer plugin to prevent these conflicts?
Answer: I configure the dependency convergence rule in the plugin. If Maven finds two different versions of the same library in the dependency tree, it will throw a build error and list the conflicting paths. This forces the engineer to resolve the conflict before the code can be deployed.
Follow-up 3. Curveball. What if you find a vulnerability in a transitive dependency, but there is no update available? How do you handle that?
Answer: I would look at vulnerability mitigation. Can we disable the specific feature that uses that library? If not, I would use the exclusion tag to remove the library and manually add a compatible, patched version of that library to our direct dependencies. As a last resort, I would build a security wrapper to sanitize inputs to that specific module.
Pro tip: the classpath law.
In senior support, remember, Maven is an optimist, but the class loader is a judge. Never assume two libraries will play nice together just because the code compiled. Always audit your dependency tree as if you were looking for a security hole, because often you are.
Category 14 wrap-up. The integration lesson.
You have analyzed the complex risks of third-party integrations, from the dangers of aggressive retries to the jar hell of transitive dependencies. The lesson is that you must treat external code with the same rigor as your own. But even with perfect code and dependencies, a production system is only as stable as the humans who manage it. This brings us to Category 15, on-call handoff and escalation mistakes, where the failure is not in the software, but in the teamwork.
Category 15. On-call handoff and escalation mistakes.
In a 24/7 global support environment, the handoff is a critical point of failure. If the engineer starting their shift at 8 a.m. does not fully understand the context of the incident that started at 4 a.m., the system's recovery is at risk. This category evaluates your team collaboration and on-call maturity. Interviewers want to see how you developed standardized handoff protocols to ensure that technical context is never lost between shift changes.
The collaboration challenge. Questions 70 to 74.
Be prepared to discuss these team-based operational failures in your next interview. 70. Tell me about a time your on-call handoff caused confusion or delayed resolution. 71. Describe a situation where you left incomplete notes in the incident ticket or runbook. 72. Have you ever failed to escalate to the right subject matter expert at the right time? 73. Tell me about a time when poor documentation during a shift change prolonged an outage. 74. Explain a mistake where you stayed on an incident too long instead of handing off properly. Interviewers evaluate your ability to work as part of a seamless, high-reliability team.
Explain a bad decision you made. Question 70. The broken handoff.
Interviewer asks, tell me about a time your on-call handoff caused confusion or delayed resolution. Incident type: communication breakdown and handoff failure. Interviewer insight: this question probes your operational continuity. They want to see if you understand that an incident does not end just because your shift does. A senior engineer explains how they moved from casual chat handoffs to structured status reporting to ensure the next engineer is fully armed with the facts.
The star story and reflection.
Here is the account of how a quick 2-minute handoff led to a secondary outage. Situation: I was finishing a 12-hour night shift where I had been troubleshooting a database connection leak in our Java payment service. Task: my task was to hand over the current system state to the morning shift engineer and ensure they knew the leak was only mitigated but not fixed. Action: the bad decision plus why it happened. I made the bad decision to perform a verbal-only handoff as I was rushing to catch my train. I told the incoming engineer, I restarted the nodes. It is looking good now. I assumed he would check the Grafana trends himself and did not mention that I had only identified the symptom, not the root cause class. Result: the impact: 2 hours later, during the 10 a.m. traffic peak, the connection pool exhausted again. Because the new engineer thought the issue was fixed, he spent 90 minutes looking for new bugs in a recent deployment instead of plugging the known leak. Checkout was down for 90 minutes, resulting in a $150,000 revenue loss. Reflection: I learned that handoff is a technical contract. If you do not document the unfinished business and the assumptions of your shift, you are essentially sabotaging your teammate. Silence during a handoff is an invitation for the incident to return.
The investigation steps and root cause.
After the second outage, we analyzed why the context was lost. 1. Reviewed the Slack history and found my message, nodes restarted, health is green. 2. Identified that I had failed to mention the Hikari CP active connections metric was still steadily climbing after the restart. 3. Found that the incoming engineer had zero visibility into the heap dump I had captured but had not yet analyzed. 4. The root cause, contextual gap where a successful mitigation, restart, was communicated as a final resolution, leading the next engineer to ignore the underlying leak.
The technical resolution.
We solved the technical leak and standardized our team communication. 1. Analyzed the previously captured heap dump and identified a prepared statement leak in the currency conversion module. 2. Refactored the Java code to ensure all database connections were managed by Spring's Transaction Manager rather than manual JDBC calls. 3. Implemented a handoff dashboard in Grafana that highlights metrics that are currently trending toward a threshold. 4. Created a mandatory shift change checklist that requires engineers to document current status, last action, and open risks.
What I changed forever.
I implemented these 4 structural guardrails for on-call handoffs. 1. The T handoff template established a rule that all handoffs must include the problem, the treatment, what was done, and the threat, what could happen next. 2. Mandatory Slack summary enforced a policy that every shift change must be marked by a threaded summary in the incident channel, pinned for visibility. 3. Synchronous validation mandated a 15-minute overlapping window where the outgoing and incoming engineers must look at the dashboards together before the handoff is complete. 4. RCA completion rule established that an incident is never closed by a shift change. It stays in active investigation status until a root cause is verified in code. We reduced our mean time to resolution for multi-shift incidents by 40%.
Summary card.
Key takeaway for your interview: incident type, communication breakdown and handoff failure. Bad decision, performing a verbal-only handoff during a connection leak incident without documenting the open risks. Impact, secondary 90-minute outage during peak hours and a $150,000 revenue loss. Guardrail implemented, mandatory T handoff templates, and a 15-minute synchronous dashboard review. Never assume your teammate knows what you did not write down.
The interview-winning answer template.
During a database connection leak incident, I made the bad decision to provide a brief, verbal handoff to the next shift because I was in a rush. I told them the system was healthy because I had just restarted the nodes, but I failed to mention that the underlying leak was still active. This caused a second outage 2 hours later. I resolved this by leading the fix and then implementing a structured T handoff protocol. This taught me that technical context is the most fragile part of an incident. I have since enforced mandatory written summaries and overlapping shift reviews, which has completely eliminated handoff confusion in our team.
Follow-up 1. If an incident is extremely complex, how do you keep the handoff concise so the new engineer is not overwhelmed?
Answer: I focus on the next action. While the history is important, the incoming engineer needs to know, what is the very next thing I need to watch or do? I provide a summary of the facts but highlight the active hypothesis to give them a clear direction.
Follow-up 2. What is the most important metric to show an incoming engineer during a handoff for a Java application?
Answer: the thread state and heap trend. These tell the true story of JVM health better than CPU or latency. If the after GC heap is rising or if blocked threads are accumulating, the incident is still in progress, regardless of what the user experience looks like currently.
Follow-up 3. Curveball. What if the incoming engineer is a junior and you are handing off a critical P1? Do you stay or leave?
Answer: I stay. In a P1 situation, shift hours are secondary to system restoration. I would act as a mentor and co-pilot until the incident is stabilized or until a more senior SME can join to support the junior engineer. Senior support is about accountability, not just the clock.
Pro tip, the TTT rule.
In a senior Java support role, remember, talk is cheap, logs are expensive, but handoffs are critical. Use the problem treatment threat model. If you do not define the threat for the next shift, you have not finished your job.
Explain a bad decision you made. Question 71, the empty ticket.
Interviewer asks, describe a situation where you left incomplete notes in the incident ticket or runbook. Incident type, documentation deficit and operational amnesia. Interviewer insight, this question evaluates your long-term operational thinking. A support engineer who does not document the why is creating technical debt. They want to see how you realize the cost of poor notes and how you move to evidence-first documentation to make the team smarter.
The star story and reflection.
Here is the account of how lazy notes led to 48 hours of wasted investigation. Situation: we were managing a Java cluster that processed real-time trade data via Kafka. I had identified a specific consumer group rebalance issue that was causing consumer lag. Task: my task was to document the fix, which involved a specific change to the max.poll.records property in the incident ticket and the team runbook. Action: the bad decision plus why it happened. I made the bad decision to leave a one-sentence note, fixed Kafka lag, by updating consumer properties. I assumed the rest of the team would understand which properties I changed. I was exhausted after a 10-hour day and did not want to copy-paste the technical justification or the before and after metrics. Result: the impact. 3 months later, the lag returned during a market surge. The new team spent 48 hours investigating network latency and Java garbage collection because my note did not provide the path to the previous solution. We missed our data delivery SLA for 2 days, resulting in a formal audit. Reflection: I learned that documentation is not for now. It is a message to your future self and your future team. If you do not include the evidence, the specific property and its value, your note is just a distraction. An incomplete note is a technical debt that accrues interest in downtime.
The investigation steps and root cause.
As the team struggled to find the fix, we performed a documentation audit. 1. Searched the Jira history and found my previous ticket with 0 attachments or configuration snippets. 2. Compared the current application properties with the Git history and finally identified the change I had made 3 months prior. 3. Confirmed that the Kafka lag runbook had not been updated with the max.poll.records optimization path. 4. The root cause, documentation deficit, where the lack of what and why in the incident notes forced a full diagnostic restart for an already solved problem.
The technical resolution.
We restored the consumer throughput and modernized our documentation standard. 1. Reapplied the max.poll.records equals 50 setting to reduce the processing time per poll and stabilize the consumer group. 2. Updated the Kafka consumer lag runbook with a symptoms to solution matrix that includes specific configuration tuning steps. 3. Integrated Grafana annotations so that every time a config change is made, a marker appears on the dashboard with a link to the ticket. 4. Developed a Java config reporter that logs the active value of all Kafka properties at startup, making them searchable in Splunk.
What I changed forever.
I implemented these 4 structural guardrails for technical documentation. 1. The snippet-first rule established a policy that no configuration-related ticket can be closed without a diff or a code snippet of the change. 2. Mandatory evidence uploads enforced a rule that every incident ticket must have at least 1 screenshot of the trigger metric and 1 log fragment of the error. 3. Definition of done support. Updated our ticket definition of done to include a mandatory checkbox, runbook updated, link included. 4. Peer documentation review. Initiated a weekly RCA review where we audit the quality of the notes in the week's highest severity tickets to ensure clarity. We have had 0 repeated diagnosis events since implementing the snippet-first rule.
Summary card.
Key takeaway for your interview. Incident type, documentation deficit and operational amnesia. Bad decision, leaving a vague, 1-sentence note in a Kafka incident ticket instead of documenting the specific property change. Impact, 48 hours of wasted investigation time 3 months later and a 2-day SLA breach. Guardrail implemented, snippet first ticket policy, and mandatory runbook update checkbox for closure. Document for the person who does not know what you know.
The interview-winning answer template.
During a Kafka lag incident, I made the bad decision to leave very brief notes in the ticket, assuming the team would remember the fix. This backfired months later when the issue returned, and the team wasted 2 days re-diagnosing it from scratch. I resolved this by updating our runbooks and implementing a snippet-first policy for all tickets. This taught me that incomplete documentation is an operational risk. I now ensure that every resolution note includes the specific code change and the metrics that proved it worked, which has significantly improved our team's collective memory.
Follow-up 1. How do you balance the need for detailed notes with the need to close tickets fast to maintain your KPIs?
Answer: I view notes as an investment in our future KPI. A ticket closed fast with poor notes today will result in a ticket that takes 48 hours to close tomorrow. In senior support, the quality of resolution is always more important than the speed of closure.
Follow-up 2. What tools do you use to make incident documentation more automated and less manual?
Answer: we use Grafana annotations and Slack to Jira integrations. If we find a fix, we can push the Slack thread directly to the Jira ticket. We also use templates in our wiki that auto-populate with the latest infrastructure metadata to save time.
Follow-up 3. Curveball. What if you find a runbook that is stale and actually wrong? What do you do?
Answer: I immediately flag it as deprecated or stale to prevent someone else from using it. I then look at the last modified date and the ticket history to find the most recent correct version and update the runbook. A wrong runbook is more dangerous than no runbook at all.
Pro tip: the future you rule.
In a senior Java support role, always write your notes for future you at 3 a.m. If you do not think your future self can solve the problem using only your current notes, you aren't done documenting. Be clear, be specific, and always include the why.
Explain a bad decision you made. Question 72. The misdirected SME.
Interviewer asks, have you ever failed to escalate to the right subject matter expert SME at the right time? Incident type: triage error and SME misidentification. Interviewer insight: this question evaluates your systemic diagnostics. During an outage, the clock is ticking, and calling the wrong team is a waste of precious time. A senior engineer explains how they moved from blame-based escalation to evidence-based paging to ensure the right eyes are on the problem from the start.
The star story and reflection.
Here is the account of how chasing the wrong team extended a payment outage by 2 hours. Situation: our Java-based merchant gateway was experiencing a sudden spike in 504 gateway timeout errors, impacting 30% of checkout attempts. Task: my task was to identify the bottleneck and escalate to the appropriate team to restore the transaction flow. Action: the bad decision plus why it happened. I saw timeout in the logs and immediately assumed the database was the bottleneck because we had a heavy migration running. I made the bad decision to page the DBA lead and keep them on the bridge for 90 minutes. I was so focused on the database theory that I did not perform a TCP-level trace or check the VPC flow logs. Result: the impact. The database was 100% healthy. The real issue was a BGP route leak at our network edge. Because I paged the wrong team, we wasted 2 hours while the network team sat idle, unaware of the crisis. We lost an estimated $180,000 in transaction revenue during that window. Reflection: I learned that an error code like timeout is a symptom, not a destination. If you escalate based on assumption rather than metric proof, you are just spreading the confusion. Evidence-based triage is the only way to respect an SME's time.
The investigation steps and root cause.
Once the DBA proved the DB was idle, we looked at the wire to find the truth. 1. Ran JStack on the Java nodes and saw threads were in socket read state waiting for the external load balancer. 2. Used traceroute from the production host and found that packets were being routed through an unexpected ISP in a different region. 3. Correlated the latency with a BGP update log from our core routers that happened exactly when the 504 seconds started. 4. The root cause: network path instability, where an external BGP route leak caused traffic to take a suboptimal path, exceeding the Java application's 5-second socket timeout.
The technical resolution.
We bypassed the network bottleneck and restored the transaction flow. 1. Immediately escalated to the network SME and the ISP to blackhole the invalid BGP route and force traffic back to the primary backbone. 2. Increase the Java connection timeout and read timeout temporarily to 10 seconds to allow slow packets to complete while the network stabilized. 3. Implemented Hystrix command execution isolation to ensure that slow network paths in the gateway did not crash the entire JVM thread pool. 4. Added a network performance dashboard in Grafana that tracks TCP retransmissions and hop count to detect route leaks instantly.
What I changed forever.
I implemented these 4 structural guardrails to improve escalation accuracy. 1. The evidence-first paging policy established a rule that no SME team, DBA network infrastructure, can be paged without a log snippet or metric proving their layer is at fault. 2. SME expertise matrix created a symptom-to-team matrix that helps junior engineers identify the right team based on specific Java exceptions, for example, socket timeout versus lock acquisition. 3. Cross-layer monitoring, integrated network RTT round-trip time, metrics directly into the application dashboard to provide outside-in visibility for Java developers. 4. Mandatory triage checklists, enforced a 5-minute isolation checklist, ping, traceroute, top, DF, that must be completed before any high-severity escalation occurs. We reduced our wrong team escalation rate by 70% since adopting the evidence-first policy.
Summary card.
Key takeaway for your interview: incident type, triage error and SME misidentification. Bad decision, assuming a timeout was a database issue and paging the DBA team without performing a network trace. Impact: 2-hour delayed resolution and $180,000 revenue loss while the real root cause, network leak, went unaddressed. Guardrail implemented. Mandatory, evidence-first paging policy and application-integrated network monitoring. Triage the pipe before you blame the source.
The interview-winning answer template.
During a major payment outage, I made the bad decision to escalate to the database team based on an assumption that their migration was causing our timeouts. I kept the wrong team on the bridge for 90 minutes, only to find the root cause was a network BGP leak. This taught me that escalation must be driven by metric proof, not intuition. I have since implemented an evidence-first paging policy and cross-layer monitoring, which ensures we involve the correct SME team within minutes. This has significantly reduced our MTTR and improved cross-team respect during incidents.
Follow-up 1. How do you handle a situation where multiple teams are pointing fingers at each other during an incident?
Answer: I take the role of objective arbitrator. I look at the boundary metrics. For example, if the app logs show a 10-second wait for the DB, but the DB logs show 0.1 second query times, I prove that the delay is in the network between them. Data stops the finger pointing and refocuses the team on the bridge.
Follow-up 2. What is the most effective way to communicate with an SME when you page them at 3 a.m.?
Answer: I provide a 30-second briefing. I tell them 1. What the business impact is. 2. What I have ruled out. 3. The specific evidence, log or metric that points to their system. This allows them to start working immediately without having to re-triage the entire incident.
Follow-up 3. Curveball. What if you page the right team, but they say everything looks fine on our side and the issue is still happening? What's your next move?
Answer: I ask for CO observation. I invite them to look at the application logs with me. Often, a team sees their system as healthy because their alerts did not fire, but the application is seeing an edge case, like a malformed header, that only appears in the interaction between the 2 layers.
Pro tip: the proof of fault rule.
In senior support, never say I think the network is down. Say I see a 20% packet loss on port 443 between app node A and DB node B. Technical precision in your escalation will get you the right experts faster. Stop assuming, start measuring.
Explain a bad decision you made. Question 73. The shift change gap.
Interviewer asks, tell me about a time when poor documentation during a shift change prolonged an outage. Incident type: documentation deficit and shift change fragmentation. Interviewer insight. This question targets your operational continuity. In a 24/7 environment, an incident does not care about your sleep schedule. They want to see that you understand the danger of half-baked handoffs and how you implemented incident state persistence to ensure the recovery never skips a beat.
The star story and reflection.
Here is the account of how a missing detail in a handoff cost the team 3 hours. Situation: we were managing a high-volume Kafka consumer cluster for an insurance firm. A poison pill message had stalled our processing pipeline. Task: my task was to identify the offset of the bad message and hand off the recovery plan to the incoming morning shift engineer. Action: the bad decision plus why it happened. I made the bad decision to leave a general note in the handoff ticket. Kafka lag identified. Need to skip the current offset on the claims topic. I did not specify the consumer group ID or the partition number because I assumed there was only one group active. I was exhausted and rushed the handoff. Result: the impact. The morning engineer reset the offsets for the search index group by mistake, which was healthy. This caused a 3-hour data integrity issue where search results were out of sync. The real poison pill in the claims group remained stuck. The total outage lasted 6 hours instead of 1, resulting in a massive backlog of 500,000 unprocessed claims. Reflection: I learned that general information is dangerous information in a handoff. If you do not provide unique identifiers, IDs, partitions, IPs, you are giving your teammate a map with no street names. Technical handoffs require surgical precision, not just general summaries.
The investigation steps and root cause.
As the morning team reported zero progress, we performed a process audit. 1. Analyzed the Kafka audit logs and found that an offset reset was performed on the wrong consumer group. 2. Compared the handoff ticket with the Kafka dashboard and confirmed the partition 4 was still blocked on a serialization exception. 3. Identified that my handoff note was too vague to be actionable for an engineer who had not been on the A-Tower bridge call. 4. The root cause: shift change fragmentation, where the lack of specific technical identifiers in the handoff notes led to a misinterpretation of the recovery plan.
The technical resolution.
We corrected the offsets and standardized our handoff protocol. 1. Immediately performed a re-rewind of the search index offsets to restore data integrity for that group. 2. Correctly identified and skipped the poison pill offset in the claims group partition 4 to unblock the pipeline. 3. Implemented a Java-based poison pill sentinel that automatically moves malformed Kafka messages to a dead letter queue, DLQ. 4. Developed a handoff dashboard that displays the specific consumer group, partition, and offset that are currently in an error state.
What I changed forever.
I implemented these 4 structural guardrails for shift change continuity. 1. The identifier mandate established a rule that no technical handoff is complete without a unique system ID. For example, consumer group ID, thread ID, or DBP ID. 2. Mandatory overlap window enforced a 15-minute live handshake period where the outgoing and incoming engineers must walk through the ticket together. 3. Automated ticket summaries. Integrated a Slack bot that automatically pulls the last 5 logs and active metric into the handoff ticket to provide instant context. 4. Standardized Kafka runbooks. Created a specific action matrix for Kafka issues, requiring engineers to fill in the topic and group before running any CLI command. We reduced our handoff-related outages to 0 after implementing the identifier mandate.
Summary card.
Key takeaway for your interview: incident type, documentation deficit and shift change fragmentation. Bad decision: providing a vague Kafka handoff note without specific consumer group IDs or partition numbers. Impact: 3-hour secondary data sync issue and 500,000 unprocessed claims due to incorrect offset resets. Guardrail implemented: mandatory unique identifier handoff policy and automated DLQ processing for poison pills. A handoff should be a copy-paste instruction, not a guessing game.
The interview-winning answer template.
During a Kafka poison pill incident, I made the bad decision to provide a vague shift handoff note that did not include the specific consumer group ID. This led the morning team to reset the wrong offsets, causing a 3-hour secondary data issue. I resolved this by leading the recovery and then implementing a unique identifier handoff mandate. This taught me that technical clarity is more important than speed during shift changes. I have since enforced mandatory 15-minute synchronous handoffs and automated ticket summaries, ensuring our team never loses context between shifts again.
Follow-up 1. If you are at the end of a 12-hour shift and a P1 starts, do you stay or hand off immediately?
Answer: I stay for the first 30 minutes to stabilize the triage. Then, I perform a structured handoff to a fresh engineer. A fatigued engineer is a risk. In senior support, we prioritize quality of decision-making over heroism. The fresh eyes of my teammate are better for the business than my 13th hour of work.
Follow-up 2. How do you handle a teammate who consistently gives poor, vague handoffs?
Answer: I address it during the post-mortem or a one-on-one. I show them the total cost of the vagueness, how it led to extra downtime or wasted work. I then provide them with our standardized handoff template to make it easier for them to give high-quality updates in the future.
Follow-up 3. Curveball. What if the handoff notes are perfect, but the incident tools like Jira or Slack go down during the shift change? How do you hand off then?
Answer: we use a secondary out-of-band channel, like a Zoom bridge or a private mobile group. Every support team should have an emergency communication plan. In senior roles, we never rely on a single tool for operational continuity.
Pro tip, the identity rule.
In a senior Java support role, remember, identifiers are the language of truth. Never use words like the service or the topic in a handoff. Use service of V2 or claims events partition for. Specificity saves systems.
Explain a bad decision you made. Question 74. The hero complex.
Interviewer asks, explain a mistake where you stayed on an incident too long instead of handing off properly. Incident type: fatigue management and operational tunnel vision. Interviewer insight: this question evaluates your judgment and team trust. A senior engineer knows that after 10 hours of debugging, the brain makes mistakes. They want to see that you have moved past the hero complex and understand that a fresh pair of eyes is the most powerful tool in production support.
The star story and reflection.
Here is the account of how staying on a bridge for 14 hours made an incident worse. Situation: we were in the middle of a massive out-of-memory crisis that was crashing our entire Java inventory cluster every 20 minutes. Task: my task was to identify the leak and provide a JVM configuration fix to stabilize the environment. Action: the bad decision plus why it happened. I made the bad decision to stay on the incident bridge for 14 straight hours. I refused to hand off to the morning shift because I felt I was close to the answer and did not want to waste time re-explaining the context. I suffered from tunnel vision and extreme cognitive fatigue. Result: the impact. In my exhausted state, I wrote a cleanup regex to purge some temporary files. I made a typo in the regex that accidentally deleted our core application.yml file on the primary node. I turned a performance issue into a total blackout. The outage was extended by 4 hours because of my human error. We lost an additional $200,000 in revenue during those 4 hours. Reflection: I learned that a tired hero is a hazard. After 10 hours, your diagnostic quality drops by 50%. A senior engineer's greatest skill is knowing when to step away and let a fresh mind take over. Fatigue is the quietest source of catastrophic human error.
The investigation steps and root cause.
As the server failed to restart, the morning team audited my last actions. 1. Ran history on the server and identified the malformed rm command I had executed. 2. Confirmed that the application.yml was missing from the /config directory. 3. Observed that my Slack communication had become incoherent and erratic in the final 2 hours of the shift. 4. The root cause: cognitive fatigue, leading to a high-severity human error during a critical recovery window, caused by a refusal to hand off tasks.
The technical resolution.
The fresh morning shift restored the system and enforced a rest policy. 1. Immediately restored the application.yml from the Git repository using the automated CI/CD pipeline. 2. Identified the memory leak within 30 minutes of taking over. It was a simple static map in a new cache module that I had missed because of fatigue. 3. Implemented a read-only file system for core configuration directories to prevent accidental deletion via regex or manual commands. 4. Enforced a mandatory sleep and reset period for me, removing my production access for 24 hours to ensure recovery.
What I changed forever.
I implemented these 4 structural guardrails for fatigue management. 1. The 10-hour hard cap established a team rule that no engineer can remain in an active P1 incident role for more than 10 consecutive hours without a 4-hour rest. 2. Mandatory fresh eyes audit mandated that any destructive command RM, update, delete run after hour 8 of a shift must be peer-reviewed by a second engineer. 3. The shadow lead rotation implemented a policy where every P1 incident has a primary and a secondary lead. The secondary's only job is to prepare for the handoff. 4. Fatigue-aware incident command trained our incident commanders to actively monitor for signs of engineer burnout and force handoffs even if the engineer resists. We have reduced human error downtime by 80% since enforcing shift caps.
Summary card.
Key takeaway for your interview. Incident type, fatigue management and operational tunnel vision. Bad decision, staying on a P1 bridge for 14 hours and refusing to hand off, leading to a catastrophic typo that deleted core config files. Impact, total system blackout extended by 4 hours and $200,000 additional revenue loss. Guardrail implemented, mandatory 10-hour hard cap for incident response and fresh eyes audit for destructive commands. A senior engineer trusts their team as much as they trust their code.
The interview-winning answer template.
During a massive memory leak crisis, I made the bad decision to stay on the bridge for 14 hours because I felt responsible for the fix. In my exhausted state, I made a typo in a cleanup script that deleted our core configuration, causing a total blackout for 4 hours. I resolved this by handing off to a fresh team who fixed the issue in 30 minutes. This taught me that heroism is an operational risk. I have since implemented a 10-hour hard cap for incident response and a fresh eyes policy for all production changes, which has made our support much more reliable.
Follow-up 1. How do you gracefully hand off when you are just about to find the fix?
Answer: I record my current hypothesis and the path I have ruled out in the ticket. I tell the new engineer, I think the leak is in this class. I have checked the logs here and here. I am stepping away now to ensure you have a clean slate to finish the job. I prioritize the system over my own sense of completion.
Follow-up 2. What are the signs of cognitive fatigue you look for in your teammates during an incident?
Answer: I look for repetitive questions, irritability, or tunnel vision, focusing on one minor detail while the house is burning. If an engineer stops seeing the big picture or starts making simple typos in chat, I know it is time to force a handoff.
Follow-up 3. Curveball. What if there is no one to hand off to? For example, a very small team. What's your move then?
Answer: then I prioritize stabilization over RCA. I would perform a safe mitigation, like a scheduled restart or a cluster drain. Communicate to stakeholders that we are entering a maintenance window for 4 hours and get some rest. A system on life support is better than a system being managed by a zombie engineer.
Pro tip: the fresh eyes law.
In a senior Java support role, remember, the answer is usually invisible to the person who has been looking for it for 8 hours. Do not be a hero, be a teammate. Step away, sleep, and let the fresh mind find the sense-sized bug you missed.
Category 15 wrap-up. The collaboration lesson.
We have explored the vital importance of the human element in production support, from the precision required in technical handoffs to the dangers of the hero complex. The lesson is that a senior engineer builds a collective team brain through documentation and disciplined communication. But as we move into modern, cloud-native environments, the complexity shifts from managing people to managing ephemeral infrastructure. This leads us into Category 16, Cloud and Containerization Mistakes.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, and system design. Required for your Java job interviews like Java Application Support Engineer jobs, AWS Java Developer jobs, Java Backend Developer jobs, Site Reliability Engineer SRE jobs, Java DevOps Engineer jobs, Java Kubernetes Developer jobs, Java Blockchain Developer jobs, Application Security Engineer jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem solving, interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people. Also for your interviews, you people can download all 6 PDFs in a single zip file from below given links.
Category 16. Cloud and containerization mistakes.
In a modern Java environment, your application no longer lives on a static server. It lives in a Kubernetes pod. This transition changes everything, from how you calculate memory to how you define service health. This category evaluates your ability to troubleshoot in a containerized world. Interviewers want to see that you understand the difference between a JVM crash and a Kubernetes OOMKilled, and that you know how to configure resource limits to survive in a shared cloud environment.
The Cloud Challenge, questions 75 to 78.
Be prepared to discuss these Kubernetes and Docker failures in your next interview. 75. Tell me about a time you misconfigured Kubernetes resources causing Java pods to be OOMKilled. 76. Describe a situation where a container probe failure caused rolling outages in your Java app. 77. Have you ever chased a performance issue that turned out to be noisy neighbors or CPU throttling? 78. Explain a mistake where local testing passed, but the Docker image was missing critical dependencies. Interviewers evaluate your transition from traditional server thinking to ephemeral container troubleshooting.
Explain a bad decision you made. Question 75. The Kubernetes OOMKilled.
Interviewer asks, tell me about a time you misconfigured Kubernetes resources causing Java pods to be OOMKilled by the node. Incident type, resource mismanagement, and container memory violation. Interviewer insight. This question tests your understanding of container awareness in Java. A junior engineer blames K 8 seconds for being aggressive. A senior engineer explains how they failed to account for non-heap memory and how they implemented max RAM percentage to ensure the JVM and pod work in harmony.
The star story and reflection.
Here is the account of how a tight Kubernetes limit crashed our microservices. Situation: we were migrating a high-volume Java 11 microservice to a Kubernetes cluster. We wanted to maximize pod density to save cloud costs. Task: my task was to define the YAML resource requests and limits for the deployment. Action: the bad decision plus why it happened. I made the bad decision to set the Kubernetes memory limit to 2 GB while setting the JVM heap XMX also to 2 GB. I assumed that since the JVM would not exceed 2 GB, the container was safe. I ignored the metaspace, code cache, and compressed class space that live outside the heap. Result: the impact. Within 10 minutes of hitting production traffic, the pods began disappearing. There were no out-of-memory error messages in the logs. The pods just entered a crash loop back-off state. We suffered a rolling outage across the cluster for 45 minutes, affecting 10,000 active sessions and causing $40,000 in lost revenue. Reflection: I learned that the JVM is much greedier than just its heap. In a container, the total memory footprint RSS is what the OS cares about. If you do not leave air for non-heap resources, Kubernetes will kill your pod without warning. The JVM heap is not the container limit. It is only a subset of it.
The investigation steps and root cause.
As the application logs showed no errors, I looked at the Kubernetes control plane. 1. Ran kubectl describe pod and identified the reason, OOMKilled and exit code, 137 status. 2. Used kubectl top pod to observe that the memory usage was pinned at exactly 100% of the limit. 3. Checked the Prometheus metrics for container resident set size and saw it exceeded the 2 GB limit due to metaspace and thread stacks. 4. The root cause, container resource misconfiguration, where the JVM heap was set equal to the pod limit, leaving zero room for native memory overhead.
The technical resolution.
We realigned the JVM with the Kubernetes limits. 1. Immediately increase the Kubernetes memory limit to 3 GB while keeping the JVM heap at 2 GB to provide immediate relief. 2. Remove the hard-coded XMX flag and replaced it with -XX:\max RAM percentage equals 75.0 to allow the JVM to scale dynamically with the pod limits. 3. Enabled -XX: native memory tracking equals summary to provide visibility into metaspace and direct buffer usage in the pod logs. 4. Implemented a pod disruption budget to ensure that even during OOM events, a minimum number of pods remained available to handle traffic.
What I changed forever.
I implemented these 4 structural guardrails for containerized Java safety. 1. The 25% buffer rule established a standard that JVM max heap must never exceed 75% of the Kubernetes container limit. 2. Percentage-based tuning mandated the use of max RAM percentage instead of fixed XMX values to ensure environment parity between dev and prod. 3. OOMKilled monitoring configured a high-priority alert in Grafana that triggers on kubepod OOMKilled events, distinguishing them from standard application crashes. 4. Resource linter in CI/CD added a step in our pipeline that validates the deployment YAML against a best practices schema, flagging any pod where limits equal heap size. We have reduced our OOMKilled incidents by 100% since adopting percentage-based tuning.
Summary card.
Key takeaway for your interview: incident type, resource mismanagement and container memory violation. Bad decision, setting K8 seconds pod limits equal to JVM max heap, leaving no room for native memory. Impact, exit code 137 OOMKilled, and a 45-minute rolling outage for 10,000 users. Guardrail implemented. Mandatory percentage-based heap sizing, -XX:\max RAM percentage equals 75.0, and RSS-aware alerting. In Kubernetes, the container is the boundary. The JVM is just the guest.
The interview-winning answer template.
During our first major Kubernetes migration, I made the bad decision to set our Java pod limits equal to the JVM heap size. I did not account for native memory like metaspace, causing the node to OOMKilled our pods under load. I resolved this by increasing the pod overhead and switching to percentage-based heap tuning. This taught me that containerized Java requires a full-stack view of memory. I have since enforced a 25% buffer rule and automated OOMKilled monitoring, ensuring our pods stay stable regardless of traffic spikes.
Follow-up 1. What is exit code 137, and how is it different from exit code 1?
Answer: exit code 137 means the process was terminated by an external signal SIG-kill because it exceeded its container memory limit, 128 plus 9. Exit code 1 usually means the application crashed internally due to a code error or an uncaught exception.
Follow-up 2. Why would you set requests lower than limits in Kubernetes for a Java application?
Answer: requests are for scheduling, finding a node with enough space. Limits are for enforcement, killing the pod if it goes over. We set requests lower to allow for bursting during startup or high load, but we ensure the request is high enough to satisfy the JVM's minimum heap requirement.
Follow-up 3. Curveball. If the node itself is running out of memory, but your pod is under its limit, will Kubernetes still kill your pod?
Answer: yes. This is called node pressure eviction. Kubernetes will start killing pods to save the node, starting with pods that have best effort or burstable quality of service, QoS. To prevent this, we use guaranteed QoS by setting requests equal to limits for critical services.
Pro tip: the container-aware rule.
In modern Java support, never use XMX in a pod. Always use -XX:\max RAM percentage. This makes your application container-aware, allowing it to automatically adjust its heap based on the Kubernetes YAML without requiring a code or config change for every environment.
Explain a bad decision you made. Question 76. The flapping probe.
Interviewer asks, describe a situation where a container probe failure caused rolling outages in your Java app. Incident type, misconfigured health checks and cascading restart. Interviewer insight, this question reveals your orchestration maturity. A junior engineer thinks probes are simple heartbeats. A senior engineer knows that a poorly configured liveness probe can turn a temporary delay into a permanent crash loop. They want to see how you move to decoupled probes to protect the application's uptime.
The star story and reflection.
Here is the account of how an overambitious health check crashed our production API. Situation: we were managing a high-throughput Spring Boot application in Kubernetes. We used the /actuator or health endpoint for both liveness and readiness probes. Task: my task was to ensure that the pods were automatically restarted if the application became unresponsive. Action: the bad decision plus why it happened. I made the bad decision to include a deep database check inside the liveness probe. I assumed that if the application could not reach the database, the pod should be killed and restarted. I wanted a self-healing system that would reset during database glitches. Result: the impact. During a routine database failover, the DB was unreachable for 30 seconds. Because the liveness probe failed, Kubernetes began killing and restarting all 50 pods at once. The restarts created a connection storm that prevented the DB from recovering. What should have been a 30-second glitch became a 2-hour total blackout. Reflection: I learned that liveness is a drastic measure. It means I am dead, kill me. If you link liveness to a downstream dependency, you aren't fixing the service. You are launching a suicide pact for your entire cluster. A liveness probe should only monitor internal application health, never external ones.
The investigation steps and root cause.
As the pods entered a massive restart loop, I audited the Kubernetes events. 1. Ran kubectl get events and saw hundreds of liveness probe failed. HTTP 503 messages across the namespace. 2. Checked the Spring Boot logs and found the actuator was reporting down because the DB health indicator had timed out. 3. Identified that the restart loop was happening faster than the application's startup time, 60 seconds, preventing any pod from becoming ready. 4. The root cause, liveness probe entanglement, where a transient downstream dependency failure triggered a global pod termination cycle.
The technical resolution.
We decoupled the probes and restored the cluster stability. 1. Immediately modified the Kubernetes deployment to set liveness probe.failure threshold to 10 to stop the immediate restart loop. 2. Separated the probes, created a dedicated /health or liveness endpoint that only checks the JVM memory and threads, and a /health or readiness endpoint that checks dependencies. 3. Increased the initial delay seconds for the liveness probe to 120 seconds to allow the Spring context to fully initialize without being killed. 4. Configured the readiness probe to simply stop sending traffic to a pod during a DB failure, while keeping the pod alive to recover automatically.
What I changed forever.
I implemented these 4 structural guardrails for Kubernetes health checks. 1. The dependency isolation standard established a hard rule that liveness probes must never check external dependencies like SQL, RIDIs, or third-party APIs. 2. Readiness for dependencies mandated that external health checks live only in the readiness probe, ensuring traffic is redirected without killing the process. 3. Startup probe implementation migrated our legacy initial delay settings to dedicated startup probes for apps with slow initialization, like heavy Spring monoliths. 4. Probe timeout alerting configured Prometheus alerts for probe latency to detect when a health check is becoming slow, which is often a precursor to a total failure. We have reduced our restart loop incidents to 0 since adopting probe separation.
Summary card.
Key takeaway for your interview. Incident type, misconfigured health checks and cascading restart. Bad decision, using a deep actuator health check, checking the DB for a Kubernetes liveness probe. Impact 2-hour total blackout as a 30-second DB failover triggered a global pod restart loop. Guardrail implemented, separated liveness internal health from readiness dependency health, and implemented startup probes. A liveness probe is a kill signal. Use it with extreme caution.
The interview winning answer template.
During a database failover, I made the bad decision to have our Kubernetes liveness probe check the DB health. This caused K 8 seconds to kill every pod in the cluster simultaneously, turning a minor glitch into a 2-hour outage. I resolved this by separating our probes and ensuring liveness only checks the internal JVM state. This taught me that liveness is a last resort. I have since implemented readiness-only dependency checks and startup probes, which ensures our services can survive downstream instability without crashing their own nodes.
Follow-up 1. What is the primary difference between a liveness, readiness, and startup probe?
Answer: startup probes run first and disable the other two until the app is booted. Readiness probes determine if a pod can accept traffic. Liveness probes determine if the pod needs to be restarted entirely. Readiness protects the user. Liveness protects the system from a deadlock process.
Follow-up 2. If the readiness probe fails but the liveness probe passes, what happens to the pod?
Answer: the pod remains running, but its ready status becomes false. The Kubernetes service will remove the pod's IP from the load balancer, so it stops receiving traffic. It will stay in this state until the readiness probe passes again.
Follow-up 3. Curveball. What if your probes are too frequent, for example, every 1 second? What is the risk to a Java application?
Answer: it can cause resource starvation and log bloat. Each probe call is a fresh HTTP request that consumes a worker thread and CPU cycles. In a busy JVM, thousands of probe calls per minute can compete with business traffic and lead to false failure timeouts.
Pro tip: the independence rule.
In a senior Java support role, remember, probes must be independent. Your application pod should be able to pass its liveness probe even if every other service in the data center is down. Use readiness to manage traffic, but use liveness only to catch local JVM deadlocks.
Explain a bad decision you made. Question 77. The CPU throttling trap.
Interviewer asks, have you ever chased a performance issue that turned out to be noisy neighbors or CPU throttling? Incident type: infrastructure resource contention and CFS quota throttling. Interviewer insight: this is a high-level question about shared infrastructure. Junior engineers blame the Java code for being slow. A senior engineer knows that the Kubernetes CFS quota can throttle a healthy app. They want to see how you used throttling metrics to identify that the node, not the code, was the problem.
The star story and reflection.
Here is the account of how I spent 4 hours tuning GC while Kubernetes was choking our CPU. Situation: one of our high concurrency Java APIs was suffering from random response time spikes that jumped from 100 milliseconds to 2 seconds for no apparent reason. Task: my task was to identify the performance bottleneck and stabilize the API latency during the peak afternoon window. Action: the bad decision plus why it happened. I saw stop the world pauses in the logs and assumed we had a garbage collection problem. I made the bad decision to spend 4 hours aggressively tuning the G1 GC parameters and heap sizes. I ignored the container metrics because I believed the JVM logs were the source of truth. Result: the impact. My tuning did nothing. The latency spikes continued, causing 5,000 customer timeouts. The real issue was CPU throttling by the Kubernetes CFS, completely fair scheduler. Our pods were using their full CPU limit in short bursts, and the OS was suspending our process for milliseconds at a time. My delay caused 4 hours of customer frustration. Reflection: I learned that internal slowness, like slow GC, is often an effect of external constraints. If the OS is starving the JVM of CPU cycles, the JVM will appear slow even if the code is perfect. A throttled CPU makes a healthy JVM look like a broken one.
The investigation steps and root cause.
Once I realized the GC tuning was not working, I looked at the container runtime metrics. 1. Analyze the Prometheus metric container underscore CPU underscore CFS underscore throttled underscore periods underscore total, and saw it was spiking in sync with the latency. 2. Observed that our CPU limit was set to 2 cores, but our Java application's fork join pool was trying to use all 16 cores of the underlying node. 3. Found that the JVM was making bursty allocations that exceeded the 100 millisecond CFS quota window, causing the OS to pause the application threads. 4. The root cause, CPU quota mismatch where the application's thread concurrency was not aligned with the Kubernetes CPU limits, leading to aggressive throttling.
The technical resolution.
We realigned the application with the container limits. 1. Immediately increase the Kubernetes CPU limit to 4 cores and set the requests equal to the limits to ensure guaranteed QoS. 2. Explicitly limited the Java common pool using java.util.concurrent.fork join pool.common.parallelism equals 4 to match the pod limit. 3. Switch to a newer JVM version, Java 11.0.3+, that had improved CFS-aware logic for better resource utilization inside containers. 4. Added a CPU throttling dashboard in Grafana that alerts us the moment a pod loses more than 5% of its periods to throttling.
What I changed forever.
I implemented these 4 structural guardrails to prevent CPU-related performance issues. 1. The guaranteed QoS policy mandated that all P1 critical Java services must have CPU requests equal to CPU limits to prevent noisy neighbor preemption. 2. Explicit thread configuration established a rule that all thread pools, Tomcat, HTTP clients, fork join must be explicitly sized based on pod CPU limits, never left to auto-detection. 3. Throttling first triage updated our performance runbook to make CPU throttling the first metric checked during any latency investigation in Kubernetes. 4. Vertical pod autoscaler, VPA, implemented VPA in recommendation mode to help us accurately size pods based on their real-world burst requirements. We have reduced our mystery latency incidents by 80% since adopting throttling-aware monitoring.
Summary card.
Key takeaway for your interview: incident type, infrastructure resource contention, and CFS quota throttling. Bad decision, assuming latency was a Java GC issue and wasting 4 hours tuning the JVM, while K8 seconds was throttling the CPU. Impact: 5,000 customer timeouts and 4 hours of degraded performance due to pod-level resource limits. Guardrail implemented: mandatory guaranteed QoS, requests equals limits, and automated CPU throttling alerts. In the cloud, the OS is the ultimate judge of your application's speed.
The interview-winning answer template.
During a latency crisis, I made the bad decision to focus entirely on Java GC logs, thinking the app was slow. After 4 hours of tuning, I realized the problem was actually Kubernetes CPU throttling. Our app was hitting its limits in microbursts, and the OS was suspending our threads. I resolved this by setting our CPU requests equal to limits and aligning our Java thread pools. This taught me that internal slowness is often an external resource constraint. I have since implemented throttling-aware dashboards, which has completely eliminated mystery latency spikes in our cluster.
Follow-up 1. What is CFS throttling, and why does it happen even if a pod is under its average CPU limit?
Answer: Kubernetes measures CPU usage in 100 milliseconds windows. If a pod uses its entire quota in the first 20 milliseconds of that window, a burst, the OS will suspend it for the remaining 80 milliseconds. This causes latency spikes even if the average CPU over a minute looks low.
Follow-up 2. How do you size a thread pool for a Java app running in a pod with 0.5 CPU limit?
Answer: I would set the thread pool to 1 or 2 threads. If you have 200 threads competing for 0.5 CPUs, you will suffer from massive context switching overhead. In senior support, we always align thread count with available CPU to maximize throughput.
Follow-up 3. Curveball. What is a noisy neighbor in Kubernetes, and how do you protect your Java app from one?
Answer: a noisy neighbor is another pod on the same node that is consuming excessive shared resources, like I/O or cache. I protect critical apps by using resource requests, which reserves capacity, and anti-affinity rules to ensure 2 heavy traffic apps never share the same physical node.
Pro tip: the throttling law.
In a senior Java support role, remember, you cannot debug what you cannot see. If you are running in Kubernetes, your JVM metrics are only half the story. Always check the throttled periods metric in your node exporter, or you will spend your life fixing code that is not actually slow.
Explain a bad decision you made. Question 78. The certless Docker image.
Interviewer asks, explain a mistake where local testing passed, but the Docker image built for production was missing critical dependencies or certificates. Incident type: Docker image mismatch and security handshake failure. Interviewer insight: this question targets your packaging discipline. In a containerized world, the build artifact is the entire image. They want to see how you moved from implicit dependencies to explicit Docker layers, and how you implemented post-build validation to ensure the image is truly production-ready.
The star story and reflection.
Here is the account of how a slim Docker image broke our secure API connections. Situation: we were moving to multi-stage Docker builds to reduce our image size for a new Java microservice that communicated with an external bank API. Task: my task was to optimize the Docker file and ensure the final production image was under 200 megabytes. Action: the bad decision plus why it happened. I made the bad decision to use a distroless base image for the final stage without verifying the pre-installed libraries. I assumed that because the build stage had all the certificates, the run stage would inherit them automatically. I was so focused on image size that I skipped the handshake test in the staging environment. Result: the impact. In production, the service failed to connect to the bank API. It threw SSL handshake exception. Pkix path building failed because the new slim image was missing the CA certificates bundle. All outgoing payments were blocked for 3 hours, resulting in a major SLA breach and a $120,000 revenue impact. Reflection: I learned that a slim image is a high-risk image. If you do not explicitly manage your OS-level dependencies like certificates and fonts, your Java code will fail the moment it tries to interact with the outside world. Optimizing for size should never compromise the application's runtime context.
The investigation steps and root cause.
As the connection errors flooded our logs, we audited the Docker image. 1. Analyzed the stack trace and identified the failure to verify the server's certificate chain. 2. Ran a Docker run at entry.sh on the production image and checked the /etc or SSL or certs directory. 3. Confirmed that the directory was empty because the distroless image I chose did not include the standard CA bundle. 4. The root cause: multi-stage build leakage, where critical OS-level dependencies, certificates, were lost between the build and execution stages of the Docker image.
The technical resolution.
We restored the security chain and hardened our image builds. 1. Immediately reverted to the previous fat Docker image to restore the payment processing flow. 2. Updated the Docker file to explicitly copy the CA certificates bundle from the build stage to the run stage using the copy from command. 3. Modified the Java startup script to include javax.net.debug equals SSL as a temporary debugging aid to verify the handshake sequence. 4. Implemented a post-build integration test that pings a secure mock-in point to verify SSL connectivity before the image is pushed to the registry.
What I changed forever.
I implemented these 4 structural guardrails for Docker image safety. 1. The base image standard established a rule that all production images must use a pre-approved, security-hardened company base image that includes all necessary CA certs and fonts. 2. Automated image scanning integrated Aqua or Trivy into our CI pipeline to automatically scan images for missing dependencies and security vulnerabilities before release. 3. Explicit layer auditing enforced a rule that every Dockerfile PR must include a layer audit showing exactly what is being copied into the final image. 4. Staging handshake verification mandated that every microservice release must pass an egress test in staging that verifies connectivity to all third-party APIs. We have reduced our image mismatch incidents to 0 since adopting pre-approved base images.
Summary card.
Key takeaway for your interview: incident type, Docker image mismatch and security handshake failure. Bad decision, using a distroless base image for the final production stage without verifying the presence of CA certificates. Impact, SSL handshake exception across all pods, blocking all outgoing payments for 3 hours and $120,000 revenue loss. Guardrail implemented, mandatory hardened base image standard and automated egress test in the staging pipeline. A Docker image is a promise of a complete runtime. Make sure it keeps that promise.
The interview winning answer template.
While optimizing our microservices, I made the bad decision to use a distroless Docker image to save space, but I failed to realize it was missing standard CA certificates. This caused our Java application to fail all secure API handshakes in production, resulting in a 3-hour payment blackout. I resolved this by correcting the Docker layers and implementing post-build egress tests. This taught me that slim images require more validation, not less. I have since enforced a policy of using pre-approved base images, which has completely eliminated dependency-related failures in our releases.
Follow-up 1. What is a multi-stage Docker build, and why is it recommended for Java applications?
Answer: multi-stage builds use one stage for building with Maven or JDK, and a second stage for running with just the JRE. It is recommended because it keeps the final image small and secure by removing the compiler and source code from the production environment.
Follow-up 2. How do you handle custom certificates, internal CAs, in a containerized environment?
Answer: we use init containers or secrets in Kubernetes. We store the certificate in a secret and mount it as a volume in the pod. At startup, a script adds the certificate to the Java caserts file in the container's memory so the app can trust internal services.
Follow-up 3. Curveball. What if your Docker image works in AWS, but fails in Azure because of a storage driver issue? How do you diagnose that?
Answer: I would look at the image layers using Docker Inspect. I would check for OS-level library differences, like glib versus muscle. To prevent this, we use OCI-compliant images and perform cross-cloud testing if we are in a multi-cloud environment to ensure the image behaves identically on different container runtimes.
Pro tip, the full context rule.
In a senior Java support role, remember, your code does not run on air. It runs on an OS, which runs on a container. If you optimize for image size, you are cutting the context out of your application. Always verify the minimum viable OS required for your app to talk to the world.
Category 16 wrap-up, the container lesson.
We have seen how the shift from VMs to Kubernetes pods changes the rules of resource management. The lesson is that in a containerized world, the application is not the master of the host. It is a guest that must strictly respect the quotas and probes of the orchestrator. But even with perfect container sizing, a Java application can still freeze from the inside due to poorly managed threads. This leads us to Category 17, concurrency, locks, and threading mistakes.
Category 17, concurrency, locks, and threading mistakes.
Threading and concurrency are the hallmarks of a senior Java support engineer. This is the domain where junior engineers get lost in logs, while senior engineers dive into thread dumps. This category evaluates your deep understanding of the Java memory model, lock contention, and the hidden bottlenecks of asynchronous processing. Interviewers want to see that you can identify a deadlock or a thundering herd and implement non-blocking strategies to ensure system-wide responsiveness.
The concurrency challenge, questions 79 to 82.
Be prepared to discuss these advanced multi-threading and locking failures in your next interview. 79. Tell me about a time your application suffered from a deadlock in production and how you misdiagnosed it. 80. Describe a situation where a shared resource became a bottleneck and caused thread starvation. 81. Have you ever encountered a thundering herd problem when a cache expired? 82. Explain a mistake where asynchronous processing masked the true source of an error. Interviewers evaluate your mastery of the Java concurrency utilities and your ability to solve complex race conditions.
Explain a bad decision you made. Question 79, the circular lock.
Interviewer asks, tell me about a time your application suffered from a deadlock in production. How did you misdiagnose it initially? Incident type, Java deadlock and resource contention. Interviewer insight, this question probes your forensic triage skills. Deadlocks cause frozen systems with 0% CPU, which often fools engineers into thinking it is a network issue. A senior engineer explains how they use JStack to prove a circular dependency, and how they refactored the code to use global lock ordering.
The star story and reflection.
Here is the account of how a circular dependency in our code froze the entire checkout flow. Situation: we were managing a Java-based retail platform. During a high concurrency flash sale, the checkout API response time suddenly jumped from 50 milliseconds to infinite timeout. Task: My task was to identify the source of the freeze and restore the transaction processing before the sale ended. Action: the bad decision plus why it happened. I saw that the CPU usage on the servers dropped to near zero. I made the bad decision to assume the load balancer had stopped sending traffic, or that the firewall was blocking incoming requests. I spent 45 minutes auditing network security groups and VPC flow logs because low CPU suggested the app was not doing any work. Result: the impact. The network was healthy. The Java application was alive but frozen internally. By the time I took a thread dump, 400 worker threads were blocked. We lost 45 minutes of prime sale time, resulting in a $250,000 revenue loss and thousands of abandoned carts. Reflection: I learned that zero CPU is the primary symptom of a deadlock. In a senior support role, if the system is slow but the resources are idle, the threads are fighting for a lock. A thread dump is the only way to see the standoff. In Java, a silent application is often a deadlocked one.
The investigation steps and root cause.
Once I pivoted to JVM diagnostics, the root cause was immediately visible. 1. Ran JStack-LPID and searched for the string found one deadlock. 2. Identified that thread A held a lock on the inventory service and was waiting for the pricing service lock. 3. Identified that thread B held a lock on the pricing service and was waiting for the inventory service lock. 4. The root cause: circular deadlock caused by inconsistent lock acquisition order between two different modules during a high concurrency event.
The technical resolution.
We broke the lock and hardened the concurrency logic. 1. Immediately performed a rolling restart of the cluster to clear the blocked threads and restore service for the remainder of the sale. 2. Refactored the Java code to implement global lock ordering, ensuring every module always acquires the inventory lock before the pricing lock. 3. Replaced the legacy synchronized blocks with reentrant lock.try lock parentheses with a 5-second timeout to ensure threads fail fast rather than hanging indefinitely. 4. Added a wait-free cache for pricing data to reduce the frequency of entering the synchronized blocks during peak load.
What I changed forever.
I implemented these 4 structural guardrails for concurrency safety. 1. Deadlock-aware monitoring. Configured our APM tool to automatically trigger a thread dump and a P1 alert if blocked threads exceed 5% of the pool. 2. Mandatory concurrency reviews. Established a rule that any code using the synchronized keyword or lock interface must undergo a dedicated concurrency audit by a lead architect. 3. Static analysis for locks. Integrated find bugs or sonar Quebec concurrency rules into our pipeline to detect potential lock inversion during the build phase. 4. The zero CPU triage rule. Updated our support runbook to make thread dump analysis the #1 priority if a latency spike is accompanied by a CPU drop. We have reduced our silent freeze incidents to 0 since adopting lock ordering standards.
Summary card.
Key takeaway for your interview: incident type, Java deadlock and resource contention. Bad decision, assuming a low CPU system hang was a network issue and wasting 45 minutes on firewall audits. Impact, total checkout blackout during a flash sale and $250,000 lost revenue. Guardrail implemented, mandatory global lock ordering and automated JStack capture for blocked threads. Your CPU does not know when your threads are fighting. You must look at the dump.
The interview-winning answer template.
During a high concurrency sale, I made the bad decision to treat a total API hang as a network failure because the CPU usage was at 0. I spent 45 minutes auditing firewalls before a thread dump revealed a circular deadlock between our inventory and pricing services. I resolved this by refactoring our locking order and implementing try-lock timeouts. This taught me that low CPU is a major diagnostic signal for deadlocks. I have since implemented automated thread dump triggers and mandatory concurrency audits, which has completely eliminated silent freezes in our production environment.
Follow-up 1. What is the difference between a deadlock and a live lock in a Java application?
Answer: in a deadlock, threads are stationary and waiting forever, 0% CPU. In a live lock, threads are constantly changing state or retrying in response to each other but making 0 progress, high CPU. Both result in a system hang, but the CPU usage is the key differentiator.
Follow-up 2. Why is reentrant lock generally preferred over the synchronized keyword in senior Java support?
Answer: reentrant lock provides extended capabilities like try lock parentheses, timeouts, lock interruptibly parentheses, and fairness settings. These allow us to write safe code that can give up on a lock and log an error rather than hanging the thread forever, which is impossible with synchronized blocks.
Follow-up 3 Curveball. What if you find a deadlock in a third-party library that you cannot change? How do you fix it?
Answer: I would use external synchronization. I would wrap the calls to that library in a single-threaded serializing proxy or use our own global lock to ensure that only one thread can enter the problematic library code at a time. I would also open an urgent bug report with the vendor.
Pro tip, the lock order rule.
In a senior Java support role, remember, deadlocks are logical errors. They only happen when threads do not agree on the order of operations. Always establish a strict lock hierarchy, a before B, B before C, and enforce it across your entire codebase, or concurrency will eventually freeze your system.
Explain a bad decision you made. Question 80, the thread starvation.
Interviewer asks, describe a situation where a shared resource became a bottleneck and caused thread starvation. Incident type: shared resource contention and thread pool exhaustion. Interviewer insight: this question evaluates your full-stack dependency knowledge. Threads do not just wait on each other, they wait on connections and external APIs. A senior engineer explains how they mismanaged a connection pool and how they implemented bulkhead isolation to protect the application from a single slow resource.
The star story and reflection.
Here is the account of how a logging database took down our entire user-facing API. Situation: we were managing a Java-based microservice that processed customer orders. The app had two database connections, a high-performance primary DB for orders and a legacy DB for audit logging. Task: my task was to ensure the order processing remained fast, even if the secondary audit logging was slightly delayed. Action: the bad decision plus why it happened. I made the bad decision to use a single shared thread pool for both the order processing and the audit logging tasks. I assumed that because the audit calls were short, they would not impact the orders. I did not set a separate timeout for the legacy DB connection. Result: the impact. The legacy DB suffered a hardware failure and became extremely slow, taking 20 seconds per request. Because I was using a shared pool, the audit tasks quickly occupied all 200 threads. Order processing, which was healthy, could not get a thread to run. The entire site went down for 2 hours, resulting in $180,000 in lost transactions. Reflection: I learned that a minor dependency can become a fatal bottleneck if it shares resources with critical paths. In senior support, we use bulkheads to ensure that if one engine fails, the rest of the plane keeps flying. Resource isolation is the key to distributed system resilience.
The investigation steps and root cause.
As the application health checks began failing, I performed a thread resource audit. 1. Ran JStack and found 195 out of 200 threads were in socket read state, all waiting for the legacy DB IP address. 2. Used JCMD PID thread.print to see the call stack and confirmed that the threads were blocked inside the audit logging service. 3. Checked the Hikari CP metrics and saw active connections for the legacy pool were at 100%, while the primary pool was at 5%. 4. The root cause, thread starvation via shared pool, where a slow, non-critical dependency exhausted the common execution resources required by the critical business logic.
The technical resolution.
We isolated the failure and hardened the resource architecture. 1. Immediately applied a hot configuration change to disable the audit logging module, which instantly released the threads and restored order processing. 2. Refactored the application to use bulkhead isolation via Resilience 4J, giving the audit service its own dedicated thread pool with a small max size of 10. 3. Implemented a fail-fast connection timeout of 2 seconds for the legacy DB to ensure threads are never held longer than a typical user's patience. 4. Added a circuit breaker that automatically stops all logging attempts if the legacy DB latency exceeds 5 seconds, protecting the JVM from further starvation.
What I changed forever.
I implemented these 4 structural guardrails for resource isolation. 1. The bulkhead standard established an architectural rule that every external dependency DB, API, MQ must have its own isolated thread pool and connection pool. 2. Dependency tiering policy mandated that Tier 1 critical services can never wait on Tier 3 optional services in the same synchronous execution path. 3. Automated pool monitoring configured alerts for connection acquisition wait time on every individual pool, catching bottlenecks before they impact the thread count. 4. Failure mode integration testing added a suite of chaos tests that simulate high latency in secondary dependencies to prove the core system remains stable. We have reduced our cascading failure incidents by 90% since adopting bulkhead isolation.
Summary card.
Key takeaway for your interview. Incident type, shared resource contention and thread pool exhaustion. Bad decision, using a single shared thread pool for both critical order processing and non-critical audit logging. Impact, slow secondary database crashed the entire site for 2 hours, resulting in $180,000 lost revenue. Guardrail implemented, mandatory bulkhead isolation for all dependencies and strict per-resource timeouts. Never let an optional feature become a critical bottleneck.
The interview-winning answer template.
During a production outage, I made the bad decision to allow our core order processing to share a thread pool with a non-critical audit logging service. When the logging database slowed down, it exhausted all our worker threads and brought the entire site down for 2 hours. I resolved this by disabling the logging module and then refactoring the app using the bulkhead pattern to isolate each dependency. This taught me that shared resources are a risk for cascading failures. I have since enforced a policy of strict thread pool isolation and per-resource timeouts, which has made our architecture significantly more resilient.
Follow-up 1. What is the bulkhead pattern and how did it get its name?
Answer: it is named after the internal walls of a ship. If one section, the bulkhead, is flooded with water, the wall prevents the water from spreading to the rest of the ship. In Java, it means isolating a service's threads so that if that service fails, it does not sink the entire application.
Follow-up 2. How do you size an isolated thread pool for a secondary service like audit logging?
Answer: I use Little's Law. I look at the average response time of the service and the arrival rate of requests. For a non-critical service, I keep the pool small, for example, 5 to 10 threads, and use a bounded queue. If the pool is full, I would rather drop a log entry than hang an order.
Follow-up 3. Curveball. What if you isolate the pools, but the memory becomes the bottleneck instead of the threads? How do you fix that?
Answer: that usually happens if the isolated pools have unbounded queues. Even if the threads are limited, the memory fills up with pending tasks. I would implement backpressure by using a fixed size queue and a caller-runs rejection policy to slow down the producer when the consumer is overwhelmed.
Pro tip: the isolation law.
In a senior Java support role, remember, shared resources are shared risks. If you have 2 different services using the same database, the same thread pool, or the same network interface, they are not 2 services. They are one single point of failure. Isolate at the resource level to build true resilience.
Explain a bad decision you made. Question 81. The cache stampede.
Interviewer asks, have you ever encountered a thundering herd problem when a cache expired? How did you fix it? Incident type: cache stampede and database resource exhaustion. Interviewer insight: this question tests your high-scale architectural awareness. Caching is a standard tool, but uniform TTLS, time to live, create a massive risk during peak load. A senior engineer explains how they moved from static caching to probabilistic jitter and mutex loading to protect the backend database from being crushed by simultaneous cache misses.
The star story and reflection.
Here is the account of how a successful cache resulted in a database blackout. Situation: we were managing a high-volume retail site. To improve performance, we cached the product inventory data in Redis for 60 minutes. Task: my task was to ensure the application could handle 50,000 concurrent users during a holiday promotional event. Action: the bad decision plus why it happened. I made the bad decision to set a fixed TTL of exactly 3,600 seconds for all cached product items. I wanted to simplify the cache invalidation logic and assume the database could handle the refresh load because it was only a few hundred items. Result: the impact. Exactly 60 minutes after the promotion started, The cache for the top 10 items expired at the same millisecond. 50,000 concurrent requests bypassed the cache and hit the database simultaneously. The DB CPU hit 100% instantly, causing the Java connection pool to exhaust. The entire site went down for 20 minutes due to this thundering herd effect. Reflection: I learned that a cache is not just a performance booster, it is a shield. If your shield breaks all at once, your defense is gone. You must ensure that cache expirations are staggered, and that only one thread is allowed to rebuild a specific cache key at a time. In high-traffic systems, the simultaneity of events is your biggest enemy.
The investigation steps and root cause.
As the API response time spiked to 30 seconds, we performed a rapid triage. 1. Checked the Redis metrics and saw a massive get-miss spike followed by a drop in throughput. 2. Ran pg_stat_activity on the database and saw 500 identical select queries for the same product ID, all in active state. 3. Captured a Java thread dump and found hundreds of threads blocked on Hikari pool.get connection parentheses. 4. The root cause, cache stampede, where a synchronized expiration of a hot key caused a massive surge of redundant queries to the primary database.
The technical resolution.
We implemented origin protection logic to stabilize the data layer. 1. Immediately increased the DB connection pool size temporarily to allow the system to clear the query backlog. 2. Implemented TTL jitter by adding a random offset plus or minus 5 minutes to the Redis expiration time for every key, ensuring they never expire simultaneously. 3. Introduced mutex locking using redisen, so that only the first thread that detects a cache miss is allowed to query the DB. Others wait for the result. 4. Configured a soft expiry pattern where the application continues to serve stale data for 5 seconds while a background thread refreshes the cache.
What I changed forever.
I implemented these 4 structural guardrails for high-scale caching safety. 1. Mandatory cache jitter. Established a coding standard where all TTLs must be calculated as base plus random jitter to prevent synchronized expirations. 2. Single flight pattern. Enforced the use of mutex or locking for all hotkey cache loading to ensure the origin is only hit once per miss. 3. Stale while revalidate policy. Migrated our critical data paths to a background refresh model, where the user never waits for a cache miss to finish. 4. DB surge protection. Configured database-level statement timeouts and connection quotas to automatically kill redundant queries during a stampede event. We have reduced our cache-driven DB surges by 95% since implementing jitter.
Summary card.
Key takeaway for your interview. Incident type: cache stampede and database resource exhaustion. Bad decision: using a uniform fixed TTL for all cached product inventory items in a high-traffic environment. Impact: 20-minute site blackout as 50,000 concurrent users crushed the database during a simultaneous cache expiration. Guardrail implemented: probabilistic TTL jitter and mutex-based cache loading, single flight pattern. Protect the origin at all costs. A cache is a shield, not a guarantee.
The interview-winning answer template.
During a high-traffic sale, I made the bad decision to use a fixed TTL for our product cache. This resulted in a thundering herd problem where the cache for our most popular items expired at the same time, hitting our database with 50,000 concurrent requests and causing a 20-minute outage. I resolved this by implementing TTL jitter and mutex-based cache loading. This taught me that caching strategies must account for expiration concurrency. I have since enforced a stale while revalidate policy and mandatory TTL randomization, which has made our data layer significantly more resilient to traffic spikes.
Follow-up 1. What is the difference between cache stampede and cache penetration?
Answer: a cache stampede happens when a valid key expires, and many users try to reload it at once. Cache penetration happens when users query for invalid keys that do not exist in the DB, bypassing the cache every time. I use Bloom filters or caching nulls to solve penetration, but I use jitter to solve stampedes.
Follow-up 2. When using a mutex lock to reload a cache, what happens to the 49,999 users who did not get the lock?
Answer: it depends on the policy. They can either wait and retry the cache, briefly hanging, or they can be served the last known good stale value. In senior support, We usually prefer serving stale data for 2 seconds over hanging the user thread, as availability is our priority.
Follow-up 3, curveball. What if your Redis cluster itself is the source of the latency? How do you bypass it without killing the DB?
Answer: I use a circuit breaker for the cache. If Redis latency exceeds 20 milliseconds, the circuit opens and we fall back to a local in-memory cache, like caffeine, or a degraded mode where we show static data. We never let a failing cache layer become a direct path to crushing the database.
Pro tip, the jitter rule.
In a senior Java support role, remember, never let your system do the same thing at the same time. Whether it is cache expiration, log rotation, or scheduled batch jobs, always add random jitter. Synchronization in a distributed system is just a coordinated failure in waiting.
Explain a bad decision you made. Question 82, the silent async failure.
Interviewer asks, explain a mistake where asynchronous processing masked the true source of an error. Incident type, asynchronous exception masking and thread management error. Interviewer insight, this question reveals your diagnostic maturity. Asynchronous code, futures or MQs, detaches the error from the request thread. A senior engineer explains how they used fire and forget incorrectly, and how they implemented structured concurrency to ensure no exception is ever swallowed in a background thread.
The star story and reflection.
Here is the account of how async code hit a major data loss bug for 4 hours. Situation: we were managing a Java microservice that sent order confirmation emails. To keep the API response time under 100 milliseconds, we moved the email sending logic to a completable future run async parentheses block. Task: my task was to ensure that every successful order resulted in a customer notification within 5 minutes. Action: the bad decision plus why it happened. I made the bad decision to use a fire and forget approach for the async block without adding an exceptionally parentheses or handle parentheses block. I assumed that because the order was saved in the DB, the async task would just work. I wanted to avoid adding complex error handling to the cleanup logic. Result: the impact. An SMTP credentials change caused the email service to fail. Because the exceptions were happening in a background thread with no handler, they were swallowed by the JVM. Our success metrics stayed green, but 50,000 customers never received their orders. We only discovered the issue 4 hours later when customer support calls spiked. The delay caused a major reputation hit. Reflection: I learned that asynchronous does not mean unimportant. If you do not explicitly join or handle the result of a future, you are essentially telling the JVM to ignore any failures. Every background thread must have a loud and clear error reporting path. Swallowed exceptions in async code are the most expensive bugs to find.
The investigation steps and root cause.
As the support team reported missing emails, I audited the background threads. 1. Searched the application logs for error and found 0 entries related to the email service. 2. Took a thread dump and found the fork join pool worker threads were all idle, suggesting they were not stuck, just finished. 3. Enabled trace logging and finally saw the completable future terminating with a messaging exception that was never bubbled up to the main logs. 4. The root cause: exception swallowing in an asynchronous block, where the lack of a terminal error handler allowed background failures to remain invisible to the monitoring system.
The technical resolution.
We restored the notifications and hardened the async error handling. 1. Immediately fixed the SMTP credentials and reran a manual batch job to send the 50,000 missing confirmation emails. 2. Refactored all completable future blocks to include a mandatory, exceptionally parentheses block that logs the stack trace and increments a failure metric. 3. Configured a custom uncaught exception handler for our executor service to ensure that even if a thread dies unexpectedly, the error is recorded in the OS logs. 4. Implemented a dead letter table where any failed async notification is stored for automatic retry or manual intervention.
What I changed forever.
I implemented these 4 structural guardrails for asynchronous processing safety. 1. Mandatory error handlers. Established a check-style rule that fails the build if a completable future or future is created without a corresponding error handling method. 2. Async task monitoring. Integrated micrometer to track the number of started versus completed background tasks. A discrepancy now triggers a P2 alert. 3. Structured concurrency standards began migrating our async logic to scoped values in structured task scopes, Java 21+, to ensure clear ownership of background errors. 4. Shadow logging for async mandated that all background tasks must log a task started and task success/failure message with the original request ID for traceability. We have had 0 silent async failures since implementing mandatory error handlers.
Summary card.
Key takeaway for your interview: incident type, asynchronous exception masking and thread management error. Bad decision, using fire and forget async processing without adding an exceptionally parentheses block to handle failures. Impact: 50,000 customers missed order confirmations, and the issue was invisible to monitoring for 4 hours. Guardrail implemented, mandatory terminal error handlers for all futures, and automated task completion monitoring. If you do not join the future, you do not own the error.
The interview-winning answer template.
During a notification service update, I made the bad decision to move our email logic to an asynchronous block without implementing an error handler. When our SMTP credentials failed, the exceptions were swallowed by the background threads, and our monitoring stayed green while 50,000 customers were impacted. I resolved this by adding exceptionally parentheses blocks and implementing a dead letter queue. This taught me that async code requires explicit visibility. I have since enforced a policy where no background task can be deployed without mandatory logging and failure metrics, which has completely eliminated silent failures in our stack.
Follow-up 1. Why does the JVM swallow exceptions in a completable future by default?
Answer: a completable future is designed to be a pipeline. If an error occurs, it stores that exception internally so it can be handled later by a .get or join parentheses call. If you never call those methods or add an error handler, the exception has nowhere to go and dies with the future object.
Follow-up 2. What is structured concurrency, and how does it solve this problem?
Answer: structured concurrency treats multiple tasks as a single unit of work. If one subtask fails, the entire scope is notified, and all other tasks can be canceled. It ensures that background tasks have a clear parent who is responsible for catching and reporting their errors.
Follow-up 3. Curveball. What if you add error handling, but the logging thread itself is what's failing in the async block? How do you find the error then?
Answer: I would look at the standard error, stand error stream, and the hs_error_PID files. If the logging framework fails, for example, disk full, the JVM will usually attempt to print a panic message to the console. I also monitor the native thread count at the OS level to see if background threads are dying and being recreated in a loop.
Pro tip: the terminal chain rule.
In a senior Java support role, remember, an unhandled future is a lost exception. Every async chain must end with a terminal block, either a join, and exceptionally, or a handle. If your code is fire and forget, you are just firing a bullet into the dark and forgetting where it landed.
Category 17 wrap-up. The concurrency lesson.
We have navigated the dangerous waters of Java threading, from deadlocks that freeze the system to the chaos of thundering herds. The lesson is that concurrency requires absolute precision in lock ordering and resource isolation. But in a modern distributed architecture, the bottleneck often moves from internal threads to the pipes that connect our services. This leads us to Category 18, message queue and event-driven mistakes, where the challenges move from synchronous locks to asynchronous data streams.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, and system design. Required for your Java job interviews like Java Application Support Engineer jobs, AWS Java Developer jobs, Java Backend Developer jobs, Site Reliability Engineer SRE jobs, Java DevOps Engineer jobs, Java Kubernetes Developer jobs, Java Blockchain Developer jobs, Application Security Engineer jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem solving. Interview questions and answers where almost 80% of the people are failing to answer. System design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people. Also for your interviews, you people can download all 6 PDFs in a single zip file from below given links.
Category 18. Message queue and event-driven mistakes.
Modern Java applications are no longer isolated monoliths. They are parts of a vast, event-driven ecosystem powered by Kafka and RabbitMQ. This architectural shift introduces unique failure modes like poison pills, consumer lag, and idempotency errors. This category evaluates your ability to manage asynchronous state and backpressure. Interviewers want to see that you can troubleshoot a stalled pipeline and that you understand the critical difference between message delivery and message processing.
The event-driven challenge. Questions 83 to 86.
Be prepared to discuss these specific Kafka and message queue failures in your next interview. 83. Tell me about a time a poison pill message halted your entire processing pipeline. 84. Describe a situation where your Kafka consumer fell drastically behind and your initial fix failed. 85. Have you ever accidentally processed an event twice because your Java service was not idempotent? 86. Explain a mistake you made involving message ordering or partition key misconfigurations. Interviewers evaluate your mastery of distributed event processing and asynchronous resilience.
Explain a bad decision you made. Question 83. The poison pill.
Interviewer asks, tell me about a time a poison pill message halted your entire processing pipeline. How did you clear it? Incident type, asynchronous failure and serialization error. Interviewer insight, this question evaluates your pipeline resilience. A junior engineer tries to fix the bad message. A senior engineer builds a system that isolates the bad message. They want to see that you understand the danger of a consumer getting stuck in a retry loop and how you implemented a dead letter queue, DLQ, to maintain throughput.
The star story and reflection.
Here is the account of how one malformed JSON message paralyzed our data platform. Situation: we were managing a Java-based streaming platform that consumed customer activity events from Kafka and stored them in an Elasticsearch cluster. Task: my task was to ensure that the events were processed with sub-second latency to support a real-time marketing dashboard. Action: the bad decision plus why it happened. A developer pushed a change to an upstream producer that sent a message with a string in a field where our consumer expected a long. I made the bad decision to rely on the default Kafka error handler, which was configured to retry on error. I assumed any serialization error was transient and would resolve itself after a network flutter. Result: the impact. The consumer entered a death loop. It would pull the malformed message, fail to deserialize it, and then immediately pull the same message again. Within 10 minutes, the entire consumer group was stuck on that one offset. Data processing stopped for 4 hours, and our marketing dashboards went completely blank. We missed a critical promo window, resulting in an estimated $50,000 in lost conversion value. Reflection: I learned that in event-driven systems, retrying a permanent format error is a form of insanity. If a message is fundamentally broken, retrying it 1,000 times will not fix it. It will only hold your entire pipeline hostage. Fail fast on data format, retry slow on network state.
The investigation steps and root cause.
As the consumer lag spiked to millions of records, we performed a forensic trace. 1. Checked the consumer logs and identified a serialization exception repeating every 100 milliseconds. 2. Used the Kafka console consumer tool to peek at the specific offset and confirmed the user_ID field contained a malformed non-numeric string. 3. Identified that our Java application had zero catch and skip logic for deserialization errors inside the poll loop. 4. The root cause: poison pill message, where a permanent schema violation triggered a default retry policy that halted the entire partition's progress.
The technical resolution.
We cleared the pipeline and implemented an isolation strategy. 1. Immediately performed a manual offset reset to move the consumer past the bad message to restore the flow of healthy data. 2. Implemented a custom deserialization error handler in the Spring Kafka configuration to catch malformed messages at the entry point. 3. Configured a dead letter queue (DLQ) topic where malformed messages are automatically routed for manual inspection without stopping the consumer. 4. Added a validation interceptor that logs the raw byte payload of any failing message, making it 10 times easier to debug future producer errors.
What I changed forever.
I implemented these 4 structural guardrails for event-driven reliability. 1. The DLQ standard established a hard rule that no production consumer can be deployed without a configured dead letter queue and a login continue error handler. 2. Schema registry enforcement migrated all Kafka topics to Avro with a centralized schema registry to catch malformed messages at the producer level before they ever hit the wire. 3. Automated lag alerting configured a critical P1 alert that triggers if consumer lag on a single partition remains static, while CPU is high, identifying poison pills instantly. 4. Message sanity unit tests integrated a corrupt payload test suite into our CI pipeline that proves the consumer can survive garbage input without crashing. We have reduced our pipeline stall incidents by 100% since adopting schema registry enforcement.
Summary card.
Key takeaway for your interview: incident type, asynchronous failure and serialization error. Bad decision, relying on default retry on error policies for Kafka consumers, which allowed a single malformed message to stall the entire pipeline. Impact: 4-hour data processing blackout and $50,000 lost conversion value due to missing dashboards. Guardrail implemented: mandatory dead letter queues (DLQ) and schema registry enforcement to catch format errors at the source. A resilient consumer must be able to step over the garbage to get to the data.
The interview-winning answer template.
During a real-time data migration, I made the bad decision to use a default Kafka retry policy that did not distinguish between transient network errors and permanent format errors. One malformed JSON message caused our entire consumer group to enter a death loop, stalling our processing pipeline for 4 hours. I resolved this by manually skipping the offset and implementing a dead letter queue strategy. This taught me that event-driven systems require strict boundary validation. I have since enforced the use of a schema registry and mandatory error handling interceptors, ensuring that a single poison pill can never again stop our entire data flow.
Follow-up 1. What is the difference between a retry topic and a dead letter topic?
Answer: a retry topic is for transient failures, like a slow database, where we want to try again after a delay. A dead letter topic is a graveyard for permanent failures, like malformed JSON, where the message is moved aside for manual human audit.
Follow-up 2. How do you handle a message that is too large for Kafka to process? Is that also a poison pill?
Answer: yes, if it exceeds the max.request.size or message.max.bytes. The consumer will fail to even pull the message. We handle this by using claim check patterns. We store the large payload in S3 and only send a small pointer message through Kafka.
Follow-up 3. Curveball. What if you skip a message, but it turns out that message was a critical account deletion request? How do you ensure it is not lost forever?
Answer: this is why the DLQ must be actionable. We do not just dump messages there to die. We have a reprocessor tool that allows a support engineer to edit the malformed message in the DLQ and re-inject it into the main topic once the fix is applied.
Pro tip: the schema law.
In a senior Java support role, remember, code is ephemeral, but data is forever. If you do not use a schema registry to lock your message contracts, you are effectively letting every producer in your company write to your application's memory. Protect your consumer with a schema, or prepare for a poison pill.
Explain a bad decision you made. Question 84. The scaling trap.
Interviewer asks, describe a situation where your Kafka consumer fell drastically behind. Was your initial fix the right one? Incident type: performance bottleneck, and improper horizontal scaling. Interviewer insight. This question tests your understanding of asynchronous backpressure. Junior engineers just add more pods. A senior engineer looks at the processing time versus poll interval balance. They want to see that you understand the rebalance storm and how you optimize the Java consumer's internal loop to handle high throughput.
The star story and reflection.
Here is the account of how adding more pods made our Kafka lag even worse. Situation: we were managing a Java consumer that processed user rewards after a purchase. During a double points weekend, the consumer lag jumped from 0 to 2 million messages. Task: my task was to reduce the lag and ensure customers received their rewards within our 15-minute SLA. Action: the bad decision plus why it happened. I saw the lag and immediately assumed we did not have enough parallelism. I made the bad decision to double the number of consumer pods from 10 to 20 without checking the number of Kafka partitions. I was in panic mode and followed the basic scale-out intuition. Result: the impact. The fix failed spectacularly. Because our topic only had 10 partitions, the 10 new pods sat completely idle. More importantly, the extra pods triggered a rebalance storm that lasted 15 minutes, stopping all processing. The lag grew to 5 million messages, and we breached our reward SLA for 200,000 customers. Reflection: I learned that in Kafka, parallelism is capped by the number of partitions. Scaling the application beyond the partition count is just adding expensive spectators that slow down the cluster with constant rebalancing. Parallelism is a property of the topic, not just the application.
The investigation steps and root cause.
As the lag continued to climb, I performed a deep internal consumer audit. 1. Ran Kafka consumer groups describe and saw that each of the 10 partitions had only one consumer assigned, leaving 10 pods idle. 2. Analyzed the Java logs and found that each reward calculation was taking 800 milliseconds due to a slow DB query, far too slow for the message volume. 3. Identified that our max.poll.records was set to 500, meaning a single poll took 400 seconds to process, exceeding the max.poll.interval.ms limit. 4. The root cause: livelock via rebalancing, where the slow processing of large batches caused the consumer to miss heartbeats, triggering constant rebalances that stopped all throughput.
The technical resolution.
We optimized the consumer loop and stabilized the rebalancing logic. 1. Immediately reduced max.poll.records to 50 to ensure the processing loop finished well before the heartbeat timeout. 2. Increased the max.poll.interval.ms to 10 minutes to provide a larger safety buffer for slow database spikes. 3. Refactored the Java code to use an internal executor service, worker pool, to process messages in parallel within a single partition consumer. 4. Collaborated with the Kafka team to increase the partition count from 10 to 50, allowing our 20 pods to actually contribute to the work.
What I changed forever.
I implemented these 4 structural guardrails for consumer performance. 1. Partition-aware scaling established a rule that the max replica count in Kubernetes must always be less than or equal to the Kafka partition count. 2. Decoupled poll and process mandated that all high-throughput consumers must use an internal thread pool for processing to ensure the Kafka poll thread is never blocked. 3. Incremental rebalancing configured the cooperative sticky señor in our Java clients to minimize the impact of rebalancing during scaling events. 4. Throughput to partition baseline added a requirement that every new topic must be provisioned with 3 times the current peak partition count to allow for future horizontal scaling. We have reduced our consumer lag incidents by 80% since adopting the decoupled poll architecture.
Summary card.
Key takeaway for your interview: incident type, performance bottleneck and improper horizontal scaling. Bad decision, doubling consumer pods beyond the partition count, which triggered a rebalance storm and stopped all processing. Impact: SLA breach for 200,000 customers and a 5 million message backlog that took 6 hours to clear. Guardrail implemented, mandatory cooperative sticky rebalancing, and decoupled internal thread pools for all high-volume consumers. Scale your partitions before you scale your pods.
The interview-winning answer template.
During a major traffic surge, I made the bad decision to double our consumer pod count to fix a growing Kafka lag. However, I did not check the partition count. which was only 10. The extra pods caused a massive rebalance storm that completely stopped our processing and worsened the lag. I resolved this by tuning the poll intervals and increasing our partition count. This taught me that Kafka parallelism is a server-side constraint. I have since implemented partition-aware scaling policies and internal worker pools, which has made our event-driven services much more resilient to sudden spikes in volume.
Follow-up 1. What happens if a consumer pod crashes? How does Kafka handle that partition?
Answer: Kafka detects the missed heartbeat. After the session.timeout.ms expires, it triggers a rebalance. The partition that was assigned to the crashed pod is then moved to another healthy pod in the same consumer group to resume processing from the last committed offset.
Follow-up 2. What is consumer lag, and which metric do you monitor to find it?
Answer: consumer lag is the difference between the last produced offset and the last committed offset. I monitor the records lag max metric in Prometheus. If this number is increasing, it means the application is not processing messages as fast as they are being produced.
Follow-up 3. Curveball. What if the lag is 0 but the business reports that data is missing in the UI? What then?
Answer: that points to an idempotency or filter issue. I would check the consumer logs for dropped or filtered messages. It is possible the application is successfully committing the offset, but failing to save the result to the DB due to a logic bug. Lag only measures consumption, not successful business completion.
Pro tip, the rebalance rule.
In a senior Java support role, remember, rebalancing is the stop-the-world event of Kafka. Every time a pod joins or leaves, processing stops. Use cooperative sticky assignors and ensure your max.poll.interval.ms is at least 2 times your slowest processing time to prevent accidental rebalance cycles.
Explain a bad decision you made. Question 85. The duplicate payment.
Interviewer asks, have you ever accidentally processed an event twice because your Java service was not idempotent? What was the business impact? Incident type: data duplication and lack of idempotency. Interviewer insight: this question tests your understanding of at least once delivery semantics. In distributed systems, a message will eventually be delivered twice. A senior engineer explains how they moved from naive consumers to idempotent receivers, using deduplication tables and unique business keys to protect financial integrity.
The star story and reflection.
Here is the account of how a Kafka rebalance caused $50,000 in duplicate charges. Situation: we were managing a high-frequency Java service that processed refund requests from a Kafka topic and called a third-party payment gateway. Task: my task was to ensure each refund request was processed exactly once to maintain financial accuracy. Action: the bad decision plus why it happened. I made the bad decision to rely solely on Kafka's automatic offset commit and did not implement any internal deduplication logic. I assumed that since we were not seeing many rebalances, the risk of duplicate processing was negligible. I prioritized code simplicity over distributed safety. Result: the impact. During a network flicker, the Kafka cluster triggered a massive rebalance. A batch of 500 refund messages was processed by Node A, but the offset was not committed before Node A lost its heartbeat. Node B took over and reprocessed the same 500 messages. We double-charged the company $50,000 in refunds. Customer support was flooded with complaints, and we had to halt all payments for 5 hours to reconcile the logs. Reflection: I learned that exactly once is a myth unless you enforce it at the application layer. You cannot trust the broker to be your only guardrail. Your code must be resilient enough to see the same message twice and ignore it the second time. The network is unreliable. Your business logic must be certain.
The investigation steps and root cause.
As the finance team flagged the duplicate payouts, we performed a transaction audit. 1. Correlated the third-party transaction IDs and found 500 pairs of duplicate entries with different internal process IDs. 2. Checked the Kafka consumer logs and identified a rebalance in progress exception occurring between the process and commit steps. 3. Verified that the Java application had zero check-if-exists logic in the database before calling the external payment API. 4. The root cause: lack of application-level idempotency, where the consumer failed to handle a retry event from the broker, leading to side effects in an external system.
The technical resolution.
We implemented a deduplication pattern to stabilize the payment flow. 1. Created a processed underscore messages table in our SQL database to store the message key and timestamp for every successfully processed refund. 2. Refactored the Java code to wrap the check, process, and record steps in a single @transactional block. 3. Used a unique constraint on the message key column to ensure that a second attempt to record the same message would trigger a SQL conflict and fail safely. 4. Developed an automated reconciliation script to identify and reverse the $50,000 in duplicate payments by matching vendor logs with internal records.
What I changed forever.
I implemented these 4 structural guardrails for idempotent processing. 1. The inbox pattern standard established a hard rule that all event-driven consumers must use a deduplication table to track processed message IDs. 2. Business key mandate mandated that every producer must include a unique idempotency key in the message header, generated at the point of origin. 3. Manual offset commit policy switched all production consumers from auto-commit to manual acknowledge to give the application more control over when a message is truly done. 4. Distributed lock RIDIs implemented a 10-second RIDIs lock on the idempotency key to prevent 2 different consumer pods from processing the same message simultaneously during a rebalance. We have reduced our duplicate processing incidents to 0 since adopting the inbox pattern.
Summary card.
Key takeaway for your interview. Incident type, data duplication and lack of idempotency. Bad decision, relying on Kafka's auto-commit without implementing application-level deduplication logic. Impact, $50,000 in duplicate refunds and a 5-hour payment blackout for log reconciliation. Guardrail implemented, mandatory SQL inbox deduplication table, and RIDIs-based distributed locking for message keys. A senior engineer never assumes exactly wants delivery. They build it.
The interview-winning answer template.
During a Kafka rebalance, I made the bad decision to rely on the broker's auto-commit feature instead of building application-level idempotency. This resulted in 500 duplicate refund payments and a $50,000 financial discrepancy. I resolved this by implementing an inbox deduplication table and a manual commit policy. This taught me that in distributed systems, you must always code for the retry. I have since enforced a policy where every consumer must use unique business keys and transactional deduplication, which has completely eliminated double processing in our environment.
Follow-up 1. What is the inbox pattern and how does it relate to the outbox pattern?
Answer: the inbox pattern ensures a consumer does not process the same message twice, deduplication. The outbox pattern ensures a producer does not lose a message if the broker is down, reliability. Together, they ensure data consistency between different microservices.
Follow-up 2. How do you prevent the processed underscore messages table from growing too large and slowing down the DB?
Answer: I use a TTL or retention policy. Since most duplicates happen within seconds of the original message, I only need to keep the last 24 to 48 hours of IDs. I run a background cleanup task to prune old records, keeping the index small and fast.
Follow-up 3. Curveball. What if your checkIfExists query says the message is new, but a second thread is already halfway through processing it? How do you stop the race condition?
Answer: I use a distributed lock in RIDIs or a select for update in SQL on the message ID. This ensures only one thread can own the message processing at a time. If the second thread sees the lock is held, it waits or skips the message, preventing the race condition.
Pro tip: the side effect rule.
In a senior Java support role, remember, any operation with an external side effect, like charging a card or sending an email, must be idempotent. If you cannot undo the action easily, your code must be 100% sure it has not already done it.
Explain a bad decision you made. Question 86. The ordering out of sync.
Interviewer asks, explain a mistake involving message ordering or partition key misconfigurations. Incident type, message sequencing error and state inconsistency. Interviewer insight, this question reveals your understanding of semantic partitioning. Junior engineers think all partitions are equal. A senior engineer knows that related messages, like create order and cancel order, must go to the same partition to maintain sequence. They want to see how you troubleshoot race conditions in a parallel processing environment.
The star story and reflection.
Here is the account of how random partitioning corrupted our warehouse inventory. Situation: we were managing a Java microservice that updated warehouse inventory levels based on Kafka events from the sales and returns departments. Task: my task was to ensure that the stock levels in the database were perfectly synchronized with the real-time activity of our 500 warehouses. Action: the bad decision plus why it happened. I made the bad decision to use a null partition key for the inventory updates topic. I assumed that round-robin distribution would be better for load balancing across our 20 consumer pods. I did not realize that the sequence of stock in and stock out mattered more than even load distribution. Result: the impact. Related events for the same product arrived at different pods simultaneously. A delete stock out message was processed by pod A before the create stock in message reached pod B. This caused a negative inventory error in our database, which triggered an automated safety block on our checkout site. We lost 3 hours of sales for 50 popular products, costing the company $40,000. Reflection: I learned that in event-driven systems, parallelism is a trade-off with order. If you have stateful data, you must sacrifice perfectly even load balancing to ensure that all events for a specific business entity are processed by the same thread in the correct order. Ordering is the foundation of consistency in a distributed stream.
The investigation steps and root cause.
As the warehouse team reported impossible stock levels, we performed a trace. 1. Isolated a single product underscore ID and used Kafka runclass.sh Kafka.tools.get offset shell to find its events across partitions. 2. Discovered that the add stock event was in partition 1, while the remove stock event was in partition 5. 3. Confirmed that because the events were in different partitions, they were processed by different pods with no shared wait or lock logic. 4. The root cause: incorrect partition key strategy, where a null key allowed sequential business events to be processed in parallel, creating a race condition and data corruption.
The technical resolution.
We resequenced the pipeline and repaired the stateful data. 1. Immediately modified the producer configuration to use the product underscore ID as the partition key, ensuring all updates for a specific item always hit the same partition. 2. Performed a consumer drain where we paused processing for 10 minutes to allow the repartitioned data to settle in the brokers. 3. Wrote a Java utility that performed a full sync between the warehouse mainframe and our database to correct the negative inventory counts. 4. Implemented an optimistic locking version check in our Java JPA entities to detect and reject out-of-order updates at the database level.
What I changed forever.
I implemented these 4 structural guardrails for message ordering safety. 1. The entity key standard established a rule that all stateful topics must use a high cardinality business key, like product underscore ID as the partition key. 2. Producer linter audit added a static analysis check that alerts if a Kafka send parentheses call is made with a null key for any topic tagged as sensitive. 3. Stateful sequence checks integrated a sequence ID in our message schema. The Java consumer now logs a critical error if it receives a version 5 message before version 4. 4. Throughput balance partitioning redesigned our partition count from 20 to 100 to ensure that even with entity key partitioning, the load remains well distributed across the cluster. We have reduced our out-of-order data errors by 100% since adopting entity key partitioning.
Summary card.
Key takeaway for your interview: incident type, message sequencing error and state inconsistency. Bad decision, using a null partition key for inventory events, leading to out-of-order processing across different consumer pods. Impact: negative inventory counts and a 3-hour safety block on 50 popular products, costing $40,000. Guardrail implemented: mandatory entity key partitioning and optimistic locking in the JPA entity layer. Load balancing is useless if it destroys the meaning of your data.
The interview-winning answer template.
During a warehouse integration project, I made the bad decision to use round-robin partitioning for our inventory topic to maximize load balancing. This caused stock-out events to be processed before stock-in events for the same product, leading to negative inventory errors and a $40,000 sales loss. I resolved this by switching to product ID partitioning and implementing optimistic locking in our Java code. This taught me that ordering is non-negotiable for stateful data. I have since enforced a policy where all sequence-sensitive topics must use semantic partition keys, which has completely eliminated race conditions in our pipelines.
Follow-up 1. If you use product ID as the key, but one specific product is 1,000 times more popular than others, does not that create a hot partition problem?
Answer: yes. That is the risk of key skew. If one partition is overwhelmed, we look at subpartitioning. We might combine product ID with region ID to split the load further, or use a local cache to handle the most popular items before they even hit the Kafka stream.
Follow-up 2. Can Kafka guarantee global ordering across all partitions in a topic?
Answer: no. Kafka only guarantees ordering within a single partition. If you need global ordering for the entire topic, you are limited to a single partition, which removes your ability to scale horizontally. In senior support, we always aim for per-key ordering instead of global ordering.
Follow-up 3. Curveball. What happens to the ordering if a Kafka partition fails over to a secondary broker? Is the sequence preserved?
Answer: yes, provided the producer is configured with ax equals all and max dot in dot flight dot, requests dot per dot connection equals 1, or idempotent producer enabled. This ensures the leader has fully replicated the sequence before acknowledging, maintaining the order even during a failover.
Pro tip: the sequencing law.
In a senior Java support role, remember, parallel processing of sequential state is a bug, not a feature. If your events have a previous and a next relationship, they must never leave the same thread. Always partition by the entity ID that owns the state.
Category 18 wrap-up, the event-driven lesson.
We have seen how asynchronous systems like Kafka require a shift in thinking, from managing thread locks to managing data sequence and idempotency. The lesson is that in a distributed world, you must design for the retry and the poison pill. But technical resilience is only half the battle. In regulated environments like banking and fintech, how you manage the change itself is just as critical. This leads us to Category 19, Change Management, where we examine the risks of process shortcuts and underestimated impacts.
Category 19, Change Management.
Change management is the governance layer of production support. In a senior role, you aren't just an engineer, you are a risk assessor. This category evaluates your awareness of ITIL processes, change advisory boards, CAB, and the importance of full-spectrum impact analysis. Interviewers want to see that you respect the guardrails of the organization and that you understand why a 5-minute technical fix requires a 50-minute risk assessment.
The Change Management Challenge, questions 87 to 90.
Be prepared to discuss these governance and risk assessment failures in your next interview. 87. Tell me about a time you deployed a change without a full impact analysis. 88. Describe a change that required an emergency rollback because technical risks were underestimated. 89. Describe a mistake where a critical release window was missed due to your decision. 90. Explain a situation where a change rollback plan failed and left the system in a broken state. Interviewers evaluate your operational discipline and your ability to balance speed with safety.
Explain a bad decision you made. Question 87. The partial impact analysis.
Interviewer asks, tell me about a time you deployed a change without full impact analysis. Incident type, change management failure and dependency oversight. Interviewer insight, this question tests your silo thinking. In modern microservices, no change is isolated. A senior engineer explains how they missed a downstream dependency and how they implemented cross-team impact audits to ensure that a fix in one service does not become a failure in another.
The star story and reflection.
Here is the account of how a minor connection pool change crashed our internal auditing tool. Situation: we were optimizing our Java-based order service to handle higher concurrency. I needed to increase the Hikari CP connection pool from 20 to 50. Task: my task was to update the application configuration and perform a rolling restart to ensure the database could handle the increased throughput. Action: the bad decision plus why it happened. I performed the impact analysis only on the order service and the primary database. I made the bad decision to skip checking our internal audit tool, which shared the same database user and connection quota. I assumed that because the audit tool had low traffic, it would not be affected by a pool increase in the main app. Result: the impact. When the order service scaled up, it consumed 100% of the available database connections. The audit tool was completely starved and failed to record any compliance data for 4 hours. We failed our daily regulatory audit, resulting in a formal notice of non-compliance and a 48-hour emergency data reconstruction project. Reflection: I learned that a shared resource is a shared risk. If you only analyze the impact on the service you are fixing, you are ignoring half of the production environment. Every change must be audited against the total resource quota of the system. An impact analysis is only as good as its scope.
The investigation steps and root cause.
As the compliance alerts fired, we audited the database connection limits. 1. Ran show max_connections and confirmed the database limit was set to 100. 2. Calculated the SUM of pools across all services and found that the order service, 50, plus the reporting service, 40, and the audit tool, 15, exceeded the 100 limit. 3. Identified that the audit tool was throwing connection acquisition timeout because the main app had successfully claimed all available slots first. 4. The root cause: incomplete impact analysis where a resource change was made without calculating the cumulative effect on a shared database cluster.
The technical resolution.
We restored the connection balance and hardened the quota management. 1. Immediately reduce the order service pool back to 30 to release enough connections for the audit tool to resume operations. 2. Collaborated with the DBA team to increase the max_connections at the database level to 200, providing enough headroom for all services. 3. Implemented connection borrowing timeouts in the Java application to ensure that no single thread could hold a database connection hostage for more than 5 seconds. 4. Developed a resource quota map that documents the max pool size of every application connecting to the primary database cluster.
What I changed forever.
I implemented these 4 structural guardrails for change impact analysis. 1. Mandatory resource reconciliation. Established a rule that any change to a resource limiting setting, CPU, RAM, or DB connections, must include a cumulative impact calculation sheet. 2. Cross-functional peer review mandated that changes to shared infrastructure, like a database user, must be reviewed by the leads of all teams using that resource. 3. Quota-aware monitoring. Configured an alert that triggers if the SUM of configured pools reaches 90% of the available database connections, catching the error before the deployment. 4. Change management linter. Integrated a tool in our Jira workflow that forces engineers to answer: does this service share a DB, cache, or queue with others? Before a CAB request is generated. We have reduced our side effect outages to 0 since adopting the reconciliation policy.
Summary card.
Key takeaway for your interview: incident type, change management failure and dependency oversight. Bad decision, increasing a microservice connection pool without calculating the cumulative impact on shared database limits. Impact: total starvation of a secondary compliance tool and a failed regulatory audit for 4 hours. Guardrail implemented: mandatory cumulative impact calculation for all shared resource changes. When you tune one service, you are affecting the entire ecosystem.
The interview-winning answer template.
During a performance optimization project, I made the bad decision to increase our main service's connection pool without checking the impact on other tools sharing the same database. This exhausted our DB connection quota and crashed our internal audit tool for 4 hours, leading to a compliance breach. I resolved this by rebalancing our quotas and increasing the DB capacity. This taught me that impact analysis must be cluster-wide, not just service-wide. I have since implemented a mandatory resource reconciliation policy and cross-team reviews for all shared resource changes, which has completely eliminated side effect outages in our fleet.
Follow-up 1. How do you perform a full impact analysis in a complex architecture with 100+ microservices?
Answer: I use service mesh maps and distributed tracing, like Jaeger. By looking at the dependency graph, I can see exactly what our service talks to and what talks to it. I also check our infrastructure as code repository to see which other services share the same VPC subnets or database endpoints.
Follow-up 2. If the business demands an urgent fix and skips the impact analysis, how do you handle the risk?
Answer: I use the minimum viable triage. I perform a 10-minute audit of the most critical dependencies, DB, MQ, and security. I then record a residual risk in the incident ticket. I do not stop the fix, but I ensure that if it fails, the team knows exactly where to look for the side effects.
Follow-up 3. Curveball. What if you do the analysis, it says it is safe, but it still breaks a downstream service? What went wrong?
Answer: that is usually a version-specific conflict or an undocumented dependency. I would use that incident to update our service metadata and automated topology map. I treat every unexpected breakage as a failure of our documentation that must be corrected.
Pro tip, the shared resource rule.
In a senior Java support role, remember, there is no such thing as a local change in a distributed system. Every time you change a thread count, a pool size, or a memory limit, you are consuming a finite budget of the host or the network. Always ask, who else is eating from this same plate?
Explain a bad decision you made. Question 88. The underestimated security risk.
Interviewer asks, describe a change that required emergency rollback because risks were underestimated. Incident type: security misconfiguration and backward compatibility failure. Interviewer insight: this question evaluates your risk intuition. Some changes look standard but carry huge risks for legacy clients. A senior engineer explains how they failed to account for client-side limitations and how they moved to phased feature rollouts to ensure a safety-first approach to security upgrades.
The star story and reflection.
Here is the account of how a security hardening project became a production disaster. Situation: we were upgrading our Java API security layer to enforce TLS 1.3 for all incoming connections to comply with new industry standards. Task: my task was to update the load balancer configuration and the Java application's SSL properties to reject all older, insecure protocols, TLS 1.0 and 1.1. Action: the bad decision plus why it happened. I made the bad decision to implement this change globally across the entire cluster during a single midnight window. I assumed that because 99% of our traffic was modern, the 1% using older clients would just upgrade or was negligible. I underestimated the number of legacy Java 7 clients used by our internal warehouse scanners. Result: the impact. At 6 a.m., the warehouse operations came to a halt. 500 legacy scanners could not connect to the API, preventing any shipping labels from being printed. We had to perform an emergency rollback of the security policy within 30 minutes to resume business operations. The underestimated risk caused a 4-hour shipping delay for 50,000 orders. Reflection: I learned that security compliance is useless if it causes a denial of service for your own business. You cannot force an upgrade on legacy clients overnight. You must provide a graceful migration path and perform a full inventory of every client type. Reliability is the prerequisite for security.
The investigation steps and root cause.
As the warehouse team reported connection-terminated errors, I performed a protocol audit. 1. Ran open SSLS_client and confirmed the API was now strictly rejecting anything below TLS 1.2. 2. Checked the load balancer logs and identified thousands of handshake failures originating from the internal warehouse subnet. 3. Verified the scanner hardware specs and found they were running an embedded Java 7 runtime that did not support TLS 1.2 or 1.3 by default. 4. The root cause: unfiltered change rollout where a security policy was applied without auditing the protocol capabilities of internal legacy IoT devices.
The technical resolution.
We rolled back the change and implemented a tiered security model. 1. Immediately reverted the load balancer to allow TLS 1.1 for internal subnets only, while maintaining TLS 1.3 for the public internet. 2. Implemented a protocol dashboard that uses ELK logs to count the percentage of traffic using each SSL version by IP address. 3. Launched a coordinated project with the warehouse team to patch the Java 7 scanners with a modern security provider, like Bouncy Castle, to support TLS 1.2. 4. Added a compatibility interceptor in the Java API that logs a high-priority warning if a request is made using a deprecated protocol, allowing us to identify clients before we cut them off.
What I changed forever.
I implemented these 4 structural guardrails for high-risk configuration changes. 1. Phased protocol deprecation. Established a rule that no security protocol can be disabled without a 60-day observation period where all legacy traffic is logged and identified. 2. Client type inventory. Mandated that every major change must include a client impact report using user agent and IP metadata from our logs. 3. Environment-specific security zones. Implemented separate security policies for internal IoT traffic versus external web traffic to allow for staggered upgrades. 4. Automated compatibility testing. Integrated a legacy client simulator into our staging environment that attempts to connect using old SSL versions to prove the rollback plan works. We successfully migrated to TLS 1.3 6 months later, with 0 business disruption.
Summary card.
Key takeaway for your interview. Incident type: security misconfiguration and backward compatibility failure. Bad decision: enforcing TLS 1.3 globally without auditing the capabilities of legacy internal warehouse scanners. Impact: total shipping blackout for 4 hours and 50,000 delayed orders due to SSL handshake failures. Guardrail implemented: phased protocol deprecation and mandatory client impact reports for all security changes. Do not burn the bridge before ensuring everyone has crossed it.
The interview-winning answer template.
During a security hardening project, I made the bad decision to disable old SSL protocols globally to meet compliance standards. I underestimated the impact on our internal legacy scanners, which were unable to connect using modern TLS versions, causing a 4-hour shipping outage. I resolved this by performing an emergency rollback and then implementing a tiered security model. This taught me that risk assessment must include a full inventory of all client types. I have since enforced a phased deprecation policy that uses data to identify at-risk clients months before a change is applied, which has completely eliminated breaking security changes in our org.
Follow-up 1. If you find that 0.1% of users are on a truly ancient browser, do you delay a critical security fix forever?
Answer: no. I follow the notify and nudge strategy. We show those users a banner saying their browser is unsupported. After 30 days, we move them to a legacy gateway that is isolated from the rest of the app. We prioritize the security of the 99.9% while providing a clear path for the remaining few.
Follow-up 2. How do you perform a safe rollback of an SSL change without dropping active connections?
Answer: I use a graceful reload on the load balancer, like Nginx or HA proxy. This allows the process to start accepting new connections using the old protocol while letting existing TLS 1.3 connections finish normally. This ensures 0 connection resets during the rollback.
Follow-up 3. Curveball. What if the security fix was to revoke a compromised certificate? You cannot delay that. How do you handle it?
Answer: in a compromise, security beats availability. I would revoke immediately but have the support team on a high-priority bridge to manually assist critical partners who fail to connect. I would use preemptive communication to tell everyone to refresh their trust stores 10 minutes before the revocation happens.
Pro tip: the traffic audit rule.
In a senior Java support role, remember, never change a protocol you have not measured. Before you disable a feature or a version, you should have a dashboard showing exactly how many sessions are currently using it. If the number is not 0, your change is a breaking change.
Explain a bad decision you made. Question 89. The hesitation outage.
Interviewer asks, describe a mistake where a release window was missed due to your decision. Incident type: process overanalysis and operational paralysis. Interviewer insight: this question evaluates your decision-making velocity. Sometimes, perfect is the enemy of good. A senior engineer discusses how they became paralyzed by analysis paralysis and how they learned to use risk scoring to make fast, confident decisions in high-pressure windows.
The star story and reflection.
Here is the account of how a simple question delayed a critical fix by 24 hours. Situation: we had a memory leak in production that required us to restart our Java nodes every 12 hours. A fix had been developed and verified in staging. Task. My task was to approve the release window for 11 p.m. to deploy the fix and stop the manual restarts. Action. The bad decision plus why it happened. At 10:45 p.m., I noticed a tiny 2% difference in the code coverage report for the new fix. I made the bad decision to hold the release and demand a rerun of the full integration suite. I was afraid of being blamed for a regression and chose total certainty over operational necessity. Result, the impact. We missed our 11 p.m. release window. At 3 a.m., the application hit its memory limit and crashed. Because the fix was not deployed, the automated restart failed, causing a 3-hour blackout during the Asian market open. My hesitation turned a scheduled fix into an unscheduled disaster. Reflection. I learned that in production support, zero risk does not exist. Your choice is always between two different risks. Delaying a known fix for a minor discrepancy is a choice to keep the current failure alive for another day. Indecision is a decision to let the problem continue.
The investigation steps and root cause.
During the postmortem, we analyzed the decision-making bottleneck. 1. Confirmed that the 2% coverage difference was in an unreachable test helper class and had zero impact on the fix logic. 2. Identified that I had spent 30 minutes debating the metric in Slack while the release window was closing. 3. Found that our change management policy did not have a clear definition of minimum acceptable confidence for emergency fixes. 4. The root cause. Analysis paralysis, where a lack of risk prioritization framework allowed a non-critical metric to block a critical stability fix.
The technical resolution.
We stabilized the cluster and revamped our decision framework. 1. Immediately deployed the fix during an out-of-cycle emergency window the following morning to stabilize the JVM memory. 2. Implemented a risk matrix that compares the risk of release against the risk of non-release, for example, current crash frequency. 3. Added a fast-track approval for stability fixes that have been verified in UAT, bypassing non-functional metric checks like code coverage. 4. Configured the JVM with -XX:+ exit on out-of-memory error as a temporary safety net to ensure cleaner automated restarts if a fix is ever delayed again.
What I changed forever.
I implemented these 4 structural guardrails for release decision-making. 1. The threshold of confidence policy established a rule that if a fix solves a P1/P2 issue and has 90% UAT success, it must be deployed within the next window. 2. Decision time boxing mandated that for any release blocking question, a go or no-go decision must be made within 10 minutes or it is escalated to the director level. 3. Automated risk scoring integrated a script into our CI/CD that calculates a risk score based on changed lines, test results, and system criticality. 4. Post-release dark launch standard enforced a standard of using feature flags for all fixes, allowing us to deploy with less hesitation because we can toggle off instantly. We reduced our missed window rate by 90% since implementing decision time boxing.
Summary card.
Key takeaway for your interview. Incident type, process overanalysis and operational paralysis. Bad decision, delaying a critical memory leak fix due to a 2% discrepancy in code coverage reports. Impact, 3-hour total blackout for Asian markets because the known issue was allowed to crash the system one more time. Guardrail implemented, mandatory risk scoring matrix and 10-minute decision time boxing for release windows. A senior engineer manages risk. They do not seek to eliminate it entirely.
The interview winning answer template.
During a memory leak crisis, I made the bad decision to hold a critical fix because of a minor code coverage discrepancy. My hesitation caused us to miss our release window, leading to a 3-hour blackout when the system inevitably crashed again. I resolved this by leading the recovery and then building a risk scoring matrix for our team. This taught me that in production support, you must weigh the risk of a regression against the certainty of a current failure. I have since implemented 10-minute decision time boxing for all release windows, which has made our incident response significantly more decisive and reliable.
Follow-up 1. How do you justify a high-risk release to a non-technical stakeholder?
Answer: I use the cost of inaction argument. I explain that doing nothing has a 100% chance of causing an outage, like our memory leak, while deploying has a 5% chance of a regression. I present the math of availability. Most stakeholders respect a data-driven risk assessment.
Follow-up 2. What is the benefit of a feature flag in this situation?
Answer: it decouples deployment from activation. We could have deployed the code during the window but kept the fix off. Then, we could have toggled it on during a lower traffic window. It provides an instant rollback without a full deployment cycle.
Follow-up 3. Curveball. What if your manager is the one who is hesitating? How do you push the release through?
Answer: I provide a mitigation plan. I say, I understand the concern about the metric. To mitigate the risk, I will stay on a bridge for 2 hours after the release to monitor the logs personally. By taking personal accountability for the safety net, I often help the manager overcome their hesitation.
Pro tip: the good enough law.
In a senior Java support role, remember, do not let the search for the perfect fix become the cause of the next outage. If a fix is verified to solve the P1, ship it. You can always optimize the code coverage in a P3 follow-up ticket later.
Explain a bad decision you made. Question 90. The one-way rollback.
Interviewer asks, explain a change rollback plan that failed. Incident type: data incompatibility and failed disaster recovery. Interviewer insight: this question reveals your operational foresight. A senior engineer knows that a rollback is not just about binary code. It is about stateful data. They want to see how you moved from hoping it reverts to verified reversibility for every production change.
The star story and reflection.
Here is the account of a data migration that could not be undone. Situation: we were upgrading a Java service that processed customer rewards. We were migrating the reward data from a legacy XML format to a new JSON format in the database. Task: my task was to run a transform and update script and then deploy the new version of the code that expected JSON. Action: the bad decision plus why it happened. I made the bad decision to perform an in-place transformation of the existing records. I assumed that since I had a backup, a rollback would be easy. I skipped creating a rollback script that converted JSON back to XML because I thought the new code was too simple to fail. Result: the impact. The new code had a critical bug in the redemption logic. When I tried to roll back to the old code, it crashed immediately because it could not parse the new JSON format in the database. My rollback plan, restoring from backup, failed because 10,000 new transactions had happened in JSON format that would be lost if I used the old backup. The system was stuck in a forward-only state for 6 hours. Reflection: I learned that a rollback plan is not a backup. It is a reverse transformation. If you change the state of the data, you must have a tested way to revert that state without losing new business activity. Data is the only thing that does not roll back with the code.
The investigation steps and root cause.
As the old Java version failed to start, I performed a data layer audit. 1. Identified serialization exception across all old application logs. 2. Verified that the database rewards column was now populated with JSON blobs which the legacy JAX parser could not interpret. 3. Confirmed that the point-in-time backup was now 2 hours stale and would result in massive data loss if applied. 4. The root cause: irreversible data transformation, where a breaking schema change was performed without a corresponding reverse migration script.
The technical resolution.
We performed an emergency forward fix and stabilized the data. 1. Instead of rolling back, we stayed on a bridge for 6 hours to develop and deploy an emergency hotfix for the JSON redemption logic. 2. Wrote a bridge parser for the old application as a temporary measure to allow it to read both XML and JSON formats simultaneously. 3. Implemented a shadow table strategy for the next migration, where data is written to a new column while keeping the old one intact for 48 hours. 4. Used a data correction batch to fix the 10,000 JSON records that were partially corrupted during the outage window.
What I changed forever.
I implemented these 4 structural guardrails for data change safety. 1. Mandatory reverse migration tests. Established a rule that no data changing script can be run without a verified undo script that has been tested against production scale data. 2. The expand and contract pattern mandated that all schema changes must follow a 3-release cycle. 1. Add new column. 2. Write to both. 3. Remove old column. 3. Stateless rollback policy. Enforced a requirement that for any stateful change, the rollback plan must include a data replay strategy to recover transactions from logs. 4. automated schema validation, added a check in the deployment pipeline that verifies the code version against the database format and prevents a mismatch at boot time. We have reduced our one-way deployment risks to zero since adopting the expand and contract pattern.
Summary card.
Key takeaway for your interview: incident type, data incompatibility and failed disaster recovery. Bad decision, performing an in-place XML to JSON data transformation without a reverse migration script. Impact, 6-hour system hang where the system could not be rolled back without massive data loss. Guardrail implemented, mandatory expand and contract schema migration pattern, and tested reverse migration scripts. A rollback plan that loses data is just a different kind of outage.
The interview-winning answer template.
During a data migration project, I made the bad decision to transform our database records in place without a reverse migration script. When the new code failed, we could not roll back to the old version because the data was no longer in a compatible format. This left us in an emergency state for 6 hours. I resolved this by performing an emergency forward fix. This taught me that rollbacks are a data problem, not just a code problem. I have since enforced the expand and contract pattern and mandatory reverse migration testing, ensuring we always have a safe, data-consistent path back to a stable state.
Follow-up 1. What is the expand and contract pattern, and why is it safer?
Answer: it decouples the database change from the application change. You add the new field first, expand, then update the code to use it, and only much later remove the old field, contract. This ensures that if you roll back the code, the old field is still there and valid.
Follow-up 2. How do you handle data consistency if you are writing to 2 columns simultaneously during a migration?
Answer: I use a dual write logic in the Java service layer, wrapped in a single database transaction. If either write fails, the entire operation rolls back. I also use a background comparison job to find and fix any discrepancies between the old and new columns.
Follow-up 3. Curveball. What if the migration script itself is what's causing the DB to be slow during the migration? Do you stop it?
Answer: yes. If the migration script is saturating I/O or holding long locks, I kill the PID and move to a throttled migration approach. I rewrite the script to process only 1,000 rows at a time, with a 1-second sleep between batches to let the business traffic through.
Pro tip: the data reversibility law.
In a senior Java support role, remember, you do not own the rollback until you have tested the reverse. Never approve a DML or DDL change unless you have a script that can mathematically and logically undo that change. Data is state, and state is permanent.
Category 19 Wrap-up, the governance lesson.
We have explored the critical importance of change management, from the risks of uncoordinated schema updates to the paralysis of analysis during a crisis. The lesson is that professional support requires a balance of speed and audited safety. But even the most compliant change process cannot save a system that has physically run out of room. This leads us into Category 20, Capacity Planning, where we examine the failures of foresight that occur when growth outpaces infrastructure.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, and system design. Required for your Java job interviews like Java Application Support Engineer jobs, AWS Java Developer jobs, Java Backend Developer jobs, Site Reliability Engineer SRE jobs, Java DevOps Engineer jobs, Java Kubernetes Developer jobs, Java Blockchain Developer jobs, Application Security Engineer jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem solving, interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people. Also for your interviews, you people can download all 6 PDFs in a single zip file from below given links.
Category 19 Wrap-Up, the governance lesson.
We have explored the critical importance of change management, from the risks of uncoordinated schema updates to the paralysis of analysis during a crisis. The lesson is that professional support requires a balance of speed and audited safety, but even the most compliant change process cannot save a system that has physically run out of room. This leads us into Category 20, Capacity Planning, where we examine the failures of foresight that occur when growth outpaces infrastructure.
Category 20 Capacity Planning.
In a senior Java support role, you must be a system futurist. You need to predict where the next bottleneck will appear before the traffic arrives. This category evaluates your infrastructure thinking and your ability to manage physical constraints like disk, memory, and connection limits. Interviewers want to see that you move beyond reactive scaling to proactive provisioning, ensuring the application always has the resources it needs to breathe.
The Capacity Challenge, questions 91 to 93.
Be prepared to discuss these failures of infrastructure foresight in your next interview. 91. Tell me about a time when insufficient capacity planning caused a major production outage. 92. Describe a mistake you made involving disk space, memory limits, or database connection caps. 93. Describe a situation where you underestimated a traffic spike and the system failed to scale. Interviewers, evaluate your ability to plan for the worst-case growth scenario.
Explain a bad decision you made. Question 91. The batch overrun.
Interviewer asks, tell me about a time insufficient capacity planning caused an outage. Incident type, capacity exhaustion and batch processing failure. Interviewer insight, this question tests your resource forecasting. As data grows, linear processes often become exponential problems. A senior engineer explains how they failed to model data growth and how they moved to parallelized processing and resource quota alerts to ensure the system scales with the business.
The star story and reflection.
Here is the account of how a successful sales quarter crashed our midnight batch processing. Situation: we were managing a Java-based reconciliation engine that processed all daily transactions at midnight. The job was designed to run on a single large JVM node with a 16 gigabyte heap. Task: my task was to ensure the batch finished by 4 a.m. to allow the reporting team to generate the daily morning financial statements. Action: the bad decision plus why it happened. I made the bad decision to ignore the 10% month-over-month growth in transaction volume. I assumed that our vertical scaling, adding more RAM, would last us for at least a year. I skipped the throughput modeling exercise because the batch was currently finishing in 2 hours. Result: the impact. During the holiday peak, the transaction volume tripled. The single-threaded Java batch could not keep up. The JVM began suffering from GC thrashing as it struggled to hold 5 million records in memory. The batch ran for 8 hours, crashing at 6 a.m. with an out-of-memory error. We missed our reporting window for the entire European market, resulting in a P1 financial visibility incident. Reflection: I learned that vertical scaling has a hard ceiling. If your processing time is linked to data volume on a single node, you aren't scaling. You are just waiting for the data to overwhelm the hardware. You must plan for horizontal parallelism before you hit the limit. Infrastructure should be sized for the peak of the peak, not the average of the month.
The investigation steps and root cause.
As the batch failed to terminate, I performed a resource exhaustion audit. 1. Analyzed the GC logs and saw that full GC events were happening every 30 seconds, reclaiming less than 5% of the heap. 2. Ran JMap histo and identified that the transaction object count had exceeded the capacity of our fixed-size internal buffer. 3. Confirmed that the disk I/O was saturated because the database was struggling to serve the 5 million records in a single cursor window. 4. The root cause: in elastic architecture, where a monolithic batch process hit a physical memory wall, because it was not designed to partition data or scale across multiple nodes.
The technical resolution.
We restored the financial flow and re-architected the batch logic. 1. Immediately increased the JVM heap to 32 gigabytes and used the G1GC algorithm to provide enough room to finish the emergency rerun. 2. Refactored the Java code to use Spring Batch partitioning, allowing us to split the 5 million records into 10 independent chunks. 3. Migrated the job to run on a Kubernetes job cluster, where we can spin up 10 parallel worker pods to process chunks simultaneously. 4. Implemented streaming readers to ensure that only 1,000 records are held in the JVM memory at any given time, regardless of the total data volume.
What I changed forever.
I implemented these 4 structural guardrails for long-term capacity management. 1. The 80% trigger established a rule that if a process ever consumes 80% of its allocated resources, a capacity expansion ticket is automatically generated for the next sprint. 2. Mandatory load projection mandated that every new feature release must include a resource forecast showing expected CPU and RAM usage at 2 times and 5 times current traffic. 3. Horizontal first standard established an architectural standard that no new processing job can be single-threaded. All work must be designed for partitioning from day one. 4. Automated throughput alerting configured an alert that triggers if a batch job's remaining time is projected to exceed the SLA window based on its current processing rate. We reduced our batch processing time by 75% while handling 3 times more data.
Summary card.
Key takeaway for your interview: incident type, capacity exhaustion and batch processing failure. Bad decision, ignoring incremental data growth and relying on vertical scaling for a monolithic Java batch job. Impact, out-of-memory error during peak holiday window, missing financial reporting SLAs for an entire region. Guardrail implemented, transition to Spring Batch partitioning, and established mandatory 5 times traffic resource forecasting. Do not scale your RAM, scale your architecture.
The interview-winning answer template.
During a period of rapid business growth, I made the bad decision to ignore the steady increase in our batch processing volume, assuming our single-node vertical scaling would be enough. During a holiday peak, the data volume tripled and crashed our reconciliation engine, causing us to miss our financial reporting SLA. I resolved this by re-architecting the system using Spring Batch partitioning across a Kubernetes cluster. This taught me that vertical scaling is a temporary patch. I have since enforced a horizontal first design standard and mandatory load projections, ensuring our systems are ready for 5 times traffic surges at all times.
Follow-up 1. How do you perform load projection if you do not have historical data for new feature?
Answer: I use stress testing to failure. We run the new feature in a performance environment and gradually increase traffic until the JVM crashes or the latency breaches the SLA. This gives us the resource per transaction cost, which we use to calculate the capacity needed for the target launch volume.
Follow-up 2. What is the risk of over-provisioning infrastructure just to be safe?
Answer: the risk is cloud waste and financial inefficiency. A senior engineer does not just ask for infinite resources. We aim for just-in-time capacity. I use auto-scaling and spot instances to ensure we have the power for peaks without paying for idle hardware during low-traffic windows.
Follow-up 3. Curveball. What if the database is the bottleneck and you cannot scale it horizontally? How do you solve the capacity issue then?
Answer: I look at read offloading and caching. I move all non-critical scans to read replicas. If the primary writer is still hit, I implement write queuing via Kafka to flatten the spikes and allow the database to process transactions at a steady, sustainable rate rather than being crushed by a burst.
Pro tip: the data wall law.
In a senior Java support role, remember, every system has a data wall. Your job is to find that wall through performance testing before the business finds it through an outage. If you do not know the exact transaction count that will crash your app, you have not finished your capacity plan.
Explain a bad decision you made. Question 92. The socket leak.
Interviewer asks, describe a mistake involving disk space, memory, or connection limits. Incident type: OS resource violation and file descriptor leak. Interviewer insight: this question reveals your kernel-level knowledge. In Linux, everything is a file. A Java app can crash not because the JVM is full, but because the OS has run out of file descriptors. A senior engineer explains how they mismanaged socket closures and how they implemented system limit monitoring to prevent invisible resource crashes.
The star story and reflection.
Here is the account of how too many open connections brought down our API gateway. Situation: we were running a Java Netty-based API gateway that handled 5,000 concurrent WebSocket connections for a real-time betting app. Task: my task was to ensure the gateway remained stable as we scaled the number of concurrent users from 5,000 to 20,000. Action: the bad decision plus why it happened. I focused entirely on the JVM heap and CPU limits. I made the bad decision to leave the Linux ulimit open files at its default value of 1024. I assumed that since we had auto-scaling pods, Kubernetes would just spin up new nodes if the current one was overwhelmed. Result: the impact. When user traffic spiked to 5,000, each pod hit the 1024 file descriptor limit. New users were rejected with java.eo.io exception, too many open files. Even worse, the pods could not write to their own logs or health check files because the OS refused to open new file handles. The entire cluster entered a zombie state for 60 minutes, costing $100,000 in lost bets during a major game. Reflection: I learned that internal Java health is irrelevant if the external OS limits are reached. A senior engineer must treat the Linux kernel limits, file descriptors, PID limits, TCP buffers, as part of the application's configuration. A healthy application cannot run on a restricted kernel.
The investigation steps and root cause.
As the logs remained empty, I performed a host-level resource audit. 1. Ran lsofppidwcl and confirmed the Java process was holding exactly 1024 open file descriptors. 2. Checked the cat/proc/sys/fs/filemax and saw the system-wide limit was high, but the per-process limit was low. 3. Identified that each active socket and log file and jar library counts as a single file descriptor in the eyes of the Linux kernel. 4. The root cause: OS resource misconfiguration, where a high-concurrency Java application was constrained by an outdated default process limit, ulimit, causing a socket-level denial of service.
The technical resolution.
I unblocked the kernel and implemented resource leak detection. 1. Immediately applied ulimit and 65,536 on the running nodes and restarted the Java pods to restore the connection throughput. 2. Updated our Docker security context and Kubernetes deployment YAML to explicitly set the ulimit for all production pods. 3. Implemented a custom file descriptor monitor in our Java code that exports the current count of open handles to Prometheus. 4. Refactored the WebSocket idle timeout logic to ensure that stale connections were closed and their descriptors released after 60 seconds of inactivity.
What I changed forever.
I implemented these 4 structural guardrails for OS resource safety. 1. The kernel-first triage mandated that for all connection-related incidents, the first check must be ulimit and LSOF rather than the application logs. 2. High descriptor standard established a global policy that all production Java containers must be provisioned with a minimum of 65,000 file descriptors. 3. File descriptor alerting configured a critical P1 alert that triggers if any pod consumes more than 60% of its allocated OS file handles. 4. Socket leak regression test integrated a soak test in the pipeline that monitors file descriptor growth over 4 hours and fails the build if the count does not return to baseline. We have reduced our OS-level resource incidents by 100% since adopting these monitors.
Summary card.
Key takeaway for your interview: incident type, OS resource violation and file descriptor leak. Bad decision, leaving the Linux ulimit at its default of 1024 for a high-concurrency API gateway. Impact: too many open files error causing a 60-minute global lockout and $100,000 lost revenue. Guardrail implemented: mandatory container-level ulimit provisioning and automated file descriptor alerting. Everything in Linux is a file. Do not run our fingers to hold them.
The interview-winning answer template.
During a scaling event, I made the bad decision to ignore the OS-level resource limits of our Java gateway, focusing only on JVM heap. We hit the default Linux limit of 1024 open files, which caused the application to stop accepting connections and even stop writing its own logs. This resulted in a 60-minute blackout. I resolved this by increasing the OO limit and implementing socket leak monitoring. This taught me that the kernel is part of the application stack. I have since enforced high process limits for all our containers and implemented automated descriptor tracking, which has completely eliminated invisible resource crashes.
Follow-up 1. How do you identify a file descriptor leak in a Java application if the system has not crashed yet?
Answer: I track the open file descriptors metric over time. In a healthy app, this number should rise with traffic and drop back to a stable baseline. If the count is increasing linearly while traffic is flat, we have a leak. I would use LSOFPPID to see if the descriptors are open sockets or file streams to find the leaking module.
Follow-up 2. Besides sockets and logs, what other Java operations consume file descriptors?
Answer: jar file loading, pipe creation for subprocesses, and temporary file creation via file.createTemp file, all consume descriptors. In complex monoliths, even the number of loaded library JARs can consume hundreds of descriptors before the first request even arrives.
Follow-up 3. Curveball. What if you increase the OO limit to 1 million, but the app is still throwing connection refused? What is the next limit you check?
Answer: I would check the TCP backlog SOMIXCON and the ephemeral port range. If the application is creating and closing connections too fast, it will run out of available ports in the time_wait state. I would tune the net.ip for .ip_local_port_ range and enable TCP_TW_reuse at the kernel level.
Pro tip: the kernel standard.
In a senior Java support role, remember, defaults are for desktops, not servers. Always explicitly define your OO limit, SOMIXCON, and max_map_count in your container templates. If you are relying on the OS to choose your limits, you are giving the kernel permission to fail your application.
Explain a bad decision you made. Question 93. The lagging autoscaler.
Interviewer asks, describe a mistake where you underestimated traffic spikes. Incident type: traffic surge and auto-scaling misconfiguration. Interviewer insight: this question evaluates your dynamic scaling logic. Most engineers think auto-scaling is magic. A senior engineer knows that Java startup time, cold starts, can make auto-scaling useless during a sudden spike. They want to see how you moved from reactive scaling to predictive buffering to survive a traffic surge.
The star story and reflection.
Here is the account of how a viral social media post crashed our scalable cloud cluster. Situation: we were managing a Java-based loyalty platform. We had Kubernetes horizontal pod autoscaling, HPA, configured to scale based on 70% CPU usage. Task: my task was to ensure the platform remained available during a planned marketing event where a celebrity would mention our app on live TV. Action: the bad decision plus why it happened. I made the bad decision to trust our standard HPA settings. I assumed that as traffic spiked, Kubernetes would just spin up new pods to handle the load. I failed to account for the cold start time of our Spring monolith, which took 90 seconds to fully initialize and pass health checks. Result: the impact. When the celebrity spoke, traffic jumped from 1,000 to 50,000 users in 30 seconds. The CPU hit 100% instantly. Kubernetes tried to scale, but by the time the new pods were ready 90 seconds later, the existing pods had already crashed under the load. The system entered a cascading failure where new pods died as soon as they joined the cluster. We suffered a total blackout for 45 minutes, resulting in an estimated $150,000 in lost redemption volume. Reflection: I learned that auto-scaling is not a safety net for sudden spikes. It is a tool for gradual growth. If your startup time is slow, you must prescale based on the clock, not auto-scale based on the metric. Auto-scaling is a marathon runner, not a sprinter.
The investigation steps and root cause.
As the site crashed despite having 50 new pods, I performed a scaling audit. 1. Check the HPA events and confirm the scaling signal was sent at T plus 30 seconds into the spike. 2. analyzed the pod startup latency, and saw that pods were spending 85 seconds in the pending and starting states before the first request could be handled. 3. Observed that the incoming request queue at the load balancer was growing faster than the cluster's total throughput capacity. 4. The root cause, scaling lag, where the time to ready for new Java pods exceeded the rate of traffic growth, leading to resource saturation and cascading node failure.
The technical resolution.
We stabilized the cluster and revamped our surge protection architecture. 1. Immediately increased the minimum replicas to 100 pods manually to absorb the remaining traffic surge and stop the crash loop. 2. Implemented predictive scaling, using Keta, that triggers a scale-out event based on external trigger like a schedule rather than just CPU usage. 3. Optimize the Java application startup time by enabling class data sharing, CDS, and lazy initialization, reducing the cold start from 90 seconds to 25 seconds. 4. Introduced a global rate limiter at the load balancer to queue excess users rather than letting them crash the backend pods.
What I changed forever.
I implemented these 4 structural guardrails for traffic surge protection. 1. Mandatory prescaling. Established a policy that for any planned marketing or TV event, we must warm the cluster by prescaling to 50% of the projected peak volume. 2. Startup time budgets. Set a hard SLA for application startup time, under 30 seconds. Any change that slows down the boot process is rejected by the build pipeline. 3. HPA sensitivity tuning. Configured scaling policies in Kubernetes to scale up aggressively, for example, doubling pods in 30 seconds, while scaling down conservatively. 4. Circuit breaker dashboards. Created a dedicated surge dashboard that monitors the health check success rate of new pods versus existing pods during scaling events. We have reduced our spike-induced outages by 90% since adopting predictive prescaling.
Summary card.
Key takeaway for your interview. Incident type, traffic surge and auto-scaling misconfiguration. Bad decision, trusting standard CPU-based auto-scaling for a sudden 50 times traffic spike without accounting for Java cold start times. Impact, cascading pod failure, 45-minute total blackout, and $150,000 lost redemption revenue. Guardrail implemented, mandatory predictive prescaling and strict startup time performance budgets. If you wait for the CPU to spike, you have already lost the battle.
The interview-winning answer template.
During a viral marketing event, I made the bad decision to rely on standard auto-scaling to handle the surge. Because our Java Spring monolith took 90 seconds to start, the new pods could not join fast enough to save the ones being crushed by traffic. This caused a 45-minute outage. I resolved this by manually prescaling and then optimizing our application's boot time. This taught me that auto-scaling is too slow for sudden spikes. I have since enforced a prescaling policy for all planned events and implemented predictive scaling based on event schedules, ensuring our cluster is already warm when the first user arrives.
Follow-up 1. What is Java cold start, and how does it affect cloud-native performance?
Answer: cold start is the time it takes for a JVM to load classes, initialize the Spring context, and warm up the JIT compiler. In a cloud environment, this lag means your app is non-productive for the first minute, which can lead to timeouts and load balancer eviction during scaling events.
Follow-up 2. How do you optimize a Spring Boot application's startup time in a container?
Answer: I use AppCDS, application class data sharing, to speed up class loading, and I enable lazy initialization for beans that aren't needed at startup. I also use AOT, ahead of time, compilation or Graal VM native images if the service needs sub-second cold starts.
Follow-up 3. Curveball. What if the cloud provider itself runs out of capacity to give you new nodes? How do you scale then?
Answer: this is a regional exhaustion event. I would use multi-region failover to route traffic to a different AWS or Azure region that has available capacity. I also use Spot, and on-demand instance diversification, to increase the chances of getting new hardware during a global surge.
Pro tip, the warm cluster rule.
In a senior Java support role, remember, cloud elasticity is an illusion during a spike. If your traffic growth is measured in seconds but your scaling time is measured in minutes, you are going down. Always pre-scale to your projected peak plus a 20% buffer before the event starts.
Category 20 wrap-up, the capacity lesson.
We have explored the physical limits of our systems, from the hidden ceilings of file descriptors to the lag of auto-scaling during a cold start. The lesson is that a senior engineer must architect for the burst, not the average. However, technical capacity is only one side of the coin. The other side is the business context. Even a technically stable system can fail if we misjudge which features matter most to our users. This leads us into Category 21, Business Impact Misjudgment.
Category 21, business impact misjudgment.
In high-stakes Java support, technical prioritization is a business decision. You often have 10 bugs but only time to fix one. This category evaluates your product thinking. Interviewers want to see that you understand the financial and reputational weight of different system components. They are looking for engineers who can admit when they prioritize the wrong technical task and how they developed a value-based triage model since that mistake.
The prioritization challenge, questions 94 to 96.
Be prepared to discuss these product-centric operational failures in your next interview. 94. Tell me about a time you underestimated the severity of a production issue and it escalated. 95. Describe a mistake where a technical issue you deprioritized severely affected high-value customers. 96. Tell me about a time a minor technical issue turned into a major customer-facing outage. Interviewers, evaluate your ability to align technical effort with business value.
Explain a bad decision you made. Question 94, the hidden lock.
Interviewer asks, tell me about a time you underestimated the severity of a production issue. Incident type, severity misclassification and resource contention. Interviewer insight, this question tests your cascading risk awareness. A senior engineer knows that a low-volume error in one service can become a total blackout in another if they share a common resource like a database. They want to see how you moved from error counting to dependency mapping to classify risk.
The star story and reflection.
Here is the account of how a minor audit log failure took down a $50 million trading floor. Situation: we were managing a Java-based trading platform. A secondary audit logging module began throwing occasional database timeout errors during the morning peak. Task: my task was to triage the timeouts and determine if we needed to pull the emergency stop on the trading gateway. Action: the bad decision plus why it happened. I saw that the audit module only handled 5% of total traffic and was not customer-facing. I made the bad decision to classify it as a P3 low-severity issue. I assumed that if the audit logs were delayed, the main trading flow would be unaffected. I did not check if the audit service shared a global transaction lock with the main order table. Result: the impact. The audit timeouts were caused by a row-level lock on a shared metadata table. Because the Java application used a single @transactional wrapper across both modules, the minor audit delay held the trading threads hostage. Within 15 minutes, the entire trading floor froze. We lost a 2-hour trading window, resulting in an estimated $400,000 in lost commissions. Reflection: I learned that there is no such thing as a low-priority component if it shares a synchronous resource path with a high-priority one. You must judge severity by the bottleneck, not by the feature name. Shared resources turn minor bugs into major outages.
The investigation steps and root cause.
As the trading floor became unresponsive, we audited the resource dependencies. 1. Ran show engine in NoDB status and identified a massive wait queue on the instrument underscore metadata table. 2. Captured a JStack dump and found 200 trading worker threads in blocked state waiting on a monitor held by the audit logger thread. 3. Discovered that the audit logger was attempting to update a last underscore used underscore at timestamp on the same metadata record as the live trades. 4. The root cause, resource coupling, where a non-critical audit task held an exclusive lock on a critical metadata record, causing a cascading system hang.
The technical resolution.
We broke the lock and decoupled the modules. 1. Immediately killed the audit logger database sessions to release the locks and allow the trading threads to finish. 2. Refactored the Java code to move the audit logging into an asynchronous execution block using a dedicated thread pool. 3. Removed the @transactional wrapper from the parent method to ensure the audit failure could never roll back or block the core trade transaction. 4. Moved the audit metadata to a separate audit-only table to eliminate row-level contention, with the high-velocity trading table.
What I changed forever.
I implemented these 4 structural guardrails for severity assessment. 1. Shared resource audit. Established a rule that no P3 or P4 incident can be downplayed until it is proven to have no shared database, thread pool, or lock with a P1 service. 2. Transaction scope linting. Integrated a static analysis check that flags any @transactional annotation that spans across multiple business domains, for example, trade plus audit. 3. Blast radius monitoring. Created a dashboard that maps component failure to revenue impact, automatically escalating any issue that impacts the checkout or trade paths. 4. Mandatory async for side effects. Enforced an architectural standard that all side effect operations, logging, notifications, analytics, must be asynchronous by default. We reduced our cascading outage rate by 90% since decoupling side effect modules.
Summary card.
Key takeaway for your interview. Incident type, severity misclassification and resource contention. Bad decision, classifying an audit log failure as low severity without checking for shared database locks with the main trading flow. Impact, 2-hour total system hang and $400,000 lost commissions due to synchronous resource coupling. Guardrail implemented, mandatory shared resource impact audit and asynchronous enforcement for all side effect modules. Dependency is the secret architect of your incident severity.
The interview-winning answer template.
During a morning peak, I made the bad decision to downplay a series of audit log timeouts as a low-severity issue because it was not a customer-facing feature. I did not realize that the audit module shared a critical database lock with our trading engine. This caused the entire platform to freeze for 2 hours, costing $400,000 in revenue. I resolved this by moving our logging to an asynchronous model and decoupling our database transactions. This taught me that severity is defined by shared bottlenecks, not just feature priority. I have since implemented mandatory shared resource audits for all incidents, which has completely eliminated cascading failures in our stack.
Follow-up 1. How do you explain technical debt and its impact on severity to a business manager?
Answer, I use the friction analogy. Technical debt is like driving with the handbrake on. You might still move, but you are consuming more fuel, and eventually the brakes will catch fire. I explain that ignoring minor bugs creates complexity debt that makes the next P1 incident 10 times harder to solve.
Follow-up 2. What is a circular dependency, and why is it a nightmare for incident triage?
Answer, it is when service awaits for B, and B waits for A. In Java, this often happens with synchronous API calls or DB locks. It makes triage a nightmare because both services look slow and healthy simultaneously, making it impossible to find the first mover of the failure without a thread dump.
Follow-up 3. Curveball. What if you escalate a P1 correctly, but the on-call engineer refuses to acknowledge it because they disagree with your severity? How do you lead?
Answer, I do not argue about technical opinions. I present the business fact. I say, our revenue dashboard shows a 50% drop in successful checkouts. Regardless of the technical cause, this is a P1 impact. I use the business data to force alignment and keep the incident moving toward resolution.
Pro tip, the bottleneck law.
In a senior Java support role, remember, a bug is only as minor as the resource it consumes. If a non-critical feature consumes a critical resource, like a DB connection or a thread, it is a critical feature. Always triage based on resource shared fate, not business label priority.
Explain a bad decision you made. Question 95, the VIP blind spot.
Interviewer asks, describe a mistake where an issue you deprioritized affected customers. Incident type, logic error and customer impact misjudgment. Interviewer insight, this question evaluates your customer empathy. Sometimes, a bug that affects only 0.1% of users is a disaster if that 0.1% represents your largest enterprise clients. A senior engineer explains how they moved from volume-based triage to value-based triage to protect the company's most critical relationships.
The star story and reflection.
Here is the account of how deprioritizing a low-volume login bug lost us a $1 million contract. Situation: we were managing a B2B Java SaaS platform. We received a report that users with special characters in their organization names could not log in via SSO, single sign-on. Task: my task was to triage the bug and assign it a priority for the upcoming development sprint. Action: the bad decision plus why it happened. I saw that this issue only affected 3 accounts out of 10,000. I made the bad decision to classify it as a P4 cosmetic per minor bug and push the fix to the next quarter's roadmap. I focused purely on the user volume and did not check the account value or the brand name of the impacted users. Result: the impact. One of those 3 accounts was our largest new enterprise client during their onboarding phase. Because they could not log in, they assumed our platform was not enterprise ready and canceled their $1 million annual contract during the trial period. My deprioritization resulted in a massive loss of ARR, annual recurring revenue, and a formal apology from our CEO. Reflection: I learned that average impact is a lie. In a B2B environment, you must triage by contract value and user segment. A bug that stops 1 VIP is a P1, even if the other 9,999 users are perfectly happy. Value-based prioritization is the difference between a support engineer and a business partner.
The investigation steps and root cause.
After the contract was lost, we performed a deep dive into the failure path. 1. Analyzed the SAML response logs and found a 400 bad request from the identity provider. 2. Identified that our Java string sanitization utility was stripping and in symbols from the organization field, which invalidated the security signature. 3. Found that the organization_name field was being used as a primary key in our session cache without proper URL encoding. 4. The root cause: edge case negligence, where a lack of support for non-alphanumeric characters in business metadata prevented SSO authentication for specific high-value corporate names.
The technical resolution.
We repaired the authentication logic and modernized our triage data. 1. Implemented a proper URL-safe base 64 encoding for all business metadata used in security handshakes and session keys. 2. Updated the Java SSO filter to use a relaxed character whitelist that supports all UTF-8 characters found in global legal entity names. 3. Added a VIP account tag to our CRM and integrated it with our ticketing system Jira to surface high-value impacts instantly. 4. Ran a global scan of our database to identify any other special character names and manually verified their login success using a synthetic test account.
What I changed forever.
I implemented these 4 structural guardrails for value-based triage. 1. The account tier overlay integrated our sales data into our Splunk dashboards. We now see errors by revenue tier rather than just total errors. 2. VIP failure alerting configured a high-priority P1 alert that triggers if even a single login failure occurs for a client in the enterprise or strategic tier. 3. Mandatory segment audit established a rule that every bug triage must answer: does this affect an active onboarding client or a contract renewal account? 4. Customer Success Sync initiated a weekly meeting between the support and customer success teams to align technical priorities with upcoming high-value milestones. We have had 0 churn related to unresolved technical gaps since adopting value-based triage.
Summary card.
Key takeaway for your interview: incident type, logic error and customer impact misjudgment. Bad decision, deprioritizing a minor SSO login bug because it only affected 3 out of 10,000 users. Impact, lost a $1 million annual contract as a major new enterprise client could not log in during onboarding. Guardrail implemented, value-based triage model, and real-time VIP segment error monitoring. A bug's priority is determined by the size of the check, the customer writes.
The interview-winning answer template.
Early in my career, I made the bad decision to deprioritize a login bug that only affected a tiny fraction of our users. Unfortunately, that fraction included our largest new enterprise client, who canceled their $1 million contract when they could not onboard. I resolved this by leading the code fix and then integrating our customer revenue data into our support dashboards. This taught me that triage must be value-based rather than just volume-based. I have since implemented VIP alerting and mandatory segment audits, ensuring we protect our most critical customer relationships first.
Follow-up 1. How do you handle a situation where a VIP customer is demanding a custom fix, that would make the product harder to support for everyone else?
Answer: I collaborate with product management. I frame the supportability risk as a long-term cost. I offer standardized alternatives that meet the customer's goal without breaking our core architecture. In senior support, my job is to protect the platform as much as the customer.
Follow-up 2. What is the risk of having a VIP-only support track? Does it demotivate the team handling standard users?
Answer: it can, if not managed correctly. I frame it as risk management. The standard users are the foundation, and the VIPs are the growth. We maintain high standards for all, but we provide a fast track for high-value impact to ensure the company's financial stability.
Follow-up 3. Curveball. What if the bug is actually in the VIP customer's own identity provider, but they are blaming your Java application? How do you tell them?
Answer: I provide proof of innocence with empathy. I share a sanitized log trace showing that our app correctly received and processed their request, but their server sent a malformed response. I offer to jump on a joint bridge call with their technical team to help them solve it. I act as a partner, not an adversary.
Pro tip, the segment rule.
In a senior Java support role, remember, not all errors are created equal. A 500 error on a settings page for a free user is a P4. A 500 error on the payment page for a strategic account is a P1. Always know the value of the request before you decide the speed of the fix.
Explain a bad decision you made. Question 96. The recommendation trap.
Interviewer asks, tell me about a time a minor issue turned into a customer-facing outage. Incident type: component interdependency and failure isolation error. Interviewer insight: this question reveals your resilience design awareness. Modern microservices often have hidden synchronicity. A senior engineer discusses how an optional feature, like recommendations, was accidentally made a blocking step in the main flow, and how they implemented graceful degradation to prevent it from happening again.
The star story and reflection.
Here is the account of how an optional feature brought down a $100 million revenue stream. Situation: we were managing a high-volume Java retail app. We launched a recommended for you carousel on the checkout page to increase upsells. Task: my task was to monitor the performance of the recommendation API and ensure it did not impact checkout latency. Action: the bad decision plus why it happened. I saw occasional 503 errors from the recommendation engine during a load test. I made the bad decision to allow the launch, assuming that a failure in recommendations would just leave a blank space on the page. I did not verify if the Java checkout controller had a timeout or a fallback around the recommendation call. Result: the impact. During the Friday peak, the recommendation engine crashed. Because the checkout controller was calling it synchronously with no timeout, every checkout thread hung for 30 seconds waiting for a response. The optional upsell feature effectively blocked 100% of mandatory orders. We lost 2 hours of checkout availability, resulting in an estimated $300,000 revenue loss. Reflection: I learned that there is no such thing as an optional feature unless it is isolated. If your code waits for a response from a secondary service before proceeding with the primary transaction, that secondary service is now a critical dependency. Isolation is the only way to ensure optional remains optional.
The investigation steps and root cause.
As the checkout success rate dropped to 0, we performed a thread audit. 1. Captured a JStack dump and found that 100% of the web container threads were in socket read state. 2. Identified that the threads were blocked inside the upsell client.getRecommendations method call. 3. Confirmed that the recommendation service was suffering from a garbage collection death spiral and was unable to return any data. 4. The root cause: implicit synchronous dependency, where a non-critical feature was integrated into the critical checkout path without a circuit breaker or a fallback.
The technical resolution.
We stabilized the checkout flow and implemented graceful degradation. 1. Immediately applied a feature flag to disable the recommendation call, which instantly unblocked the checkout threads. 2. Refactored the Java code to use Resilience 4J and wrapped the upsell call in a circuit breaker with a strict 200 milliseconds timeout. 3. Implemented a safe fallback that returns an empty list if the service is slow, allowing the checkout page to render without the carousel. 4. Move the recommendation fetch to a client-side AJAX call so it happens after the initial page load, completely decoupling it from the server-side checkout logic.
What I changed forever.
I implemented these 4 structural guardrails for feature isolation. 1. Mandatory failure mode triage. Established a rule that every new API integration must include a documented what happens when this is down. Impact assessment. 2. Default timeout standard. Enforced a global standard that no synchronous network call can be added to the code without an explicit 1 second or lower timeout. 3. Circuit breaker first policy. Established a technical mandate that all non-Tier 1 features must be wrapped in a circuit breaker before being promoted to production. 4. Front-end decoupling standard. Mandated that all discovery or engagement features, recommendations, chatbots, ratings, must be loaded via client-side scripts to protect the server-side flow. We have reduced our cascading blackout incidents to 0 since adopting component isolation.
Summary card.
Key takeaway for your interview. Incident type, component interdependency and failure isolation error. Bad decision, allowing an optional upsell feature to run synchronously in the checkout path with no timeout or circuit breaker. Impact, total checkout blackout for 2 hours and $300,000 revenue loss when the secondary recommendation engine failed. Guardrail implemented. Mandatory resilience, 4J circuit breakers, and client-side decoupling for all non-critical features. If a feature is not mandatory for the customer to buy, it should not be mandatory for the system to run.
The interview-winning answer template.
During a feature launch, I made the bad decision to allow an optional recommendation engine to run synchronously in our core checkout path. When the recommendation engine slowed down, it held our checkout threads hostage and crashed the entire site for 2 hours, costing $300,000. I resolved this by disabling the feature and implementing circuit breakers and fallbacks. This taught me that non-critical features must be physically and logically isolated. I have since enforced a policy of client-side decoupling and mandatory timeouts for all secondary services, ensuring our core business flow remains indestructible.
Follow-up 1. How do you perform chaos testing to find these hidden dependencies before they hit production?
Answer: I use tools like Gremlin or AWS Fault Injection to simulate latency or 503 errors in our non-critical dependencies. If the main flow, like checkout, fails during these tests, we know we have a hidden coupling that must be decoupled before release.
Follow-up 2. What is graceful degradation, and how does it improve the user experience during a partial outage?
Answer: it is the ability of a system to maintain core functionality when secondary components fail. Instead of a 500 error, the user sees a simplified page. It turns a total disaster into a minor inconvenience, which maintains customer trust and protects revenue.
Follow-up 3. Curveball. What if the minor issue is actually in the load balancer health check itself? How do you diagnose that?
Answer: I look for flapping pods. If the application is healthy but the load balancer is constantly removing and adding it back, I check the health check timeout. Often, a slow, deep health check is timing out at the load balancer layer, causing a healthy app to be treated as dead.
Pro tip: the dependency law.
In a senior Java support role, remember, every synchronous call is a hard dependency. If you want a feature to be optional, you must use an asynchronous call or a circuit breaker with a fallback. If you cannot survive its failure, it is not optional. It is a critical vulnerability.
Category 21 wrap-up, the business lesson.
We have seen how technical decisions, like deprioritizing an edge case bug or coupling an optional feature, can have massive financial consequences. The lesson is that a senior engineer must always translate technical risk into business impact. However, our ability to make these judgments depends entirely on the tools we use to see the system. If our tools lie to us, our decisions will be flawed. This brings us to our final category, Category 22, Observability Tools.
Category 22, Observability Tools.
Observability tools like Grafana, Dynatrace, and Datadog are the eyes of a support engineer. But as systems grow in complexity, these tools can sometimes provide misleading signals through incorrect aggregation, clock skew, or bias percentiles. This final category evaluates your tool maturity. Interviewers want to see that you do not blindly trust a dashboard, but instead understand the underlying data and how to verify it when the visuals do not match the reality.
The Tool Maturity Challenge, questions 97 to 99.
Be prepared to discuss these advanced observability traps in your next interview. 97. Tell me about a time monitoring dashboards misled your debugging process. 98. Describe a situation where APM traces pointed to the wrong service during an incident. 99. Tell me about a time when metrics aggregation hid the real issue until it was too late. Mastering the tools means knowing exactly when to stop trusting them.
Explain a bad decision you made. Question 97, the average trap.
Interviewer asks, tell me about a time monitoring dashboards misled your debugging. Incident type, observability misinterpretation and percentile bias. Interviewer insight, this question tests your statistical literacy. Junior engineers look at averages, mean. Senior engineers look at percentiles, P99, and histograms. They want to see how you realize that a green dashboard was masking a critical failure for a subset of users.
The star story and reflection.
Here is the account of how a healthy dashboard blinded me to a massive user impact. Situation: we were managing a Java-based global shipping API. Our primary dashboard tracked the average latency of our shipping rate requests. Task: my task was to monitor the service during a peak Monday morning window and ensure we stayed within our 500 milliseconds latency SLA. Action: the bad decision plus why it happened. The dashboard showed a steady 150 milliseconds average latency, which was perfectly green. I made the bad decision to ignore a handful of single-user complaints in Slack, assuming they were local ISP issues. I trusted the aggregate average on my screen because I believed the dashboard represented the whole truth. Result: the impact. While the average was 150 milliseconds, our P99 latency had exploded to 30 seconds for all users in the APAC region due to a misconfigured CDN edge. 10% of our global users were experiencing a total blackout, but because 90% were fast, the average remained healthy. We lost 3 hours of business in Asia, resulting in an estimated $60,000 revenue impact. Reflection: I learned that averages are the most dangerous metric in support. They hide the suffering of the minority. If you do not monitor the tail latency, P95, P99, your dashboard is just a tool for confirmation bias. Averages lie, percentiles tell the truth.
The investigation steps and root cause.
Once I looked past the primary dashboard, I performed a multidimensional audit. 1. Switched the Grafana view from mean to P99 and saw a vertical spike that reached the 30-second timeout limit. 2. Grouped the latency metrics by geography and identified that the failure was isolated to the Singapore and Tokyo regions. 3. Checked the CDN, Cloudflare, logs and found a WAF web application firewall rule that was accidentally blocking legitimate Java API payloads from those IPs. 4. The root cause, metric smoothing, where a healthy majority masked a catastrophic regional failure on a global dashboard that lacked geographic granularity.
The technical resolution.
We restored the regional traffic and re-engineered our observability. 1. Immediately whitelisted the impacted API patterns in the CDN to restore connectivity for APAC users. 2. Updated the Java application to export latency distribution histograms instead of just counters, providing better resolution for tail events. 3. Redesigned our primary health dashboard to display P50, P95, and P99 as 3 separate lines to make tail outliers visible at a glance. 4. Configured regional synthetic probes that ping the API from 10 different global cities to detect local outages independently of aggregate traffic.
What I changed forever.
I implemented these 4 structural guardrails for dashboard accuracy. 1. The anti-average mandate established a hard rule that all SLA alerts must be based on P99 or P95 metrics, never on the mean or average. 2. Multi-dimension dashboards mandated that every global dashboard must have regional and cluster-level breakdowns to prevent local issues from being hidden. 3. Heat map visualization. Migrated our latency monitoring to heat maps, which show the full distribution of all requests, making it impossible for a cluster of failures to hide. 4. Dashboard accuracy audits. Initiated a monthly blind spot review where we compare dashboard data against raw access logs to ensure our aggregation logic is not masking errors. We reduced our regional outage detection time by 90% after implementing tail latency monitoring.
Summary card.
Key takeaway for your interview: incident type, observability misinterpretation and percentile bias. Bad decision, relying on a green average latency dashboard while ignoring individual regional complaints. Impact: 3-hour regional blackout for PSC users and $60,000 revenue loss. Guardrail implemented: mandatory P99 tail latency alerting and geographic-specific dashboard breakdowns. Never let a mean metric make you act mean to your customers.
The interview-winning answer template.
During a regional network outage, I made the bad decision to trust our green average latency dashboard, which showed a healthy 150 milliseconds response time. I did not realize that 10% of our users were experiencing 30-second timeouts because the average masked their suffering. I resolved this by switching to P99 monitoring and regional health probes. This taught me that averages are dangerous in distributed systems. I have since enforced a policy where all critical alerts must be based on tail latency percentiles, ensuring that even a small subset of failing users is immediately visible to our support team.
Follow-up 1. Why is P99 better than average, mean, for detecting Java garbage collection issues?
Answer: GC pauses are outlier events. A 2-second stop-the-world pause once every minute will barely move the average latency of 1,000 requests. However, it will cause a massive, obvious spike in the P99 metric. P99 is essentially a GC sensor.
Follow-up 2. What is percentile aggregation, and why cannot you just average the P99 seconds from different servers?
Answer: you cannot average percentiles. If server A's P99 is 1 second and server B's P99 is 10 seconds, the cluster P99 is not 5.5 seconds. This is the error of aggregation. To get a true cluster P99, you need to use histograms or T-digests that preserve the original distribution of data across all nodes.
Follow-up 3. Curveball. What if your P99 is 10 seconds, but your users aren't complaining? Is it still an incident?
Answer: I would check the context. If the 10-second latency is on a background PDF generation task, it might be acceptable. If it is on the login or checkout button, it is a P1 disaster. I always correlate technical latency with user action priority before deciding the urgency.
Pro tip: the tail rule.
In a senior Java support role, remember, you live and die in the tail. The average user is happy, but the users in the P99.9 are the ones who cancel their contracts and call the CEO. If you aren't monitoring the tail, you aren't supporting the business.
Explain a bad decision you made. Question 98. The ghost trace.
Interviewer asks, describe a situation where APM traces pointed to the wrong service. Incident type: distributed tracing misalignment and span propagation error. Interviewer insight: this question reveals your understanding of asynchronous tracing. In modern microservices, trace context can become corrupted during thread handoffs. A senior engineer explains how they misdiagnosed a bottleneck because of a stale trace, and how they implemented strict context propagation to ensure truth in their telemetry.
The star story and reflection.
Here is the account of how a lying trace led to a 4-hour developer wild goose chase. Situation: we were troubleshooting a high latency issue in our order fulfillment flow. Our app dynamics showed a 15-second trace where the time was being spent in a downstream email notification service. Task: my task was to identify the root cause of the slow fulfillment and coordinate with the team owning the bottleneck. Action: the bad decision plus why it happened. I blindly trusted the APM waterfall visualization. I made the bad decision to page the email service team at 11 p.m. and forced them to spend 3 hours auditing their SMTP servers and database. I followed the visual evidence without verifying the span timing at the network layer. Result: the impact. The email service was perfectly fast, responding in 200 milliseconds. The APM trace was lying because our main Java app had a bug in its async thread wrapper that did not close the parent span until 15 seconds later. We wasted 12 man-hours of senior dev time and delayed the fulfillment fix by 4 hours, causing a $100,000 backlog. Reflection: I learned that an APM trace is a software construct, not a physical fact. If the trace context is not handoffed correctly between Java threads, the trace will stretch or break, pointing to a downstream service that is actually innocent. A trace is only as accurate as the thread handoff that carries it.
The investigation steps and root cause.
Once the email team proved their innocence, I audited the tracing instrumentation. 1. Used TCP dump to capture the XB3 trace ID headers and confirm the email service returned a response in 210 milliseconds. 2. Inspected the fulfillment service Java code and found a completable future block that was missing a span.finish parentheses call in its terminal stage. 3. Identified that the parent span was being kept open while the thread was returned to the pool, making it look like the child call was still active. 4. The root cause, stale span context, where a failure to explicitly close a tracing span during an asynchronous thread handoff caused a false latency reporting for downstream dependencies.
The technical resolution.
We corrected the tracing logic and implemented a validation layer. 1. Immediately refactored the async wrapper to use the Open Telemetry Context Propagator, ensuring spans are closed automatically when a thread finishes. 2. Added a finally block to all custom executor service wrappers to ensure any dangling tracing contexts are cleared before the thread is reused. 3. Implemented span event logging, which records the exact microsecond a network call is made and received, providing a network fact to verify against the trace visual. 4. Conducted a team-wide trace interpretation workshop to teach engineers how to identify context leaks by looking at gap times in waterfalls.
What I changed forever.
I implemented these 4 structural guardrails for tracing integrity. 1. The correlation sanity rule established a rule that for any P1, we must verify APM latency against service-level access logs before paging a downstream team. 2. Auto-instrumentation standard mandated the use of Java agent-based auto-instrumentation rather than manual SDK spans to reduce human error in context management. 3. Tracing integration tests added a telemetry validation test suite that proves trace context is preserved across 100% of asynchronous handoffs during the build. 4. Negative time alerts configured a diagnostic alert for any trace showing gap time, parent minus child duration, exceeding 2 seconds, flagging potential instrumentation bugs. We reduced our wrong team escalations by 100% after adopting trace sanity checks.
Summary card.
Key takeaway for your interview: incident type, distributed tracing misalignment and span propagation error. Bad decision, blindly trusting a 15-second APM trace waterfall and paging the wrong downstream team at 11 p.m. Impact: 12 lost developer man-hours and a 4-hour delay in fixing a critical fulfillment bug. Guardrail implemented: mandatory verification of traces against access logs and automated context propagation testing in CI/CD. A trace is a story. Always check the source logs to see if the story is true.
The interview-winning answer template.
During a high-latency incident, I made the bad decision to blindly trust our APM trace, which showed a downstream service was slow. I paged that team and wasted 3 hours of their time, only to discover the latency was a trace leak in our own Java async code. This taught me that instrumentation can be misleading. I have since implemented correlation sanity checks where we must verify traces against raw access logs before escalating. I also enforced open telemetry standards for all thread handoffs, which has completely eliminated misleading telemetry in our cluster.
Follow-up 1. How do you handle clock skew when tracing a request across 10 different physical servers?
Answer: clock skew can make a downstream call look like it started before the upstream call. I ensure all servers use NTP network time protocol for millisecond level sync. I also use relative timestamps, duration, in the tracing tool to analyze bottlenecks rather than relying on absolute system time.
Follow-up 2. What is the overhead of full tracing, 100% sampling, in a Java application processing 10,000 requests per second?
Answer: the overhead can be significant, 10 to 20% CPU, due to object allocation and network export. In a senior support role, I advocate for probabilistic sampling at 1% for baseline health and dynamic upsampling to 100% only during an active incident investigation.
Follow-up 3, curveball. What if you see a broken trace where the IDs do not match? How do you restitch the story together?
Answer: I use the business identifier. I search all logs across the cluster for the order_ID or correlation_ID. Even if the APM tracing context was dropped, the business key allows me to manually reconstruct the sequence of events across different microservices.
Pro tip, the waterfall trap.
In a senior Java support role, remember, the waterfall does not show the code, it shows the timer. If you see a long gap between spans, do not look at the network, look at your Java thread pool. Your app might be pausing the work before the timer is even started.
Explain a bad decision you made. Question 99, the zombie pod.
Interviewer asks, tell me about a time metrics aggregation hid the real issue. Incident type, aggregation bias and zombie node syndrome. Interviewer insight, this final question tests your fleet awareness. In a cluster of 1,000 pods, a 1% failure rate is a minor blip to an aggregate metric, but a total failure for thousands of users. A senior engineer explains how they moved from global averages to outlier detection and anomaly per node alerting.
The star story and reflection.
Here is the account of how our 99% success rate hit a 100% failure for our VIPs. Situation: we were managing a high-scale Java cluster of 100 pods in Kubernetes. Our primary dashboard monitored the total cluster success rate. Task: my task was to ensure the global success rate remained above 99.5% to meet our contractual business SLA. Action: the bad decision plus why it happened. For 6 hours, the dashboard showed a steady 99.1% success rate. I made the bad decision to ignore the 0.4% drop, assuming it was just network noise or client-side disconnects. I trusted the aggregate number because it was still within the margin of error. Result: the impact. The 0.9% of errors were all coming from one single zombie pod that had a corrupted local cache. That pod was receiving 1% of traffic and failing 100% of its requests. 5,000 users were hitting that pod and were unable to log in for 6 hours. Because we only looked at the SUM, the failure was mathematically invisible. We lost $50,000 in revenue and received hundreds of angry customer tweets. Reflection: I learned that healthy in aggregate can mean dead in reality. In a large fleet, you must monitor the minimum success rate per pod, not just the total success rate of the cluster. One bad apple will rot the customer experience. Aggregation is the curtain that hides the zombie pods.
The investigation steps and root cause.
As the support tickets accumulated, I performed a per-node health audit. 1. Used Prometheus to group by pod_name for the 500 error rate and identified orderpod AF42 was showing a 100% failure line. 2. Ran kubectl logs orderpod AF42 and found thousands of access denied exception errors that were not appearing on other pods. 3. Found that the zombie pod had failed to refresh its internal IAM credentials, leaving it in a permanently unauthorized state while still passing basic liveness probes. 4. The root cause, aggregation masking, where a cluster-wide metric diluted the impact of a single node failure, allowing a critical service gap to persist for hours.
The technical resolution.
We terminated the zombie and re-engineered our fleet health detection. 1. Immediately ran kubectl delete pod orderpod AF42, which allowed the deployment to spin up a fresh pod with valid credentials. 2. Implemented a fleet variance alert in Prometheus that triggers if any single pod's error rate deviates by more than 10% from the cluster average. 3. Added a self-termination logic in the Java code. If a pod fails 10 consecutive security handshakes, the JVM calls system.exit, 1 to force a Kubernetes restart. 4. Integrated success rate per pod tiles into the primary Grafana dashboard using a heat map to visualize outliers instantly.
What I changed forever.
I implemented these 4 structural guardrails for fleet observability. 1. Outlier-based alerting. Established a policy that no global average can be used for P1 alerts. All alerts must now look for node-level deviations. 2. Automatic zombie killing. Configured a Kubernetes operator that monitors pod health and automatically evicts any node showing a sustained high error rate. 3. Error density monitoring. Mandated the use of quantiles in our metrics, for example, the 99th percentile of error rates per node, to catch local failures instantly. 4. Credential handshake probes. Redesigned our Kubernetes readiness probes to include a security token check, ensuring a pod is not ready if it cannot authenticate. We have reduced our unnoticed node failure time from 6 hours to 60 seconds.
Summary card.
Key takeaway for your interview: incident type, aggregation bias and zombie node syndrome. Bad decision, trusting a 99% global success rate while a single pod was failing for 100% of its users. Impact: 5,000 users blocked for 6 hours and a $50,000 revenue loss due to a mathematically hidden failure. Guardrail implemented. Mandatory outlier detection, alerting, and automated security token health probes. Support the one user, not the average user.
The interview-winning answer template.
During a high-scale service operation, I made the bad decision to trust our global 99% success rate metric. I ignored a small 0.4% drop, only to find that one zombie pod was failing 100% of its requests for 5,000 users. I resolved this by evicting the pod and implementing outlier detection alerting. This taught me that aggregation is the enemy of support. I have since enforced a policy where we alert on node-level deviations, ensuring that even a single pod failure is detected and self-healed in seconds, regardless of how healthy the rest of the cluster looks.
Follow-up 1. What is zombie pod syndrome, and why is it so common in Java environments?
Answer: it happens when a pod stays alive according to Kubernetes. The JVM process is running, but it is dead to the business, for example, credentials expired, internal thread pool deadlocked, or local cache corrupted. It is common because liveness probes are often too shallow to detect deep application logic failures.
Follow-up 2. How do you configure a deviation alert in Prometheus to catch these outliers?
Answer: I use the stddev, standard deviation function. I compare the error rate of an individual pod against the average and stddev of the whole consumer group. If a pod is 3 standard deviations away from the mean, it triggers an anomaly alert.
Follow-up 3. Curveball. What if all pods start failing at once? Does your deviation alert still work?
Answer: no, because the variance would be 0. This is why we need dual-layer alerting. We use deviation alerts to catch the zombies, single pod issues, and static threshold alerts, for example, greater than 5% global error, to catch massive outages like a broken DB or network failure.
Pro tip: the outlier law.
In a senior Java support role, remember, the average is for the boardroom, the outlier is for the engine room. Your users do not live in an average, they live in their own specific session. If you do not hunt the outliers, you are leaving your users to fail in silence.
Category 22 wrap-up. The observability lesson.
We have concluded our deep dive into observability tools. The final lesson is that your dashboards are only as good as the math behind them. Whether it is avoiding the average trap or identifying zombie pods in a massive cluster, a senior engineer must always look past the visual summary to find the raw data. Mastering these tools means knowing exactly when they are providing a clear signal and when they are masking a critical failure.
Part 2 wrap-up. Strategic operational leadership.
In this second part of our series, we moved beyond the tactical fixes to the strategic challenges of modern support. We covered 45 high-level scenarios across security, Kubernetes, Kafka, and complex Java concurrency. These are the domains that define a senior or lead application support engineer. By focusing on architectural isolation, data integrity, and cross-team collaboration, you have demonstrated the maturity required to manage mission-critical systems in the cloud.
The 99-question legacy. A complete support handbook.
Across this 2-part series, we have shared 99 real-world production stories covering every corner of the Java ecosystem. In Part 1, we established the foundations of JVM tuning, database management, and tactical incident response. In Part 2, we scaled those skills to the distributed world of containers and event-driven architecture. If you missed any part of the first 54 questions, please check the link in the description to complete your technical preparation.
Final step, secure your senior role.
The behavioral question, "Tell me about a bad decision you made," is no longer a threat to your interview. It is now your greatest opportunity to show expertise. Use our 9-part framework to turn your mistakes into evidence of your leadership. If this reference grade guide has helped you feel more confident for your next senior Java support interview, please subscribe to the channel and hit the notification bell. We are committed to providing the technical depth you need to pass your interviews and secure your next job offer. Good luck on the production floor.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, and system design. Required for your Java job interviews like Java Application Support Engineer jobs, AWS Java Developer jobs, Java Backend Developer jobs, Site Reliability Engineer SRE jobs, Java DevOps Engineer jobs, Java Kubernetes Developer jobs, Java Blockchain Developer jobs, Application Security Engineer jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem solving, interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people. Also for your interviews, you people can download all 6 PDFs in a single zip file from below given links. For more exciting tips, tricks and more importantly, for valuable insights of interviews, please share, like, and subscribe to my channel. It has a lot of valuable information about various insights of interviews. It has a wide range of real-world portfolio projects of various technologies for interviews, and it has wide range of most asked interview questions and answers of various technologies like data science, SAP, AWS, DevOps, and full-stack web development, and more. That will be useful during interviews. It has a wide range of most asked interview questions and answers and real-world portfolio projects of various technologies for freshers, for 2 to 3 years, experienced candidates, and for 5 or above years, experienced candidates to test their skills by knowing most asked interview questions and make themselves ready for interviews.